in a daze. Why do I feel like I have been here before? Find me a way from this place. I can't escape anymore, and I'm losing sight, unsure where I'll land when I close my eyes. Brings back who I am. Bring back who I am. Bring back who I am. I'm counting the days I have been walking, can't seem to find any door. I can't run away, stuck to the surface, can't seem to lose the floor. And I'm losing sight, unsure where I'll land when I close my eyes. Brings back who I am. Bring back who I am. Bring back who I am. told you should get laid out. Every girl is mine, didn't know it, just you make you fly, girl. Shut your eyes and breathe, I show you my world. My lips make it rain, I get you high, girl. Get you high, girl. Every girl is mine, didn't know it, just you make you fly, girl. Shut your eyes and breathe, I show you my world. My lips make it rain, I get you high, girl. Get you high, girl. Everybody slip through my window, head chased by my pillow. Get it, you have and I won't make you better. No, they don't want me there. For all of the lies that I told you and everybody slip through my window, head chased by my pillow. Get it, you have and I won't make you better. No, they don't want me there. For all of the lies that I told you should get laid.
Tell me something, do you regret it? Hanging all your dreams like coats and the way we had it. Tell me something, are we pretending like this 3-year dead end road is still something magic? Cause I don't wanna be the one holding you down. I'll never be alone here wearing a crown. I gave you everything, but I know better now. I gotta let go, I just wish I knew how. I just wish I knew how. I gotta let go, I just wish I knew how. Just wish I knew how. There's no good reason to call it over. Just a feeling in my bones and I can't ignore it. Good on paper, you're going nowhere. See that look inside your eyes and it's getting colder. I've been getting dizzy from all this back and forth. Tell me am I losing my head, losing my heart? every dawn. From the hate that was there before it was gone. Bathing in your love again, I can't really just be your friend. You know I'm ready for the end. Can't fix it from the inside. Need help from the outside. Make me feel tied up. Bathing in your love again, I can't really just be your friend. You know I'm ready for the end. So come on.
Hello.
Hey, how are you doing?
All good? You do?
Yeah, see how that works?
Yeah, that's it.
Hello, guys. This is
Hello.
Mario on the technical support. Will you be speaking on this session?
So
I will be.
I'm one of the chairs, and Ili is the fourth speaker.
It's,
Oh, sorry, they told me that both chairs were on site, but that's not true.
Nope, I told them that I'm going to be remote, but they didn't pass it
Okay.
on apparently.
And Ellie, will you be speaking now?
yes, I'm the fourth speaker in the next session. Yes.
Okay. Do you have a presentation?
Yes, I do.
Can you please make sure that you can share your screen?
Let's give it a shot. So, can you see it?
Yeah, that's perfect. So
Okay.
when you start, can you start with that screen share? I'm using NDI, so I can bring your video separately. You're muted.
Yeah. Can you go again, please? I couldn't hear that.
Um,
I can tell no one what you've been. Things are about to change, it's evolution. Wait to shake the ground, you feel it moving. With the revolution.
You might be lost like sunshine in the night. You know what they say, life's about to end. If you wanna be someone, you don't have to wait. You just have to change. What if I were you? Would it be easier for me to be heard and to be seen? What am I supposed to do? Is it all now up to you? I am not that strong. I don't even know where I belong. You just have to try harder than you fight. You might be lost like sunshine in the night. You know what they say, life's about to end. If you wanna be someone, you don't have to wait. You just have to try harder than you fight. You might be lost like sunshine in the night. You know what they say, life's about to
All right. Oh, good. Ooh. All right. Welcome to the next Blue Sky session, the second Blue Sky section. And what we're going to do is we have 4 incredible speakers. I'm going to get off immediately to let them start. But there's a little competition, which is if whoever can figure out the common denominator among these 4 talks, okay? And it can't be just like robot learning, okay? It's got to be something really, really interesting and clever. So think about that as they go. All right, the first one up is Kayleen Stocking from UC Berkeley. Kayleen.
All right, thank you all for being here bright and early. So I'm going to be talking about work with my collaborators, Alison Gopnik and Claire Tomlin. And the title of my talk is From Robot Learning to Robot Understanding, which is a little bit ambitious, but hopefully over the next few minutes, I can convince you that maybe there is in fact something sort of to this. So consider this situation where you have a little pizza delivery robot that is trying to deliver some pizza by rolling along the sidewalk towards the top of the screen. Now, if you live in an area where these robots are common, you may have heard the rumor that they are in fact teleoperated by humans. So imagine for a second that you are a human in charge of controlling this robot and getting it to its destination. Now, when you encounter this situation, you need to be able to safely navigate around pedestrians. And looking in this particular case, you can see that this human is standing by a bus stop. And so it's quite reasonable to infer that they're probably waiting for a bus. And since there's no bus in sight, they're probably not going to move anywhere. And so it does seem like it is, in fact, probably safe to go ahead and pass this pedestrian on the sidewalk. But we can also consider this alternative situation where there's a soccer ball on the other side of the sidewalk. And in this case, a quite reasonable hypothesis that sort of seems to come to mind is that maybe the human just dropped or kicked this soccer ball, and therefore they might be about to run across the sidewalk to go retrieve it. And so in this case, we want to be a little bit more cautious about continuing to go forward in this situation. And so that's sort of our reasonable conclusion here. Now, what we really want is for this robot to be autonomous and to make this kind of decision on its own. But looking at these 2 figures, we can imagine that the appearance of the human might be quite similar in these 2 cases. And so a good question is like, how does the robot disambiguate between these 2 scenarios and figure out which of these is safe and which is not? And we can imagine that especially for these more rare edge cases, especially like the soccer ball situation, we might not have data in our training distribution that this robot has seen before that it can leverage to figure out that this situation is unsafe. And even though you have probably never been in this exact situation, you can probably still come to the conclusion that the soccer ball situation warrants extra caution. And so somehow we're able to do this without having seen this prior exact situation before. So how can we give this ability to the robot? Well, if just doing deep learning isn't good enough, we might think that maybe a model can help instead. So for a model to be useful in this situation, I think there are a few different criteria that we would like it to fulfill. So first of all, it should be able to represent the relationships between objects, such as between the human and the soccer ball. It should be able to predict future states of the scenario, contingent on how the robot is interacting with the world. It should be able to handle the uncertainty and dynamicism inherent to interacting with the real world. And finally, it should be able to support online inference so that it can really operate in real time. And so I think that there is actually a kind of model that might fulfill all of these criteria, and that's the causal graphical model. So just to give a brief overview of how these work, we can assign each object or variable in this scene a node in a causal graph. And each of these nodes is going to be associated with some probability distribution over possible values it can take on. So in this example, we might have a hypothesis that the human is waiting for the bus or that they are playing with a ball. And so these can be our 2 different values. And then finally, we're going to have causal relationships between each pair of nodes. And this is going to tell us how the probability distribution of one variable is going to be affected by the value of other variables. And these relationships between nodes is really what's going to allow us to perform inference and to make good predictions about novel situations. So returning to our motivating example, if we observe the human by the bus stop, and we have these 2 candidate models that I have here below, The one on the left is representing a human waiting for a bus, and the one on the right is representing a human playing with a soccer ball. And if we have these two candidate models, we can sort of use the evidence from the scene, namely the fact that there is a bus stop there and not a soccer ball, to realize that the model on the left is in fact a lot better description of this scene. And furthermore, we can use the relationships encoded in this model to infer that because the human is not very likely to run across the sidewalk, it is in fact probably going to be safe to pass them. And we can do a similar procedure with the soccer ball situation, where we can infer that the model on the right is a better fit, and that furthermore, we need to be a little bit more careful about continuing to go forward. This sort of begs the question, however, like even if we can do this inference and get really good predictions, we need to have these good candidate models before we can do this procedure. And this is really the key question, where do these models come from? And this has been called a lot of different things by different people. For example, it's been called the frame problem by the philosopher Hubert Dreyfus. And we can take, but all is not lost, because we can take inspiration from emerging ideas from cognitive science about how humans are able to solve this problem. So for example, one possibility is that if we represent the space of all possible models for a particular situation, the process of choosing candidate models could be considered a stochastic search problem. And we could do better at this stochastic search, for example, by learning prior distributions that might be conditioned on things like the current task that we're trying to execute or the current setting. Once we've drawn candidate models from this stochastic search space, we might also want to be able to refine them. And for this, we might be able to take inspiration from things like how humans intentionally improve our hypotheses by doing things like trying to make them simpler or more accurate. And so these gives us some ideas of how we might be able to do this. Now, even though we have some ideas, this might all seem quite, vague and difficult to you, and that probably because it is quite vague and difficult. But I want to take the last few moments to try and convince you that this is a good idea, even though it's quite difficult. So we know that interaction with the world is really critical for learning, and specifically learning for both animals and robots. And this is something that we have leveraged in reinforcement learning. But reinforcement learning only gives you causal information with respect to a particular reward function. And a really key hallmark of human intelligence and human learning is that we are able to take causal information that we've learned while performing one task and flexibly apply it to other tasks that have nothing to do with what we were doing before. And causal theories appear to be a really key part of how we are in fact able to do this. And so I think that this really presents a really wonderful opportunity for emerging research in cognitive science and how the human mind works to help inform better algorithms for robots to sort of be able to leverage these same kinds of abilities. And furthermore, for the tasks and platforms of robotics to help test and refine our theories about how human causal modeling works. So my hope is that by sort of leveraging this virtuous cycle, we will in fact be able to transition at least a little bit from robots that learn to robots that understand. Thank you.
Thank you, Kayleen. Great. So we're going to hold questions until the panel. So we'll have a chance for all four speakers. So write down your questions so you don't forget which ones you want to ask Kayleen. And next we're going to bring up Victoria Dean from Carnegie Mellon.
Hello, I'm Victoria, and I'm here to talk about Robots on Demand, our vision for a democratized robotics research cloud, with Yo Shavit and my advisor Abhinav Gupta at Carnegie Mellon's Robotics Institute. Gonna need the clicker for this. Imagine someone trying to get started in robotics research. First, she has to obtain a robot. Then she tries to set up ROS, but the networking's a mess. After days of trying to get libraries to play nicely with each other, she finally sets up the software infrastructure. But she doesn't have a task. After picking all of the sets of objects to grasp and tuning the success metrics, she's finally completed all the setup just to start her project. Unfortunately for her, her method turns out to require millions of samples. And that's not including the baseline she has to recreate. Back to simulation she goes. Meanwhile, the computer vision researcher has written 3 papers in time to submit to CVPR next week. How does he do it? He uses a GPU cluster with an easy interface for parallelizing experiments. He has software tools and open source baselines that make it easy to get started. And last but not least, he has access to large-scale datasets. The vision researcher is free to focus on developing new algorithms rather than the extraneous work that the robotics researcher is still stuck on. So the question is, how can we make research on real robots as easy as computer vision is? Enter the Robotics Research Cloud, a physical center filled with real robots in which a researcher can remotely submit experiments that will run on these robots. Common tasks and environments act as benchmarks, and all of the experiment data is open sourced. We've seen all of these components in prior efforts, but we need to put them all together at scale. With the Robotics Research Cloud, the field will look pretty different. Research won't be limited to those with robotics expertise and the resources to afford real robots. An ML researcher with no hardware experience could conduct real-world experiments, or even a high school student could participate. All CoRL submissions will have experiments on real robots, so we won't have to debate whether to reject a paper because they didn't have real-world results. And finally, when everyone has access to the same hardware, anyone can show that their method is the best. Labs with the most resources won't just have state-of-the-art results because they had the best robots to train on. A number of questions remain which will guide the design of such a cloud. First, we'll have to pick the robots. We could use off-the-shelf robot arms, though these might become obsolete over time. We could also use more forward-looking technologies like hands or soft robots, which would allow hardware researchers to have a real experimental testbed. Next, we'll need to pick which kind of tasks to use as benchmarks. They should allow for autonomous resets and evaluation, and possible manipulation tasks would be pouring, scooping, or writing. The level of abstraction will change the user interface and experience. So giving more direct access allows for flexibility, but the lack of constraints could lead to safety issues. Next, do we need teleoperation for trying out tasks or collecting demonstrations? Having real-time remote teleoperation might require more engineering investment. Finally, this will be an expensive effort, which will require combining multiple funding sources. We've seen interest from both government and industry sources, and we're actively pursuing both. So let's say that we can get good answers to all of these open questions. Then we can look at a timeline for scaling up the first robotics cloud center in the next 5 years. The initial work is in developing infrastructure, which we're actually already doing. With seed funding from Schmidt Futures, we're creating a remotely operable robot interface. Next, we'll need to scale up the robots. We'll decide on and acquire the relevant hardware by next fall. By spring 2023, the robots are assembled and available for remote access by a select set of labs, and their experiments will inaugurate the open source dataset. That summer, the center will begin operations with the experiment queue open to the larger community. The following 2 years of use with 100 robots will lead to 400,000 robot hours. If we estimate that a robotics paper takes 100 robot hours worth of experiments, then this would lead to 4,000 papers by 2025. As you can see, the Robotics Research Cloud holds a lot of promise and also asks a lot of questions. If you have thoughts, we'd love to hear from you during Q&A. You can also visit roboticscloud.org to get involved or email us directly. We look forward to making this dream a reality with help from all of you. Thanks.
Thank you, Victoria. I appreciate that. It was a kind of a blue sky wish, and then you're actually going to deliver it. 4,000 papers. I like that that metric. Okay, terrific, excellent. I should acknowledge Jens Kober. Jens is online. He's virtually here, and he's going to be helping us co-chair this session. And especially the fourth speaker. But before that, we have Martin Riedmüller from DeepMind, who's going to give us another entry into the competition of What is the common denominator? Martin.
So welcome everybody. I'm going to talk about collect and infer, which hopefully gives us a fresh look on data efficient reinforcement learning. And this is joint work with my co-authors, Toby Springberg, Roland Hafner, and Niklas Hayes. And also a lot of discussion with my team and other colleagues at DeepMind has gone into this work. So reinforcement learning is becoming more and more important in robotic control. There's famous work by Sergey Levin, for example, in Google about the arm farm, famous sim-to-real work by OpenAI, very impressive hand manipulation of a hand, and also learning from scratch, which we are pursuing in our team. But all these work have in common that data efficiency is really a key ingredient to make reinforcement learning work in the real world. So the classical reinforcement learning work doesn't care too much about data efficiency. So data comes in, transition comes in, the policy is updated, the new policy is applied to the plant, and the data is basically thrown away. This changed by the introduction of an actual memory that stores all the transitions and reuses those, which make the whole reinforcement learning process much more data efficient. And the FITQ or the neural FITQ algorithms are example of this. And collect and infer is basically a continuation of that work that puts this to the extreme and really asks for reinforcement learning that is most data efficient, as data efficient as it could be. So, and it basically proposes to see reinforcement learning as two distinct but interconnected processes. One is to collect the data with the question, what data collect to make the most learning progress? And the other question is, if we have some data, how can we infer the most knowledge out of it? How can we squeeze everything out of a data source? So basically, this splits this overall agent in two distinct processes. And one of the big advantages now is that we can have clear metrics to optimize each of these two processes separately. For the inference, the question is, given a fixed batch of data, what is the best learning algorithm to get the best policy out of this? And there's already a lot of research going on in this direction. And on the other side, the collection question, which is not so much investigated, but should be much more. Namely, if we have a fixed data budget, what is the right way to collect the data so that an inference algorithm can get the most out of that data? I just want to quickly refer to some research that is already done here. I don't want to go into that table, but the thing here is you have a fixed data set and the different learning algorithms come up with very different qualities of the policies that you see reflected in the very different numbers here. So the inference algorithm that works on the data really matters a lot. And also the same is true for the collection. The question is, what is the right way to collect the data? And here we have a similar experiment. So we have, again, a fixed data budget. The learning algorithm, the inference algorithm is also fixed, but only the collection, the data collection procedure changes. And as you see at the bars over here, the quality of the resulting policy changes dramatically with a difference in the collection policy. So that is recent work of our intern, Will Whitney, but there's also a lot of other work which is referenced in the paper. There's also already an agent architecture that lives to that idea, which is called scheduled auxiliary control. And the idea is basically that you have a lot of skills that are available to the agent, and the scheduler selects what skill to apply next in order to collect the best data for the learning procedure. And again, there's also an inference procedure that tries to get out the best of the data by using relabeling, for example, and other means to squeeze out the best of the data. And the suggestion would be that going forward, we not only think in reinforcement learning for policies, but also think in learning models, learning statistics, learning new reward functions, so everything can be learned out of the data and then used to make the agent even more efficient in the collection process. And this also lives in the spirit a bit like Rich Sutton and colleagues already have proposed 10 years ago with a hard architecture to transform experience into knowledge. So Collected in four. It hopefully inspires novel ways how to optimize, evaluate, and improve these two parts, namely collection and batch reinforcement learning, which has already started but can be improved a lot. And it also gives a blueprint for the design of new future agent that hopefully much more data efficient and then also apply to a lot of even more interesting robotic domains. And there are many further interesting research directions around these topics, hopefully inspired by this framework, and hopefully this framework helps to give a clear direction for future research that you can also find in the paper. Thank you.
Thank you, Martin. Excellent. Okay, good. So we have three positions, and Jans, I'm going to try and see if we can turn things over to you remotely. Is that possible? We're good at there. Okay, can you give him
That's the speaker, Eli
Yes, that's us, yes.
who's going to talk on dual arm adversarial robot learning. The floor is yours.
Okay, perfect. Hello, everyone. I'm very glad to be able to present to you dual arm adversarial robot learning. So when we talk about our robot learning work, we often focus on concepts, algorithms, theories, systems, implementations, and so on and so forth. But what we usually fail to mention are all the human and engineering details or efforts actually that are needed to run such experiments. And for instance, randomizing the state of the environment or objects in the environment. So let's say the robot is trying to learn to perform a peg and hole task. Ideally, you would want the hole to be at random different poses at the beginning of each episode. So how do you do that? A similar but more general concept is the environment reset mechanism. So at the beginning of each trial, you would want to reset the robot and everything related to the task to a certain initial position. And here you might face problems like objects being stuck, like a peg stuck in a hole, or obstacles and similar. Another beast is like the reward computation. So how can you actually obtain the reward? You need access to the states of every object or every entity related to the task. And of course, safety itself is a big problem. So of course, in simulation, this is very simple. So as you can see in the snippet of code on the right, that's all handled. But in reality, that's not the case. So what we ideally would want to have is actually the capability to run long-term experiments and forget about them. But what we usually have is a human in the loop, typically a PhD student hanging around the lab, moving objects around, resetting the environment, pushing the robot, and keeping a hand on the safety button. So can we get rid of, or at least reduce the need of human in the loop during robot learning, specifically for manipulation? And this is what I talk about in this paper. So what if we actually try to replace this human in the loop with another robot, because that solves everything, and try to formulate the whole problem as a joint optimization problem. And of course, I talk about details of maybe how to do that in the paper. But in a nutshell, what we end up having is like two robots, a trainee trying to perform the task by trial and error or anything. And then the trainer robot, which here plays the role of a human. So it resets the environment, whether in a predefined way or a simultaneously learned way. This could also be adversarial. It could also apply adversarial actions during the learning process of the trainee. And this could be based, for instance, on adversarial reinforcement learning from Pinto et al. And many other things to support the whole process. So what do we actually gain out of this? So hopefully that's a step towards more autonomous experiments. For instance, if we revisit the peg and hole example, and now the hole could be assembled to the end effector of the trainer robot. and you could easily reset the environment, randomize the position, all kinds of things. And because you have access to the state or the whereabouts of this object, the hole in that case, or an object if you're doing pick and place, it's easy to design safety mechanisms to collect data for robot supervised learning. So for instance, since you know where the objects are, you could collect data sets of, let's say, images and whereabouts or poses of the object you want to manipulate, and use that to train your perception modules. Based on this knowledge, one could also design heuristic exploration policies to guide the exploration further. And another interesting aspect is, for instance, for human-robot interaction tasks, the trainer robot could simulate a human motion, and that's hard, but let's say it's possible, while the trainee tries to learn the HRI task, the corresponding one. What about challenges? So of course, we're adding another robot, so we're adding to the complexity. That's gonna be a problem by itself, and of course, we have to acknowledge that. We also have the additional cost to have the second robot, maintain it, and run the experiments. And of course, an interesting idea is, why just stop at one robot supporting? So why not more N robots? Of course, with only 2 robots, we might again fall into the same problems. Maybe the object is out of reach of all of both robots, and it's again impossible to reset the environment. So maybe scaling up might be the way. Now, in summary, whether based on the concept I proposed or what the previous speaker, specifically Victoria, proposed, I think we need a feasible real-world alternative to simulation for robot learning. Now, DARL, or the concept I just presented, is just one idea, but what else can you do? So I'm looking forward to discussions about the topic now or in the future. Thank you.
Thank you, Eli. Okay, great. Can we bring everyone up onto the stage for the adversarial part of this talk? No. Let's see. Jens, you're online. Can you hear us?
Yes.
Can we hear you? Okay, good. So I want to open it up for questions, and then we'll leave a little time at the end for the hypothesis about what's the common denominator. But Jens, do you want to go first?
Yes, so we have one online question for Kayleen by Sivan Zhuang. It seems that causal should be dynamic, otherwise a causal graph might be unreasonable in certain situations.
I'm not sure I heard the first part of that, but I caught that the causal model might be unreasonable in certain situations, and I think
should be dynamic. That was the statement.
Yeah, so I think in the example I presented, it was like quite a static situation, and I think that might be, I guess, like the easiest kind of situation to tackle first, and I think that there is some sort of situations where that could be quite useful. But I definitely agree that in order to get this to work more broadly, we would need to somehow incorporate dynamics into the model, and potentially things like factor graphs, I think, could be a useful inspiration for how we might be able to accomplish that, but I think there's a lot of sort of ground that would need to be covered there.
Great, thank you. And question, yes.
Question for Martin. So I like the appeal of this collect and infer framework. It kind of reminds me loosely of like ADMM methods and mini-max optimization that we see in like GAN literature. But simultaneously, there's this kind of alternate perspective to GANs, which is based on just like minimizing F divergences instead of this kind of dual optimization process. So what are your thoughts on like that in the collect and infer framework?
Yeah, I think that is something that we really should tackle in future research. So the current collect and infer is basically just making aware that there are these two optimization processes and that they should be combined. And I think, as you mentioned, there are very different ways how to implement this optimization as a dual optimization or as something being more competitive. But this is really something that is completely open to future research.
Yes, right in the...
Hi, it's Victoria. Will the data that are collected and sent by the robot, the actions and observations, so on, be made public, like as opposed to siloed per user?
Yeah, absolutely. We'll have a shared data set with all of the experiments run by anyone.
Good. Okay, right over here, there's a question. Did you have your hand up over there? You're next. Two.
Hey, Victoria, this is a question for you. So, there's a big aspect to having a robot farm, which is maintenance, and, robots drift at different rates. Do you have any thoughts on how you would do this reliably and evaluate reliably?
Yeah, absolutely. So there's, I guess, a couple parts to that. There's staffing, which might involve things like putting objects back when the robot throws them or something like that, and also more hardware maintenance when motors fail and that kind of thing. For the hardware maintenance, the hope would be that since we have a large collection of robots that are copies of each other, then we could have some deal with the manufacturer where they might provide help with that. For the other part of staffing, yeah, we'll definitely need staff for the center, and that's something we've factored into the plans.
Hey, another question for Victoria. Sorry to throw it all at you at once. I really like the idea for the robotics cloud. I'm wondering how you're feeling about kind of the saturation problem as we kind of go through your timeline. We collect, thousands upon thousands of hours of robot data on these, single robots on these single workspaces. What is your vision for scaling up beyond that, beyond the tasks that you can kind of see on this fixed workspace?
Yeah, absolutely. You're totally right that we will have saturation. So if we have 3 initial benchmark tasks, then I think the goal of any benchmark is you start out with not great performance and then you saturate it and then you move on to harder benchmarks. So we would add new tasks and also new hardware and environments over time. And I think this would be pretty easy to swap out because the capital costs of the robot hardware and sensors and that kind of thing are not actually that large compared to the infrastructure and staffing needs.
This is a question for Kayleen. So one aspect of the human tendency to look for causality is that we also over-find causality and get like pseudoscience and fake placebo effects and things like that. It's kind of out there. But do you think there's some way of, is this inherent? Do we need to do this over causality in order to be intelligent in other ways? Or do you think there's some way of not straying too far in that direction for robots?
Wow, that's a really interesting question. To be honest, I haven't considered it. My guess is that you wouldn't be just using causal modeling to try and plan your actions. And so, maybe if you're selective about the kinds of situations you're applying it in, or, like waiting until you have a certain amount of data where you feel confident about being able to make that causal prediction, you might be able to get around some of those sort of effects that you're talking about. But honestly, I think that's really interesting and I need to think about that more. So thank you for bringing that up.
Great, thank you. And so on that, just following up on that, I mean, something I noticed is that there's a fair amount of commonality between Victoria and Ellie's talks, and the commonality between you, Kayleen, and Martin is sort of that you're coming from very different. You guys are almost at the opposite of each other. I mean, in that Martin is very confident that RL is the answer, and we just need to get more efficient data collection and inference methods. But you're saying actually there's something more that we can't get from RLs. Can you say more about that? I mean, this theory of mind and the interrelationships between people seems very, very subtle. I mean, because if you imagine rather than a soccer ball, it's another person. If you're looking at those two people, you're trying to infer what is their relationship. And you think about that is so subtle, right? Are they friends? Are they enemies? Are they, do they know each other? Are they just two people having an argument and ignoring each other for the moment? There's so much to read into that. And seems like that's going to be very hard from any RL kind of scenario. So what are your thoughts on what, is there something that's missing from RL?
Yeah, so I guess sort of my take on this is that I don't think that there is anything that is impossible to do with RL that is magically made possible by the kinds of models that I was sort of proposing. But I do think that because they sort of allow you to use your knowledge about pairs of objects and sort of compose them using a graph into a new situation, that allows you to deal with edge cases that you haven't seen before. And so I think this is like something that we've seen in autonomous driving, that one of the like main challenges to getting autonomous vehicles to work in the real world is just this process of like trying to deal with as many edge cases as possible to be able to get above like some threshold of acceptable safety. And my sort of what I'm arguing for is that I think that using something like causal modeling could help us deal with a lot of those edge cases with much less data than we would require if we were purely using a deep RL type approach or a model-free RL approach. But I'm not trying to say that like I think we should get rid of RL entirely to replace it with something like causal modeling. I think I'm trying to say that perhaps this is something that is worth looking into as a way to perhaps do like a type of model-based reinforcement learning or something to like use as a safety backup or something like that.
Okay, very diplomatic. All right, Martin, why is everything that Kayleen said total rubbish?
I just wanted to start with saying thank her for making the bridge to reinforcement learning. And I think she's absolutely right. While I believe that finally polynomial that predicts you cannot go there without hurting the human, so this is probably a bad idea, then why should you try to bother to explore dumbly? So you should use, of course, that knowledge. And the second last slide that I proposed actually advocates for being much more general with the knowledge that we generate from the experience. So having models and also inferring knowledge from these models to do better data collection and avoiding obvious mistake. That's definitely something that I would like to integrate in my research if she produces the results.
Okay, very good, very diplomatic too. So, it seems like this is almost another category of these trolley problems. I mean, in some sense, what you pose there is trying to understand, is it safe to go, and understanding this relationship. And as you said, it may be a binary, but it may be many more multifold than that. And I'm just curious if everyone can talk about that aspect of what's not in that data. I mean, it seems that there's so many nuances to all the relationships that can happen. And in some way, the way we learn about relationships is by obviously interacting, but also through reading books and watching movies and everything else, right? We're constantly studying these things. My daughter reads these young adult novels, and that's how she learns about romance and interactions, right? Which are so nuanced and important. Now, here's a question, so that in some sense, you have to feel the emotions in order to be able to process them and sort of infer them. It's kind of an empathy that goes on, would you say? Now, we know that robots so far don't have emotions. Do you think that we need some model of emotional model, some effective model to work in the world? I mean, that's kind of what you're proposing in a very practical way. Is it safe to go forward? Well, I have to understand the emotions between these two people. Martin's handing that off. Okay.
Yeah, that's a really interesting way of putting it. I guess maybe this doesn't fully answer your question, but I think that when we're doing model-free reinforcement learning, that sort of like judgment about what the right thing to do is, like that moral or emotional judgment, is currently being like distilled into the reward function. And that's sort of this kind of black box thing there. I think it's well understood that we're very bad at predicting what kinds of behaviors a particular reward function will actually lead to, especially in more complex settings. And so I guess using more explicit models doesn't free you from that responsibility to try and reason about or like think about the ramifications for what you're optimizing. But maybe it does make it a little more explicit and sort of like get past the stage where we just sort of sweep it under the rug into one reward function.
Great. Okay. Yeah, because I think that the data, right, what the state of the world, when you observe these two people, the same exact state could have so many different interpretations, whether it's safe or not. It depends on history, and it depends on body language, and it depends on just the look in the person's eyes, right? So it's really, there's something very subtle in that example, which I really like. Okay, so we have more questions coming in.
Can I ask a question?
Yes. Victoria, please ask a question of your
I have a question that relates both of these two panelists.
Excellent.
Similar to the one you asked before. So Martine, it sounds like you were saying that causality could be used in the online data collection aspect, using a model for planning or something like that. But it seems like the causality aspect might actually be more useful in the offline RL setting, where the policy might actually be different from what's being used to collect the data. I'm curious what you think about causality in the infer step rather than the collect step?
That's a good question. I think that probably the inference mechanisms purely from data are probably already good enough without having an additional model, because a model would be only one way to kind of accelerate this process. So I'm not sure whether we actually need this in the inference process once we have good enough inference procedures. So I kind of really tend to believe that using models is something that you use while you're acting in the world, but the more you're acting, and it's probably there's an analogy to humans. So if you're doing a new task, then you probably are using a model. How can I reach this object on the table? But once you did this 1,000 times, you stop thinking about this. So this is basically probably also something that Kahneman means with his system 1 and system 2 analogy. So I think, or I have the belief at the moment, that models are mostly useful for the data collection and for the behavior, for doing behaviors. But finally, if you collected enough data, then you should be good enough to go without a model for the inference process. But that's just a belief, and that's can be proven wrong, and can be absolutely right.
I guess just like pushing the analogy to human minds just a little bit further, I guess you could also make the argument that sleep seems to be pretty important, and maybe that is like sort of related to offline learning in some sense.
Ooh, good. Sleep. We haven't had that come up yet. The whole conference, actually, but that's great. So let me ask you a question. So Ellie, you and Victoria seem to agree quite a bit on the need for remote robots that can learn, or basically replacing the graduate student in the loop. What do you disagree with Victoria on?
Tough question. So I wouldn't say I disagree. So I think we're both trying to find feasible ways to make robot learning something feasible again. So what Victoria proposed is like a global, not just a global solution to everyone. So sharing an infrastructure, sharing data, which I think is great. But I guess at some point, although this is great, at some point there might be a limit to related to the question from one of the like previous question. So this might reach maybe at some point a certain limit. We might not be able to integrate more tasks, or we might say at some point, that's it, these are the tasks that our benchmark has. What I was proposing was rather like a local lab-wise solution to or like an alternative to simulation. So I wouldn't say that it's one or the other, rather the two.
Okay, Victoria, you want to rebut that?
Yeah, I think Ellie's right that the setup where you have an adversary could be really interesting. I think it would be harder to do this for benchmarks because every sort of individual experimenter would have different results because it's kind of a more non-stationary task. But yeah, I think I generally agree that autonomous, taking the grad student out of the loop is a good idea. One other difference would be whether we have one robot or two robots. So I think in my system, you would ideally just have one robot that's doing autonomous resets and evaluation and that kind of thing. And so I'd be curious what Ellie thinks about when we need one robot or we need two robots that are in different form factors or something like that.
Mm-hmm. Good. So it's a really nice idea because Ellie's really talking about the robots interacting. You were talking about all these robots in parallel in some ways. So he's trying to bring them together, which is really an interesting idea. Good. So we have time for one more question before we get to our final round. I'm going to give this to our fearless Ed. John's here because he's been working so hard.
Thanks, Ken. So I feel like one of the themes might be, do we focus on changing the hardware setup or do we focus on changing the algorithms that are running on the robots? So I think that Kayleen and Ellie are advocating, well, let's change the hardware. Let's have lots and lots of robots together to collect data, or we have two robots doing dual arm manipulation. And then Kayleen and Martin are advocating, well, let's have better algorithms. How do we actually control those robots? So I'm wondering, what you guys think in terms of which of those is actually more important. So, for example, let's say we just we were to freeze the algorithms and only focus on building better hardware setups such that we could use those algorithms, or we freeze the today's hardware setups and only focus on developing algorithms. And let's say you had 10 years of freezing one and developing the other. Which of those two methods do you think would result in the best policies in the next 10 years or so?
Ooh, good one. Okay, so you got one word answer here. You can either have algorithms or hardware advances in the next 10 years. What do you choose? Victoria?
Algorithms.
Okay. Martin?
Freeze the hardware.
Freeze the hardware.
Yeah,
okay.
Algorithms.
Okay, we are. And Ellie, are you there? What are you voting for?
I agree. Algorithms too, yeah.
Oh, everybody agrees. Okay. Too bad all you hardware makers. So let's see, any hypotheses about, and Jens, please jump in there. I'm happy if you have a question or anything you want to add right now before we wrap up.
We had a couple of questions for actually Victoria online. I'm just going to pick one that I find interesting by Jackie K from DeepMind. Can the robot cloud really be democratized when there are huge corporations with lots of resources contributing to robotics? Can the design of the challenge really be fair for all participants?
Yeah, I think that's a great question. One of the areas I'm pretty excited about is helping out lower resource labs. And so we would consider doing something like providing scholarships or support to maybe people at colleges that wouldn't ordinarily have robotics labs and that kind of thing. I think there's still some interesting interplay between companies that have a lot more resources and this cloud, whether that be if they're sponsoring the cloud, how does that affect their priority with the use of the resources or something like that? So I'm curious to hear if anyone has feedback, we can talk offline about that.
Great, thank you. All right, Jens, anything else from the online world? No, okay. So, all right, but how about we have like 60 seconds left. What do you see as common themes from all four talks? Anybody find anything? It's a challenge. Yes. Okay, good. Cooperative systems. Is that would you say it's fair that that's an element of your work? Kayleen? Yeah? Okay. Ellie? Would you agree that there's an element of cooperation that's in your...
Definitely. Yeah.
Definitely. Well, almost the opposite, right? But yeah, adversarial cooperation, yeah. No, it's true. I mean, that's right. So the interaction, right, between these systems. Excellent. What's your name? Eric. Eric's got the best suggestion so far. Anybody else? Common themes from online. How about, I'll throw one out, which is safety. That seems to have been something everybody talked about to some degree. Is that fair? Is it included? Martin, you had probably a little pinch less of safety, but everybody else talked about safety explicitly, but I thought you said something about safety in there, no?
It's important, of course.
Okay. Okay, with that strong endorsement, I think cooperation is on the lead here for the competition. Any other last-ditch theories that you want to put forward about common denominators here? You have one? Oh, good, okay.
I sort of noticed a theme of, whether we should be focusing on trying to get better, like standardized robot performance in the lab, or whether we should be trying to improve the capabilities of robots on complex real world situations. Mm-hmm. So maybe not like a unifying theme as much as like something that we all addressed, but came to different conclusions about the best way forward, I guess.
Good, excellent. Okay, so the difference between, let's say, very staged environments versus, or common environments, right, versus real world messy environments that are also different. Very good, and that's right. So you and Victoria sort of disagree a little bit in some sense, because you're in favor of the real world. Yeah, the messy real world. All right, excellent. Okay, listen, thank you guys so much for being such good sports, for offering these great suggestions and ideas. Ellie, thank you for your great talk. Jens, thank you as well, and thanks from all of us. Okay, I think we are moving, thank you guys. I think we're moving right into our next session, the oral sessions. And where's our first speaker? Where's our speakers here? Okay. Where's our other speakers? Okay, oh, good. Go. All right. Thank you, everyone. All right. We are now ready to start the next session, which is our oral session of 4 papers. And we will take short questions as the next speaker comes up. Jans is again my co-host. And Jans, I will ask you to step in for the second 2 papers. I'll introduce the first one, which is our own, or my one of the home team for Berkeley who are here. It is Ryan Hawk, who will speak about Thrifty dagger. Ryan?
Can you hear me? Okay, awesome. Good morning, everyone. My name is Ryan, and I'm from UC Berkeley, as Ken said, and I'm excited to share what we've been working on. So when we think about robot learning and the capabilities that we want robots to have, we want them to be able to prepare food for us. We want them to be able to dexterously manipulate objects. We want them to fulfill our orders, maybe drive us from place to place. And we want them to be able to do this all in unstructured environments, to generalize to all kinds of things, right? But where we are today, of course, is that when we deploy them in the real world, they don't always work, right? Might even be safe to say that robot learning doesn't work yet. That's why we still work on it, because we want it to work. We want it to be robust enough for things like industry solutions, where you need to deliver something like 99% reliability, or you can't have a feasible business. So is this something that is in the distant future? Well, not necessarily. There are all these companies today that kind of fix this with a certain solution, and that is to have a human in the loop, right? So if you have a human in the loop, you can catch those edge cases that robots can't handle, and then that hybrid system of human plus robot can actually get can actually get you that 99% reliability. And it might be that only a few robots need help, or maybe only a few robots need help at any given time, then one human can monitor multiple robots at the same time. So, overview of today's talk, I want to give a little bit of background on interactive imitation learning, then go over this algorithm that we're proposing, give a brief overview of our results, and then a look at what's next. So, imitation learning is the idea that a robot should be able to learn from human feedback and examples. And it's one of the dominant paradigms of robot learning today. There's these 4 great CoRL papers you'll hear about at this very conference that either learn a reward function or learn a policy from humans. And it's been able to do a diverse range of complex robotic tasks. In the simplest form, and the most popular form, there's behavior cloning. So here, the human is providing a set of task demonstrations, and these are provided in the form of observations, and there's corresponding action labels. And the robot minimizes some kind of loss function that encourages its actions to be similar to those of the human, just via something like supervised learning. Now, does this work? Not always. If you're paying attention to Byron Boot's tutorial the other day, what you can encounter is something called covariate shift, right? Or distribution shift, where due to compounding error, the robot eventually reaches a state that the human has never seen before, and now it has no idea what to do because it doesn't have any reference behavior to imitate. And what this results in is something called an imitation gap between the performance of the robot policy and the performance of the human policy. And the way to fix this is with, of course, online human feedback. What that means is human labels on the states that the robot actually visited, because this will teach you these little recovery behaviors that will get you back to that region where you actually know what you're doing. And the state-of-the-art algorithm for doing this, as most of us know, is dagger, or dataset aggregation, where the idea is that the human is going to provide an action label for every single state that the robot has visited, and over time, it'll just iteratively do that and close this gap. But dagger imposes a really high burden on the supervisor. You have to label every single state that the robot has visited, which motivates other techniques for doing this. So that's where interactive IL comes in, or interactive imitation learning, which is this new, not new, but recently gaining interest paradigm where the human or the robot cedes control to a human, and the control switches over between the robot and the human. And the nice thing about interactive IL is that it can be used flexibly at training time when the robot's still learning, or it can be used at execution time when the robot and human are working together to improve the reliability of the policy, kind of like those companies are doing. Or you can combine these both, use that data that you got from that human, use it to fine tune the policy, but also care about reliability. And this can be in something like a continual learning framework. So the central question here is, how do we switch control between the supervisor and the human? And the reason this is tricky is because, okay, say you're all the way to one extreme, and the human is just teleoperating the robot all the time. Well, then you have probably great task performance because he's a human expert, but really high burden on the supervisor, right? It's not scalable at all. You have to be controlling the robot at all times and only one robot. On the other end of the spectrum, maybe the robot's in control the entire time. Now there's no burden on the supervisor, that's great, but your performance probably isn't doing so hot because of that imitation gap and other issues. So is there a way that we can balance these competing objectives, right? Good policy performance, but also less burden on the human supervisor. So one approach that people use for doing this is human-gated interactive imitation learning. And the idea is kind of what it sounds like. The human is the one that is deciding, when do I take control? When do I give back control? But in order to do that, you just have to continuously monitor the system, right? You have to, even when you're not in control, you have to see like, okay, this is when I have to step in. So when you scale this up to a large number of robots per human, or maybe a long period of time, now this isn't so feasible after all. So another way to do this is robot-gated interactive IL. That's the counterpart to this, where the system itself is the one that decides when should it ask for help, when should it give back control. Of course, this is trickier because the system isn't an expert human, so it uses all kinds of heuristics like maybe action discrepancy or uncertainty and things like that, and then threshold on these values to determine when should I ask for help. But many prior robot algorithms or robot-gated algorithms fail to strike this balance between supervisor burden and policy performance. They result in a lot of context switching between robot and human control and other kinds of undesirable phenomena. So to this end, we introduce this new algorithm that we call Thrifty dagger, which provides new intervention criteria to hopefully better strike this balance. So let's ask ourselves this question, when should a robot ask for help? So I want you to think about these two quantities. On the x-axis here, we have novelty. And novelty is just, have you seen this data before, right? If you're in a place that you've never seen before, you probably don't know what you're doing, right? That's being off the training distribution. So that's the axis. So then let's talk about risk. So risk isn't a super common term, but in this case, we're saying, what's the probability that you fail the task, right? Then you would say that's risky. If you have a high probability of failing whatever task you're doing, that's risky. So in this case, let's say you're doing an autonomous driving situation, and your risk is crashing the car. Okay. So if you're on a highway on a sunny day, not novel, not risky. You've seen this plenty of times. You know exactly what you're doing. It's all is good. But if you're in a snowy environment, say you don't have a lot of snow in your data, now you don't know what you're doing, right? You probably veer off to the right, maybe you crash into the tree. This is novel and this is risky. Now, our key insight is that a lot of prior work would correlate these two things, and they are highly correlated, but they're not the same thing, right? They're these off-diagonal terms. So there can be states that are novel but not risky, right? Say like a wide open dirt road. Maybe you've never seen it before, but you're not going to crash. Like you can go in any direction here. Or it can be risky but not novel. So maybe you have seen a human demonstrate how to drive a tight cliff, but it's really hard to do that without falling off the cliff, right? You have a very narrow region of allowable motion. So maybe in that case, you would rather cede control to the human than take your chances driving this cliff. So how do we actually do this novelty estimation? So we train an ensemble of deep neural networks, and each of these neural networks is bootstrapped on a subset of the training data. And intuitively, if you have a state that's not very well represented, that is novel, compared to your training data set, these different networks are going to disagree what that correct action should be, more than if each of them has seen something like that before. So we threshold on that variance to kind of give us an estimate of that novelty. And the other component, risk, we propose this novel risk metric, which is a Q function. So assume that our task can be specified by convergence to some goal set, then we can say, estimate the discounted probability of reaching this goal set. And in this case, that would be estimate the discounted probability of succeeding at our task. Then risk would be 1 minus that, or the probability of failing at the task. And in order to approximate Q, we train this sample-based function approximator Q hat by minimizing this mean squared error Bellman loss, which is pretty much the standard objective, but we switch that reward term to 1G of S, where 1 is an indicator for whether or not you're in the goal set. Now, another thing you have to pay attention to is how do you threshold on these novelty and risk values to determine, when do I switch to human control, when do I switch to robot control? A lot of prior work leaves these as parameters to tune, but they can be unintuitive, like what do these numbers mean? And performance can be sensitive to that. And it's almost its own form of supervisor burden. You don't want to run your algorithm multiple times just to figure out, what these parameters should be. So instead, what we do is we let the user provide an alpha, and this alpha is your desired intervention rate, or the ratio of number of interventions to number of robot actions. So say, I know I'm only going to be available 1% of the time. I'll set alpha equals 1%. And then using this, we can use our historical risk or novelty values to kind of take the inverse CDF of that and find the 1 minus alpha quantile, and then set those thresholds accordingly. So putting it all together here, we're going to, if we're in autonomous mode, we're going to switch to supervisor mode if our novelty is sufficiently high or our risk is sufficiently high, using those automatically computed thresholds. And the nice thing about this decomposition is that we only depend on this risk term when the policy or when the state is not novel. Because if it's novel, it would have already switched, which means that it's a familiar state, which in turn means that we can probably trust that Q function that we trained because it's in the familiar region. In the other direction, if you're in supervisor mode, we check if our action discrepancy is sufficiently low, which turns out to be a more tightly correlated with novelty, because when we're in supervisor mode, we do have both robot and human action, and we check that the risk is sufficiently low, right? So now let's move on to some results. So first, we evaluate on this a peg insertion task from a RoboSuite developed by our friends at Stanford and UT Austin, where this ring is initialized in some random pose. You have to grab it, move it over to a target location, and then thread it through this peg at the end. And the reason it's hard is it's very long horizon. This is like 100 or more time steps. So by the time you get to the peg, it's often the case that you're not exactly in the right position, and it becomes this bottleneck to task progress. So what we find is that compared to ablations, compared to baselines, with fewer interventions, Thrifty Dagger can get a higher autonomous success rate, which hints to the fact that, okay, we're better able to balance this task performance objective with this human supervisor burden objective. However, here it does ask for more human actions on average, and this is because of this conservative risk criterion, which kind of doesn't give back control unless it's sure that the robot can complete the task on its own. We also evaluate our algorithms at execution time. So remember here, the goal is to optimize the policy of the hybrid robot plus human, and they're working together to do this task. Again, we see a similar thing where fewer interventions plus higher success rate, and in this case, we're matching the success rate of the Oracle human HG Dagger, where an expert human is constantly monitoring the task and is deciding when to intervene, when to not intervene. And notice that the number of actions is a lot lower now and actually comparable to the baselines because this risk critic is less conservative once the policy is better, right? Now it's not going to fail as much, it's not going to be as worried about you doing the task. We also do some physical experiments. So here is a surgical robot in our lab doing this cable routing task where we're, from images, we are routing this cable in a figure-8 pattern around several of these obstacles. So what happens here? Well, a similar thing happens. So our algorithm is comparable to HG Dagger, which is an oracle in this case, since the human is deciding these intervention points in terms of the success rate. And it's actually, this task is too hard for behavior cloning. It's prone to distribution shift. And we request a comparable amount of interventions and actions to that oracle, despite the robot being the one to request those actions. And again, the number of actions falls significantly at execution time, and here is only a small fraction of the total episode, 1.5 versus 61.3 robot actions. And the last thing I want to talk about is this cool thing that we did, this user study, where here we were interested in the question of, okay, maybe this is a scalable algorithm, how do we apply this to control of a small fleet of robots, where there's one human, multiple robots? So we recruited 10 human subjects, and each controlled a fleet of 3 robots in simulation performing that same peg insertion task from earlier. And we compared these 4 algorithms. 3 of them are robot-gated, 1 of them is human-gated, HG Dagger. In the robot-gated algorithms, what we did was we said, okay, whenever a robot asks for help, you have to help it. And if multiple ask for help, they're going to queue up after each other. But if no robot is asking for help, then what you'll do is make progress on this independent game you're playing, the game you're playing called like memory or concentration, where you have a set of face-down pairs, and every time you turn them around, you can kind of get an idea of what they are, and they only get cleared when you get pairs. So you can imagine if you're switching a lot between these 2 guys, your performance on this memory game is going to suffer. In the human-gated version, we say, okay, forget about the memory game. Your job right now is to control all 3 robots at the same time. You get a little bird's eye view on the left, and just make sure that all these guys can complete them as much as possible. And what we found is that our algorithm requested fewer interventions, fewer human actions, and was able to enable the robots to succeed at the task more often. So the throughput increased, and surprisingly, the human performance also increased. So they were able, the humans were able to find more concentration pairs in that game of memory. So we can see that being able to be judicious about when you request these interventions can give you better performance both with the human task and the robot task. And we gave the survey, and we found that the subjects found that our algorithm was less mentally demanding than something like HG Dagger. You have to keep track of all these things at once, and also less frustrating than something like Safe Dagger, which was just constantly swapping between the task and the robots. So really quickly, some limitations in future work. So we saw that this algorithm can solicit many human actions, especially earlier on in training. So it might be better suited to kinds of tasks where a context switch is way more costly than an individual action. Say if you have to walk across a warehouse to control a robot or something. We also found that earlier states are biased to be riskier or thought of as riskier. That's both because the gradient has a hard time propagating all the way back, and also because intuitively you have a higher chance of failing the task if you're farther away from the goal. So some way of controlling for that bias would be good. And we're also interested in this interactive RL setting where you're not only learning from the human, but you're also learning from your own experience. Okay, that's it. Thank you for listening, and please check out our poster if you're interested.
Okay, great. Thank you, Ryan. And I think we have time for a quick question. Any questions coming up from online, or Eric has one right here? Eric, we can always count on you. Go ahead.
What's the correlation that you see between the positive risk and positive novel?
Oh, whatever, it's fine. Okay. Wait, my mic is back on. Okay. So, yeah. So so often I would say novel states are often risky. Like almost always, like a novel state is going to be risky because you don't know what you're doing. The other case is less frequent. So there's not novel but risky. That is, I would say, less frequent. But it would be interesting to get those exact correlation numbers, as you said. Actually, I should probably run those. Yeah.
Well, it'll depend, obviously, on the task.
Right, exactly.
Yeah. Okay, great. Other questions? If not, we're going to thank you, Ryan, for giving a great talk. We have Antoine Richard. He is going to present, and then Jans will introduce the last two speakers. Go ahead.
Can you hear me? Yeah, okay. Hello, everyone. My name is Antoine Richard, and today I'll be presenting learning behaviors through physics-driven latent imagination. And this work was done in collaboration with Mathieu Gaze from Google Brain, Stéphanie Aravecchia, and Cédric Pradalier from the CNRS. So in this presentation, what we want to do is to deploy reinforcement learning onto robots in the wild. So on the left part of the screen, you can see our robot evolving in its environment. And usually when we want to deploy, reinforcement learning agent on these kind of robots, we have some issues. And the biggest one is, it's taking forever to collect the data. And not only because, we are evolving real time, but because, we need to deploy the robot in the field. We need to prep it to go into the field, and that's taking forever. And then we have other issues like where we need to watch the robot when it's evolving in its field, in its learning, and we need to make sure it's not going to harm the supervisor or it's not going to damage itself. So an obvious solution to that is actually to use simulation. But still, when we use simulation, it is a relatively long process. And then we have another issue, which is how do we transfer from that simulation to the real world? And with boats, for instance, can be troublesome because the dynamics are quite complex. And so something that's even more simpler than a simulation is model-based reinforcement learning. So one way to see model-based reinforcement learning is as a very simple and very efficient simulation. And in our case, and in this presentation, what we'll be doing is we'll be taking Dreamer, a very strong model-based reinforcement learning agent, and we'll be adapting it to better fit the problems that are related to mobile robots. So let's start with a quick overview of how Dreamer works. Then we'll get into the limitations that we encountered using Dreamer and how we solve them. So every time we do model-based reinforcement learning, the first thing we want to do is to learn a model of the environment. And so to do so in Dreamer, what we have is we learn what we call a world model. And so to do so, we need to learn 3 quantities. And the first one is an observation function. So in this case, we have a previous state, a previous action, and an observation, and that's going to give us a new state. We then have a transition function. So in this case, we have a previous state, a previous action, and that gives us a new state. And then we have a reward function. So in this case, we have a state, and we want to know what's our reward. So using all that, we can learn an actor that's going to interact only with that world model. And so to do so, we use that transition function we learned before. We're going to use the reward function that we also learned before, and we'll be learning a new function, which is called the value function. And so using that, we can now train an actor to interact and play with that world model. And then, in turn, we can also run that actor onto the simulation or the real world and use that to collect new data to better model the world. So when we do that, and that's what we've done on our own robot. So we train in simulation, use that world model to learn how to act, and then deploy the robot in 0 shot in the real world. And in fact, it works quite well. So when the dynamics of the robots are not really challenged, we don't have big issues. But as soon as we start to have big variances in the dynamics, then we have problems. So in this case, on the left part of the screen, what you can see is the robot evolving on a frozen lake, and it needs to break the ice. Or on the bottom part of the screen, you can see the robot with a device that's increasing its drag. So in these situations, while the robot is capable of performing its task, the performance is really way off the baseline. And what we were wondering is, okay, how can we change that model-based system to be able to adapt to new dynamics or better frame them? And so right now, the main issue is when we do imagination learning, we learn everything at once. So we learn the dynamics and the environment. And so what we'd like to do is actually be able to have environment and dynamics that are separated and be able to swap them out. So say if we take a car manufacturer is going to have a fleet of different vehicles. And all these vehicles, they are going to share the same environment. And the question we want to answer is, can we build a model that's able to change its dynamic models while preserving its environment and keeping knowledge about all these different types of models? So what we chose to do is to take this standard macro decision process and take the state that we had before and actually cut it into 2 substates. One state would be responsible for the dynamics of the system, and one state would be responsible for the environment. And the way we would transition from one state to another is that we'd have a transition function for the dynamics and a transition function for the environment. And the transition function for the dynamics would be triggered by an action, whereas the transition function for the environment would be triggered by the dynamics itself. So in this case, we have a physical model on one side, and the other side, we have an environment model. And the way we actually give inputs to these models for the physics is that we have a GPS and an IMU, and we fuse all that using an EKF, and that gives us our observation for the physical system. And then for the environment, we use a LiDAR or a projection of a LiDAR, and that gives us the observation input for our system. And so in doing so, basically what we do is we decouple perception from dynamics. And so the way we would perform the rollouts, so the learning in the imagination is the following. So we take our robot states, so that's our physical inputs, and we embed them into a latent dynamic state. We take our perception, we also embed them inside a perception dynamic state. And then taking that dynamic state that we just embedded, we can reconstruct a physical state. Then, using that physical state and the environment state, that gives us a new latent environmental state. And using the previous environment state and the physical state, we can take an action. That action, in turn, we can use to predict the next dynamic state. And then we can iterate. So we have a new dynamic state, we get a new robot state, we take the robot state, fuse it with the environment state, and that gives us the new environment state. Then we take an action, etc., etc. And so we have this huge rollout, and then now we can use it to learn. So we can use it to learn a reward function and a value function. Value function, yes. And the way that we work is, in this case, what we show is for simplicity, we show that we use the robot state to pick an action. But sometimes the robot state would not be enough because it would not contain everything you need. So instead, what you could do is use the dynamic state. So in our paper, we use both. And so we chose to put that to the test, and to do so, we took our boat and we deployed it on a real lake. So on our boat, we have our laser, we have our IMU, our GPS, and we have 2 computers, one for the low-level ROS operation, and Jetson Xavier for the reinforcement learning part. And then on the left, you have the environment. So the environment is our lake, and the goal of the robot was to follow the shores of the lake. And so on this lake, we have 2 interesting points. So the first one is this hairpin turn, and we have then the island, which creates a narrow channel for the robot to navigate to. And that's quite complicated. So in these, what we did is we took our agents, trained them in simulation, and then deployed them in zero shot into the real world. So the upper image is the vanilla agent, and the lower image is our agent. So what we can see on the upper image is with the vanilla dreamer is that what we have is a trajectory that's very windy, so lots of oscillations around, and our agent is much more steady. And the reasons for that, and we'll see that in a bit, is the vanilla dreamer tends to overshoot, so dynamics are not well understood actually, whereas our agent has a better understanding of how the dynamics works. And then if we have a look at the velocities that were reached by the robot, so in this case, the target was 1 meter per second. And what we can see is, well, our robot, our version of the algorithm was better able to maintain the velocity and had a smaller spread. So that's with the zero shot transfer. So the dynamics over both are relatively complex and highly nonlinear. It was very interesting for us to see that we were able to maintain a good level of performance nonetheless. And so that's a zoom on the trajectory, and what we can really see is that our agent is much more steady in comparison to the original dreamer. So going back to the very beginning of the presentation when we said, can we actually swap robots and swap models? So in this case, what we want to do is, well, we have a boat and we also have a rover. And in simulation, we wanted to make sure that we could actually train models. So in this case, we are going to train the boat to navigate along the shores of the lake. And we'll do that in simulation. And what we'll do is we will not train in simulation the rover to do the same thing. So in this case, we replace the water by a solid surface and we put the rover on it and we want it to solve the same task as the boat. And these two systems, they have different action space. So the boat is driven using left-right commands, so a bit like a tank. And the rover would be controlled a bit like your car, where you give a steering velocity and a linear velocity. And so the way that would work out is we have an online learner. So this one is using the simulation, and an offline learner. So the online learner interacts with the simulation plus its world model, whereas the offline learner only interacts with the world model. Then, using the boat, we learn the environment model from scratch. So as the boat learns, we build a good and better environment model. And we use it and we give it to our rover. Then, using what we can learn the dynamics from scratch as we learn the environment, or we could use something that we already know. Say you have a very good dynamic model for a boat where you could plug it in. And same thing with the rover. So in our case, we chose to use an LSTM to model the rover, but you don't have to. You could use a standard physical system for skid steer robots. And then finally, as we learn with the boat, we collect episodes, and that gives us data to bootstrap our imagination from, so our learning mechanism. And we transfer these episodes and we give them to the rover. So that's going to help us use that to better learn. And finally, so we learn the actor online then, on the boat. And on the rover, what we'll do is that we'll interact solely with the world model. And what that gives us as a result is, well, it's not perfect. So on the right, on the left, which one? Right. On the right, you have the offline transfer. On the left, you have the online learning. So we still see that the performances are not quite as good. But what we have is a zero-shot transfer, because we never interacted with the simulation or the real environment, and the robot is able to fulfill its task. So that's a very good baseline that will need way less human supervision to go and deploy in simulation or in the field to refine. Finally, we'll be working towards the limitation of that work right now, is that, well, for now, for this to work, where we need the robots to have the same state space. So they need to share the same physical variables. But for mobile robotics, it's take cars or boats or vacuum cleaner. Usually they share the same state space. And then a huge assumption that we do is that the environment has no impact on the dynamics of the system. And most of the time, it is true. Well, if the car crashes into a wall, clearly that's going to have a big change on the dynamics. But at the same time, you completely failed your task. So one of the main advantage of this work is that so far when we wanted to do, well, domain randomization in model-based reinforcement learning, we could hardly do that because, well, the dynamics were embedded inside the model, Whereas now we can do all that directly inside the imagination. So inside this process that generates billions and billions of trajectories, we can actually directly embed mechanism to make dynamic and very robust actors. Also at the same time, because we have this dynamic that's decoupled, we can work towards physical models that are more transparent. So we don't need to rely on neural networks to learn the dynamics. We can use classical physical system. And finally, because we have exposed more variables within the imagination, then now we can learn to make systems that are more flexible. So we could learn behaviors that are flexible and we could tweak the reward function on the fly directly within the imagination. So what that gives us is a very powerful tool to manipulate everything that's happening in the imagination, just like we could inside a regular simulator. Thank you for listening, and I'll take questions.
Excellent. Very great talk. Okay, so a question from the floor, or we'll go over to Jans for one from online.
Don't have any yet.
Okay, from the floor.
Hi. So you mentioned a lot of results about zero-shot transfer. I'm just wondering if you have any results, or perhaps even an intuition on how this kind of method would work if you did have like a few demonstrations or some data from the real world. I think this is maybe related to some of the limitations you mentioned.
Yeah, so right now our main issue is collecting this data. I think we need about 5 or 6 hours of real world data, and our batteries only last 30 minutes. So, and takes 4 hours just to put the boat in the lake. So I think it will work quite well, in particular because we can learn a better dynamic system. So right now, what's really the bottleneck is not that much the environmental model. It's really how do we model the dynamics. And if we had a better dynamic model, I don't see why we wouldn't be able to learn better. And one of the main discrepancies we see when we have these, so the difference between the performance we transferred is really down to the dynamics between the rover and the boat are completely different. The boat tends to drift a lot. So we have a lot of drifting when we take curves, whereas the rover is ground and static. So when we start to bootstrap the imagination, we have these, a lot of dynamics that don't exist for the rover, and we try to learn an actor for that. And that's, I think in our case, what we should have done is having longer horizon of imagination and discard the beginning of the imagination. But yeah, to answer your question, I believe that if we had real-world data, we would improve the performance because that would be direct domain adaptation within model-based reinforcement learning.
Antoine, did I hear you just say you would discard some data?
Yes. I mean,
okay, I don't know if you may have to leave the stage now. No. Okay, very bold, provocative statement, and thank you for the talk. One last question from me is I love this idea of modularizing these components, and I'm curious about automating, let's say, the choice of model as you go. For example, as you said, you have analytic models versus learned models, et cetera. So is there a method, or have you thought about the idea that you could start comparing these automatically and switching and tuning them, the choices between them? Because that seems a very interesting opportunity.
Well, for now, no. We are really trying to, I mean, we're still playing with it, trying to figure out where exactly we want to go. But yeah, it's interesting to actually let the network say, what do I want to split? Yeah. But we would need, I think Jeff Clune gave a very good example of why that would be important. Yeah. Like trying to let the simulation make weird things and see how, well, our agent could adapt to the weird things and choose which model are actually should be contained in some bits.
Yeah. Lots of interesting future work there. Excellent. Okay, thank you so much, Antoine. Excellent talk. Okay, Jans is online. I think he's going to introduce our next speaker. Our last two speakers are from Stanford.
Yes, the first of the two is Woodrow Wang, and he is going to tell us more about influencing towards stable multi-agent interactions.
Cool. Hey everyone, my name is Woody Wang, and I'm excited to talk today on our work on influencing towards stable multi-agent interactions. to help tackle some of the difficulties of learning in non-stationary multi-agent environments. So coordination is often critical to succeeding in multi-agent environments. For example, in this household, there are 2 robots, a blue and a red one, that have been given the task of cleaning the entire house and the front yard after a long night out at a dinner party. So the 2 robots can take on many different strategies when deciding how to optimally clean this house. So let's say that we are the blue robot, and we need to decide which trash bag to pick up next. So when deciding which trash bag to pick up, we really have to decide based on what we think the red robot will do, as we don't want to have to clean up the same trash bag as the red robot is to avoid being inefficient. So partners with changing strategies make learning in multi-agent environments really difficult. So without knowing what the red robot will clean, the blue robot may accidentally interfere with the red robot and pick up the same trash bag. This leads to a coordination failure since each robot's redundantly picking up the same trash. So the key problem here is that non-stationarity in the other agent's strategy makes learning really difficult. Without knowing what the other agent might do, it's difficult for the ego agent, the blue agent, to behave optimally. So prior works in opponent modeling suggest both reactive and proactive approaches to dealing with non-stationarity in these multi-agent environments. A reactive algorithm for the ego agent could be one that tries to forget past experiences, or maybe just retrain on more recent data, or even predict the opponent's strategy with some learned model of the opponent's behavior. So in terms of the robot cleaning example, a reactive algorithm for the blue agent might greedily move towards the nearest trash bag, or as the red robot moves towards one trash bag, the blue robot could predict where the red robot's going and move towards the other trash bag. However, predicting the opponent's strategy can be done in a proactive way as well. A proactive approach might try to learn a dynamics model of the opponent's strategy, or even use this dynamics model to influence the opponent towards some desirable strategy. And in this way, the robot is learning how to proactively influence the opponent's behavior rather than just react to the opponent's behavior. And in terms of the robot cleaning example, now the blue robot might proactively predict that the red robot's going to move towards the bottom trash bag, and then know to move towards the top trash bag. So in principle, it'd be great if the blue robot could always precisely predict exactly where the red robot's going, but this isn't always possible, especially when there's many, many trash bags. So, but if the blue robot could stabilize the red robot's strategy, then this could make learning a best response much easier. So in the context of cleaning the house, the blue robot could wait for the red robot to go outside, and then this might seem a bit silly, but the blue robot can then go, close, lock this door, and then which will stabilize the opponent's strategy to only clean the trash on the outside in the front yard. This effectively will partition the cleaning regions into 2, so making each robot's role in cleaning the house much more clear. And this simplifies the entire learning process and will help them clean all the trash. So our key insight here is that stabilizing the other agent's strategy in a multi-agent environment can reduce non-stationarity and facilitate learning a best response to the other agent. So for our problem statement, we consider 2-player multi-agent settings where there is an ego agent that we have control over and another agent that we don't have any control over, don't have direct control over. And as a specific example to introduce this problem, let's take a look at this circle environment where the ego agent is the blue circle, and the other agent chooses a goal location between any of these 3 gray goals. And the other agent's hidden strategy, shown in red, is this choice of goal, denoted by Z, and the ego agent doesn't observe the opponent's hidden strategy. The ego agent's task is to try to get as close as possible to the opponent's chosen goal. So we consider the setting where the ego agent's, where the opponent's goal location transitions based on the ego agent's trajectory. So in the circle environment, if the ego agent ends its interaction inside of the circle, the opponent will move its goal location clockwise. Otherwise, if the ego agent ends its trajectory outside the circle, then the opponent's goal location will stay stationary. And since the opponent's goal location is unobserved, stabilizing to one unobserved opponent goal will make it much more easy for the ego agent to learn how to navigate to that unknown goal. So with this problem statement, our method seeks to stabilize the opponent's strategy to help learn in a multi-agent environment. So as a definition, we define 2 opponent strategies as pairwise epsilon stable if the distance between those 2 strategies is less than epsilon. So if we go back to our circle environment, we can now look at what stabilizing the opponent's strategy would look like here. So if the blue agent ends its interaction inside the circle, then the opponent will move clockwise, and the latent strategy would be some distance away. And we want to minimize this distance between consecutive interactions in order to stabilize our opponent's strategy. So stabilizing behavior here would be for the ego agent to continually end its interaction outside of the circle so that the opponent's goal location will stay stationary. So we can now present our method, stable influencing of latent intent, or SILI, which is composed of two main components. And the first is a representation learning component, and the second is stable influencing via reinforcement learning. So I'll first describe the representation learning component on the left, which is how we learn a model of the opponent's latent strategies. So we can approximate the latent strategy dynamics by learning an encoder which maps the previous trajectory to the predicted next latent strategy. And in terms of the circle environment, the ego agent's trajectory is fed as input, and the output of the encoder is the next predicted latent strategy. And since we don't observe these latent strategies directly, we can't learn these in a supervised manner, but we can learn them in a sort of unsupervised way, since we know these latent strategies should be predictive of the task rewards and the transitions, which we do observe. So we can train this decoder that predicts the task rewards and transitions from the encoded latent strategy embeddings. And again, in terms of the circle environment, the ego agent's last predicted latent strategy, as well as state and action, is fed as input. And the output of the decoder is the predicted task reward and the predicted next state. So with these learned latent strategies and the dynamics model, we can now stably influence with reinforcement learning on the right-hand side of the diagram. So with these learned encoders, we can define a stability reward using the distance between consecutive opponent strategies. Then we can define a new reward, our total, as a linear combination between the task reward and the stability reward, parameterized by a stability weight of beta. And with beta equals 1, the SILI's entire objective is to stabilize. And with beta equals 0, the ego agent will just greedily maximize the task reward. And we can now train our policy using our total. And since our stability objective is to keep the opponent's consecutive strategies stable, it's important to condition our ego agent's policy on the last two predicted latent strategies. So in the circle environment, SILI can optimize for our stable to always learn to end the interaction outside of the circle to keep the red goal stationary. And once the opponent strategy is stable, the ego agent can begin to creep towards the true goal that's being kept stable, which is why we optimize for our total. And finally, we train our encoder and policy simultaneously. So as the encoder's representation for the opponent's strategy improves, the ego agent's policy can adjust in the loop as well. So we examined 3 methods for modeling and measuring distances between latent strategies. The first is continuous latent variables. The second is discrete latent variables. And the third is where we have partial observations of the changing strategies. So in the most general case with continuous latent variables, we allow the latent variable space to be unconstrained and use the Euclidean norm for the stability reward. And these continuous latent variables would make sense to use, for example, in the circle environment when the goals can lie anywhere on the continuous spectrum along the circumference of the circle. In the discrete latent variable setting, we use the Gumbel softmax distribution to constrain the latent variables to be categorical variables. And with the categorical latent variables, we use the discrete distance metric for the stability reward. So intuitively, it's easier to identify whether or not 2 strategies are similar enough to be clustered together than it is to identify the exact distance in this latent space between the predicted latent strategies. And finally, we have, so when we have prior knowledge that there might be a discrete number of opponent strategies, it might make sense to use discrete latent variables. And then finally, we have this setting where we have partial observations of the changing strategy, where we assume the ego agent can observe if the opponent strategy changes between time steps. So no representations learning is required in this setting to stabilize. And this corresponds to a setting where, again, it might be easy to identify whether or not opponent strategy might change between time steps, but really difficult to estimate exactly what their strategy is. So for experiments, we run experiments in a variety of simulated environments, including multiple variants of this circle environment, a driving environment, an assistive robot reaching environment, and an emergent communication environment. And for the sake of time in this talk, I'll present results in the circle point mass environment, specifically the variant with 3 goals. but we have much more results on our website and in our paper. So, right, so as a reminder, in this environment, the ego agent is in blue, and the opponent chooses a goal location in red. And the ego agent must try to get as close as possible to the opponent's chosen goal location in red. And for the strategy dynamics, if the ego agent ends its interaction inside of the circle, again, the opponent will move clockwise. Otherwise, the opponent will stay stationary. So for quantitative results, we compare our approach with multiple baselines, which I'll now introduce. So we show the task reward on the left and the stability reward on the right. So our first baseline is soft actor critic, which is the baseline reinforcement learning algorithm of our method. We use vanilla soft actor critic as a comparison for an algorithm that doesn't have any explicit opponent modeling. Stable is a variant of silly with the beta set to be 1. So stable is only optimizing for stability of the opponent goal, as can be seen by the really low task reward, but the very high stability reward here. Surprise minimizing RL, or SMRL, optimizes for a different notion of stability, where the surprise reward is proportional to the likelihood of the state given the history of the previous states. So, but notice here that SMRL doesn't optimize well for our stability objective. Lily, learning and influencing with latent intent, combines soft actor critic with representation learning to model the opponent's strategy dynamics as well. But unlike our work, Lily doesn't optimize for stabilizing the opponent's strategy at all, as can be seen by the low stability reward here. In our method, stable influencing of latent intent, or silly, achieves the highest reward here by learning to first stabilize the opponent's strategy and then maximizes the task reward with respect to that fixed strategy. And finally, we have an oracle as a baseline, which is given the true opponent strategy as an observation. So notice here that silly and oracle achieve similarly high rewards, but that the oracle doesn't need to stabilize the opponent strategy at all in order to maximize the task reward. So for some qualitative results here, the first we have here is soft actor critic. And so recall that soft actor critic does not model the opponent strategy at all. And so the local optimum is to move towards the centroid of the 3 goals when the true goal is unknown. Lily does learn a latent representation of the opponent strategy, but doesn't optimize for stabilizing. So as Lily greedily optimizes for the task reward, Lily will creep towards the boundary of the circle and could encounter an unexpected transition of the opponent strategy. Stable is that variant of silly that purely optimizes for stabilizing. And notice here that stable does learn to end every interaction outside of the circle, which stabilizes the opponent goal, but stable has no incentive to move towards the opponent's true goal. And finally, silly, our method, learns to stabilize the opponent's strategy by safely ending each interaction outside of the circle. And by doing so, silly can more easily optimize for the task reward by going near the red target. And to summarize our key contributions and takeaways, so we propose learning an unsupervised stability reward to influence other agents towards stable strategies. And we show that silly improves our robot's ability to coordinate and maximize the task reward. So thanks for listening. And here's a QR code that links to our project's website. I'm happy to take any questions now.
Questions from the audience? So one, I'll ask quickly, Woody, great talk. What about, have you thought about how robust it will be to noise? Have you done experiments injecting noise into these environments?
So let's see, with respect to noise. So I guess one of the things we're really interested in is looking at, I guess, more complex environments with more opponent strategies, and specifically, I guess, the noise of the real world too. Like a lot of the COVID restrictions. I've been in Texas this whole time while working with Dorsa from Stanford, and so I unfortunately haven't been able to do some real robot experiments yet. But we've been really interested in thinking about, for example, this steak cutting example, where if we have like a bimanual robot that's trying to cut a steak, so if we think of the 2 arms as each agent, then I guess if our objective is to cut the steak, you could imagine stabilizing could be like one of the arms could perform stabilizing behavior by holding a fork and like stabbing the steak and holding it still. And then the knife So that's essentially is going to stabilize the opponent's strategy if you think of the opponent as the stakes dynamics of moving. And then the knife can more easily cut through the stake. And so I guess with regards to noise, we'd be really interested in looking, yeah, I guess testing this in the real world.
Okay, good. Yeah, other questions? Here's one from the back.
What are the dynamics like for having two stabilizing agents in an environment?
So if you have two agents trying to stabilize each other's strategies?
Yeah.
So this is, I guess this is leading to a really good point of like, when is it possible to stabilize an opponent's strategy? Or and so I guess the way we've thought of this problem is that it's kind of like so Lily tries to influence the opponent's strategy in the sense that just to maximize the task reward. But we were really interested in looking at like how can we like explicitly influence? And so we can think of stability as just an inductive bias of saying like when our opponent's strategy might be changing a lot, if we can keep it fixed, then we can at least learn a best response to that fixed strategy. So if two agents are trying to stabilize each other, I guess it can be, I guess it depends on the environment on whether that's actually possible. But so one thing we've also looked at is making sure that this method doesn't hurt in environments where it's not possible to stabilize. So we do provide experiments on annealing the stability weight. So where you might want to start out trying to stabilize your opponent, and if it's kind of not possible, then you asymptotically will then just optimize for your task reward as you would have done so initially.
Thanks.
Great, thank you, Woody. Okay, so I don't know, Jans, if there's anyone online with a question. Otherwise, you'll introduce the last speaker of the session.
No, we didn't get any online questions. So if there's still any questions, you can also ask them during the poster session. And the last presentation for the session is SXRL, Cross-embodiment Inverse Reinforcement Learning, presented by Kevin Saka.
Everyone, I'm Kevin, and today I'll be presenting XIRL, Cross-embodiment Inverse RL. This is joint work with wonderful collaborators, Andy, Pete, Jonathan, Jeanette, and Debbie. So the goal of this work really is we want our robots to watch us humans perform tasks and then learn how to do them. But before I talk about that, I want to talk about like why have robots watch humans, and what is this cross-embodiment problem that I mentioned in the title? And the reason we want to have robots watch humans is that in typical imitation learning scenarios, you usually need to have experts teleoperate the robot to collect data. And this can be quite time-consuming and unscalable. And if you have such a setup that requires specialized hardware to do, then you typically have, your progress on the project will kind of look like this, where the amount of robot learning is kind of throttled by the grad student, and the availability of the hardware. So for example, you could forget to log the data, or you delete the data because you change your end effector. And so this isn't really scalable. What we really want is to have a curve that looks like this. And we believe the way to do this is to have robots that learn by watching. And if we can unlock this capability, then anyone can show demonstrations to the robot, and we don't need specialized hardware when we do the demo collection. And eventually, what we really want is robots that can learn by watching YouTube videos, for example. Unfortunately, the main limitation of third-person visual imitation is this issue of the correspondence problem. And if you think about this dog trying to imitate the human at opening the door, you could try to manually hand-define correspondences between the dog and the human. But you'll quickly find that trying to hand-define these correspondences can be sometimes impossible to define. So think about how you would try to define these correspondences for an octopus trying to open a peanut butter jar if you have a human demonstration doing it. And sometimes, even if there is a clear-cut correspondence between the two embodiments, there might be physical constraints between the learner and the demonstrator, which make it futile to define. There have been previous works that tackle this cross-embodiment problem, either by doing explicit domain adaptation, but that introduces visual artifacts. And Other previous works do indeed use manually defined correspondences, but as we just mentioned, this can be limiting and sometimes impossible to do. So to reiterate, in a typical imitation learning pipeline, both the learning and the demonstrating happen on the same hardware. So you have a clear-cut mapping between state action tuples from one domain to the other. But really, real intelligence can imitate with different strategies despite different embodiments. And especially in the case of robots imitating humans, because the end effector is morphologically different than the human hand, you're going to run into this problem where the robot just can't do the task the way the human does it. And so if we think about this door opening task for a minute, we can realize that it doesn't really matter how the door is open. What really matters is that it is open. And so the question we ask in this work is whether we can learn a notion of task progress that is invariant to the embodiment performing the task. So we do this in 3 steps. The first thing we do is that we self-supervise a reward function. And the way we do that is we learn an encoder using expert demonstrations of different embodiments performing a task. We learn this encoder with a temporal cycle consistency objective, which learns the task progress and encodes it in the embedding, and I'll talk a bit about that later. Once we learn this encoder, we can use it to define a reward function. And the way we do that is that we take the embedding of the current observation and we measure its distance in the embedding space to the mean goal embedding. And then once we have this learn reward function, we can plug it into a reinforcement learning algorithm like SAC and learn the behavior on the learning agent. So the way we encode this task progress in the feature embedding is we turn to this a recently introduced self-supervised pre-training method called temporal cycle consistency, or TCC for short. And what TCC does is it learns to align videos of different agents performing a task to temporally align them. And it does this by maximizing mutual soft nearest neighbors in the embedding space. And the authors showed that when you perform this unsupervised video alignment pre-training objective, you learn a very nice structured embedding space where the trajectories overlap in this embedding space. And our intuition is that it should be possible to encode task progress in this embedding space. And in fact, we did take this data set that I'll talk a bit in a minute. We took this data set of different agents performing a manipulation task, and we look at the embedding space, and we also look at the reward function. And we can see that the reward correlates nicely with task progress as the agent is performing the task. So to examine this cross-embodiment imitation setting, we introduced this kind of like MNIST for cross-embodiment imitation, which we call X-Magical. So X-Magical is a simulated benchmark. It's based on a 2D physics engine, so it makes it very fast. You have very high FPS, so quick iteration. It's easily extendable. You can add new embodiments or new tasks, and it has a gym-like API. So I encourage you to check it out. But we focused on this sweep to top task in the environment. And here we have 4 different embodiments, 3 stick agents and 1 gripper agent. The stick agents have 2 degrees of freedom, and the gripper agent has 3 degrees of freedom. And here the goal is to sweep these debris to the top of the arena here in the pink zone. And what you see is that by changing the shape of the agents, you kind of change the strategy and the way they perform the task. So if we look at demonstration data that we collected and we plot the state distribution that the agents visit in these expert demonstrations, you'll see that for an embodiment like the long stick, it's just a very simple linear trajectory to complete the task. Whereas for more complicated agents like the short stick and the gripper, they have a much wider coverage of the state, and you can look at the trajectories on the right here, randomly sampled trajectories, and see how different they are than for the long stick agent. And so the first question we wanted to ask was whether reinforcement learning could work with our learned reward. And so the setup here is that we train our reward on demonstrations of 1 agent, and we perform reinforcement learning on that same agent. And here what we want to see is that the challenge here is that our encoder should generalize to states that were unseen in the pre-training demonstrations. And what we see is that across the board on all 4 agents, our method results in more sample efficient policies. So note that all these curves here use the same RL algorithm. It's just the reward that changes. And so our policies, especially on the harder agents like the short stick and the gripper agent, perform significantly better than baseline alternatives. In a setting we care more about, which is take this reward and generalize to unseen embodiments. So what we do is we pre-train the representation on 3 embodiments, and then we perform RL on an unseen held out embodiment. And we do this for all 4 different combinations of this. And again, we have the same storyline here where across the board, we perform better than baselines. Our policies are more sample efficient and perform significantly better on the harder agents here at the bottom. On a real world challenging setup as well, where we pre-train the reward on human demonstrations and then transfer to a simulated robot for a puck pushing task. Same storyline as well. Our policies here in red perform much better than baseline alternatives and using the sparse environment reward. For some qualitative results, so the first thing I wanted to look at was what do our learned rewards look like? And so here I'm specifically teleoperating the agents and plotting the learned reward. So as you can see on the left here for the X magical benchmark, comparing the positive demonstration to a negative one, you can see that we assign much higher reward for the positive demonstration than for the negative one, and it correlates nicely with the task progress. And specifically here on the right with the Sawyer arm, you can see that for this negative demonstration where the agent arm overshoots, the reward starts to decrease as well, which is great. We also collected a data set we call XReal. We have 9 different embodiments. Some of them are shoppable on Amazon. And we perform this pens in cup and mug task, where you first have to pick up the pens, place them in the mug, and then take them out of the mug and place them in the cup. And what we see is for pathological demonstrations, like here on the right, where the global movement is the same as what you would do for a positive demonstration, but you don't grab the pens, you fake it. It assigns much lower reward than for the positive demonstration. In this case, the difference between the top row and the second row is that at the end, I'm sloppy with placing the pens in the cup and some of them fall out. You can see that the reward dips as well. So the reward is able to capture these fine-grained details. For this task here, the difference between the positive and negative demonstration is that the negative only does half the task. So we only place the pens in the first cup. So you see the reward in orange here increases, but then plateaus, whereas for the positive demonstration, it increases. And so the main takeaways here, I introduced the cross-embodiment imitation problem, and I showed that especially for robots imitating humans, you're gonna face this cross-embodiment problem. And rather than trying to define correspondences from one domain to the other, what we do is we learn a reward function that is embodiment invariant, and that encodes task progress. We showed how we can self-supervise this reward using a temporal cycle consistency objective, and that a simple reward formulation that doesn't use any time indexing or test time alignment can result in very sample-efficient policies that beat baseline alternatives. Thank you.
Thank you, Kevin.
We have an online question from Steven Chuang. What if the expert embodiment differs drastically from the test agent? Any experiments? So to put differently, how much can you actually push the difference in embodiment?
Yes, that's a great question. So the assumption we make in our work is that across different embodiments, there's going to be states that are intrinsic to the task that most embodiments are going to visit. And so in the case where you have something completely different that doesn't do anything remotely close to what you see in the expert demonstrations, I don't think that our method would give any reward signal in that sense. So yeah, the assumption is that most embodiments, they're going to be different, but there are some states that they visit that are similar, and that's what TCC is exploiting and aligning.
Yes, question over here.
Hi. Yeah, I was just curious how, if you have compared with Gale, the generative adversarial imitation learning when using only states.
We don't compare to Gale. Most of our most of our baselines are things that use reward learning methods. There's TCN, time contrastive networks. We have a goal classifier, which learns to classify whether an image is the goal state or not. But yeah, no explicit.
Do you have an intuition?
I think it would do well, but especially on tasks where, for example, when you try to transfer from stick agents to gripper agents, I think that's where our method would shine and provide, like the dense signal you're getting from the XIRL reward would perform better.
Hey, very cool project. So I'm wondering, how did you get the extra behavior for that sweeping task with all the different embodiments? It seems pretty non-trivial. Is it like a human that's kind of doing it or something else?
You could do that with a scripted oracle, but the way we do it is, define the mean average reward. So like hand define a reward function, train an SAC policy, and generate the expert demonstrations.
Okay, makes sense.
Okay. Oh, one last question. Good.
Sure. Kevin, I was wondering, you showed in the humans demonstration videos that the human was pushing the puck at a very gradual pace and making sure not to like occlude the puck and everything. So some of these things might be obvious, but could you explain to us what would be hard about imitating a video where the human just did like a natural motion without worrying about occlusion and everything, and why it would be hard?
So you're asking what would happen if you do an unnatural movement?
Rather, you do a more natural movement, like you just kind of push the puck like you normally would, like you weren't doing this for an experiment, for a robot demonstration.
So I don't know if this answers your question directly, but when we do the pre-training, we do like really aggressive data augmentation. And one data augmentation we do is cutout, where you like randomly black out a square in the scene. So effectively, we did that for the puck pushing task, and you randomly, like there's parts of the scene, the end effector, that completely disappear. And that helps the reward learn to focus on things that matter for the task, not the overall hand movement, but more, is the puck inside the goal zone or not? So I think that, there might be instances in your demonstration where you have something unnatural or you have partial observability, but I think that's good. And these are things that you can, that can help you learn a better reward function.
Great. Okay. Thank you, Kevin. Great talk.
Thank you.
Let's thank all of our speakers from this session. Thank you, guys. Very good. So we now have a short break, half an hour, and then we go into posters. Thank you, everyone.
Something about it still feels strange. Like looking in a mirror, trying to steady yourself and say to somebody else. And everything is not the same now. It feels like our lives have changed. Maybe when I'm all the way, but I'll come down, but it's killing me now. What if you had it all, but nobody to call? Maybe then you know me. 'Cause I've had everything, but no one's listening, and that's just fucking lonely. I'm so lonely. Lonely. I'm so lonely. Lonely. Everybody knows my price now. Now my heart was always made of ice. And maybe that's a price you pay for the money and fame at an early age. And everybody saw me sick. And feel like no one gave a shit. The crazy say the things I did as an idiot kid. What if you had it all, but nobody to call? Maybe then you know me. 'Cause I've had everything, but no one's listening, and that's just fucking lonely. 5 in the morning, I'm all out of breath. Don't make me forget it. Don't make me forget all the reasons I gave. Stuck in your bed, high as the ceiling. Love how you taste. Yeah, it's easy, yeah, to walk out the door and never look back. There's no reason now to keep screwing over the feelings we have, yeah. So I keep coming over, breathing your cigarette smoke. Keep coming over. You make me feel something real. Make me feel lucky. I keep on falling the further I get. Don't be mistaken, there's still some parts that just don't make sense. Stuck in my head, I keep on thinking, why won't we stay? ATC, yeah, to work out a door and having there's no reason not to keep screwing over the feelings we have. So I keep coming over, breathing your cigarette smoke, keep coming over. You make me feel something real. Make me feel lucky.
Tell me, Haley, hey, what you do when you're gone? You drive me crazy. Hey, I'm walking around in my room. You want me daily? Hey, until we're through, until you're gone. Oh my baby, hey, you drive me crazy. Ooh, what you do to me? I can barely sleep. Ooh, but if I probably dream of you. Ooh, what you do, I am going mad cause of you, what you do. It's all cool, I'm just gonna work it out. Ooh, what you do, I am going mad cause of you, what you do. It's all cool, I'm just gonna work it out. I'll be alone for a couple of days until you say that she'll come back home. It's okay, it's so fucking okay, cause I hate being on my own. You're amazingly bad for me. I don't get your strategy. You're cute, then you're mad at me. Like what? Ooh, what you do, I am going mad cause of you, what you do. It's all cool, I'm just gonna work it out. Ooh, what you do, I am going mad cause of you, what you do. It's all cool, I'm just gonna work it out. What you do. It's all cool, what you do. I'm just gonna work it out.
Behind your shadow, while you tried to take the sun down, hearts don't ever change to gold. Out there thinking that you're in the world alone. No one ever told you that you'll have to fight for something, or you'll never learn to balance. It's too cold, standing in the middle of the downpour, looking in the mirror cause it's only you that you have to lose. Headed backward on a one-way, trying to stop from running but you can't wait. Bury all the evidence you'll only learn when you crash and burn. When you crash and when you crash living in a crazy world, following the path that always twists and turns. Gave up on your sanity to hide behind the devil, cause you think you'll live forever. Say you're never getting old, out there thinking that you're in the world alone. No one ever told you
1, 2.
feeling. Staring at the pictures on the walls. Every time I see you with some other guy, I say I don't mind. But every time you start to walk away, emotions, all the color starts to fade. And every piece I need to feel complete. I miss the way you used to touch my skin. You're irreplaceable. And can't you see the pressure I've been under? Can't you see that I've been moving towards you? I am so miserable, I am so vulnerable now. She can't break bones into a million pieces, digging my grave wherever she pleases. She got me on my knees, she got me begging please. But every time you start to walk away, emotions, all the color starts to fade. And every piece I need to feel complete. I miss the way you used to touch my skin. You're irreplaceable.
she's a girl who never found the words to tell you what's been going on. And right behind the lies, those memories start to blind, so she never asked the sky for God. Or maybe she's not right, she's trapped inside a mind where everybody's always wrong. But you think when she breathes and she's more perfect than Eden, more perfect than Eden. You would say there ain't nothing that she wouldn't do. So you just hold it till it's over. Need the way she needs you. Maybe she's a girl who never found the words to tell you what's been going on. And right behind those eyes, those memories start to blind, so she never asked the sky for God. And maybe she's not right, she's trapped inside a mind where everything is always wrong. But you think when she breathes that she's more perfect than Eden, more perfect than Eden. my bed from the start, knowing I did my part to keep this thing sailing along and on and on. Tell me you don't feel the same. Show me who's to take the blame. 'Cause I see the beast we became on our own time, yeah. Look at how we stand still. Not ill, but we're not going well. We're too scared to ask why. Look at how we turn down. Step back at how we miss the ground. We're too scared to ask why. Look at how we turn down. Step back at how we miss the ground. Too scared to ask why. I took a trip to the west, thinking I'd do my best to feel like I did at the start. But all I know is maybe you don't feel the same. Maybe I should take the blame. 'Cause I see the beast we became on our own time, yeah. Look at how we stand still. Not ill, but we're not going well. We're too scared to ask why. touch the blood you own. We were a pair. I saw you there. Too much to bear. You were my life, but life is far away from fair. Was I stupid to love you? Was I reckless to help? Was it obvious to everybody else that I fallen for a lie? You were never on my side. Fool me once, fool me twice. Are you there for paradise? Now you'll never see me cry. There's just no time to die. I let it burn. You're no longer my concern. Faces from my past return. Another lesson yet to learn that I've fallen for a lie. You were never on my side. Fool me once, fool me twice. Are you there for paradise? Now you'll never see me cry. There's just no time to die. No time to die. No time to die. Fool me once, fool me twice. Are you there to paradise? Now you'll never see.
Woke up with your hand in mine, in my bedroom once again. You said it was just one more night, then it's over, it's the end. Trained ourselves to sleep, hoping it might bring some sense. Feels like we're still on the fence. Thought that we were over after everything we said. We keep coming back for more. Why are you still here when we said goodbye? Why are you still here when I turned off the lights? Your bags are packed, but you just can't leave. Do you think we're meant to be? Are we meant to be? Are we meant to be? We're meant to be. Sick of staring at our photographs, 'cause they remind me of what we were. But I can't seem to shake the feeling that we're growing when it hurts. Trained ourselves to sleep, hoping it might bring some sense. Feels like we're still on the fence. Thought that we were over after everything we said. We keep coming back for more. Why are you still here when we said goodbye? Why are you still here when I turned off the lights? Your bags are packed, but you just can't leave. Do you think we're meant to be? Are we meant to be?
We should go our separate ways, but now you're back, begging for a place to stay. Oh, it's not right. I wanna kiss you when we fight, kiss you when we fight, kiss you when we fight. So hit the road, baby. I don't wanna see the mess you made. I don't wanna hear about your mistakes. I just wanna live my life without you. You told me that we should go our separate ways, but now you're back, begging for a place to stay. Oh, it's not right. I wanna kiss you when we fight, kiss you when we fight, kiss you when we fight. So hit the road, baby. I don't wanna see the mess you made. I don't wanna hear about your mistakes. I just wanna live my life without you.
Oh, baby, shake your body. Ooh, let's go all day, all night. Ooh, if you wanna. Oh, baby, shake your body. Ooh, let's go all day, all night. Ooh, if you wanna. Come a little closer to me. Give me some of where we used to be. Come a little closer. We can do it over. Time to see you again, come back to that season. I'm looking forward to see you again, come back to that season. You're in the night with the moonlight, I like it. Which is always in the store, I like it. See it with you in the sunlight, I like it. You're always in the night with the moonlight, I like it. Which is always in the store, I like it. See it with you in the sunlight, I like it. We were young and free. 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 Time to see you again, come back to that season. I'm looking forward to see you again, come back to that season. You're in the night with the moonlight, I like it. Which is always in the store, I like it. See it with you in the sunlight, I like it. You're always in the night with the moonlight, I like it. Which is always in the store, I like it. See it with you in the sunlight, I like it. We were young and free. 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 We were young and free.
No, you'll never believe it. You can fight it all you want, you just have to receive it. And I promised I wouldn't. Yeah, I swore that I'd never tell. Nothing wrong with a little lie. We're just breathing and killing time. Got no reason to change our mind. Nothing wrong with a little lie. No one knows how we're doing, say we're feeling fine. No one knows all the corners and the back of your mind. No one knows how to love anymore, and I'm sure no one knows all the answers. No one knows how to love anymore, and I'm sure no one knows all the answers. Can I tell you a story? Can you keep it to yourself? Let me tell you a story. All the real happy endings, they don't live in fairy tales. It's the light in the morning. And I promised I wouldn't. Said I'd never ever tell. Nothing wrong with a little lie. We're just breathing and killing time. Reason to change your mind. Nothing wrong with a little lie. No one knows how we're doing, say we're feeling fine. No one knows all the corners and the back of your mind. No one knows how to love anymore, seem to know what you need. Doesn't matter who you are, don't give in, we've come too far. It's always been right here. Carve your name into the stars. You don't need to hide away, don't hide away. Show you what you need. Let's just leave the world behind.
breaks my heart, 'cause all I want is just to stay. Calling out to you in the night, knowing that it still means nothing. Will we be okay? Our worlds away. I know that it's almost over, and everyone is waiting at the edge for me. So tell me why I feel no closer than before, with no clue what was yet to be. Calling out to you in the night, knowing that it still means nothing. Will we be okay? Our worlds away.
I've been going off for broke for my friends to like me, oh, but I know they see right through me, 'cause they listen to my songs, yeah. But I don't care, no baby, I don't care. People always tell me take a breath, hey, hey, hey. I've been looking for something that haunts me all night. I've been staying up hours until the sunrise. Just so casual, always living the same life. I don't really mind, but I just need to take some time to get away. Is there something I could take for this pain to go away? 'Cause I've tried 100 methods and they always seem to fail. Am I crazy? Don't tell me I'm crazy. I just need to find another way. Hey, hey, hey. I've been looking for something that haunts me all night. I've been staying up hours until the sunrise. Just so casual, always living the same life. I don't really mind, but I just need to take some time to get away. For me, myself and I, 'cause I'm so bloody tired, yeah. But I'm alright, trust me baby, I'm alright. I'll just sit back and enjoy the ride. I've been looking for something that haunts me all night. I've been staying up hours until the sunrise. It's so casual, always living the same life. I don't really mind, but I just need to take some time to get away.
Hello. Hello,
Hi.
Vijay. Hi. Hi, nice to meet you. I'm Wei.
Wei.
Okay. Hi, nice to meet you. I think the logistics gonna be like follows. So Ashley and
Hello,
I
Wei,
gonna
and
have.
hello, Vijay. This is Mario. I am technical support. We'll be pushing you onto the screen. So I have the schedule here. We're going to have an introduction for Rhea. Then we're going to go into Dyson video and then Sony video. Can I ask who of you is our chair? Oh, it's
I'm
Wei.
the chair.
Yeah.
Yeah. So
sorry.
Mario, Ashley gonna give introduction for Vijay. Then I gonna just post the questions from the audience. So official chair is physically in London.
Yes. So I have yeah, that was the other one that I was talking about. It's
yes,
a pre-recorded
yes,
videos from Sony and Dyson. Do you want to introduce those?
No,
You're on the next session.
I'm not sure. Yes.
With just give me, this is really small.
With Pierre-Yves? Wait.
But it's good to meet you.
Me too. Very nice to meet you. Yes. Yeah, I'm actually in Delft right now, and I think actually. Then good luck.
All right, hello everybody.
A quick note before we start the next session. Just wanted to tell people that if you're looking for an outlet, then there is power in the 2 rooms that we have upstairs here. So if you go up the stairs and follow the signs to either Hilda Clark or Sarah Fell, then those 2 rooms are for your use, for taking a break. Nice quiet work rooms with lots of power. All right, and so with that, let me start the next session. We're going to have a quick 10-minute sponsor session where we're going to hear from Sony and then from Dyson. So first from Sony, pre-recorded video, please.
Hey everyone, I'm Sean, and in this video, I'll be going over Sony's company introduction. Masaru Ibuka, one of the founders of Sony, set up the company with a clear purpose: to establish an ideal factory that stresses a spirit of freedom and open-mindedness that will, through technology, contribute to Japanese culture. From these origins, Sony has continued to build upon its founding ideas through expansion and globalization, ultimately striving to bring ambitious ideas to the table, to do what has never been done before, and to continue leading in the introduction of groundbreaking technologies around Japan and the world. Sony has been able to grow a diverse business portfolio over the years, leading in a variety of industries, including game and network services, music, movies, electronic products and solutions, imaging and sensing solutions, and finance. Our global research and development centers, located across 8 countries around the world, serve as the backbone of innovation that allows Sony to continually produce novel technologies and state-of-the-art consumer electronics within these industries. Sony's people philosophy is broken down into 2 components: Special You, Diverse Sony. When we say Special You, the focus is on your individuality, as we are interested in helping you develop your career path in the field of technology. We support those with passion and those who dream, so we want our opportunities to be the basis upon which you can expand your experiences and build the practical skill sets necessary to make tangible progress toward your goals. When we say Diverse Sony, we are referring to our company culture rooted in principles of inclusion and acceptance of all people. We strongly believe that diversification across our entire company allows us to constantly adapt amid an ever-changing global society. Furthermore, we believe that diversity of thought and experience among members of our research and development teams elevates the quality of the ideas and solutions those teams propose. Therefore, to better optimize productivity, cooperation, and morale as we expand our most creative and inventive spaces, we believe that Special You and Diverse Sony must exist together in harmony. And so, we are eager to listen to your unique perspectives and to learn from your international experiences as soon as you join us. And we look forward to working with you soon.
Hi, I'm Charles Collis from Dyson. I'm head of our robotics research team. Ra suggested I said a few words. I haven't prepared much. It's mostly going to be a film from James Dyson. But yeah, just to say, we're working on some kind of advanced domestic robotics program. We're based at an old air base at Hallavington near Chippenham, which is about 5 miles from our Malmesbury headquarters. We've got teams in perception, physical interaction, control, HRI, robot learning, of course, and mechatronics. So we're a very applied group. We're building machines, integrating them, optimizing them, and aiming towards producing products that work in the real world, are very functional. yeah, so we're looking for people to come and help us who are very motivated to help bring robots into the real world, into everyday life. We also have a decent-sized internship program as well. So PhDs very welcome to come and join us for a few months during or perhaps at the end of their PhD if they're not quite sure what to do next. It'd be great to come and join us for a bit and see if that's something you might want to do. Yeah. So we're going to have a few words from James Dyson. He's our biggest supporter in the company in terms of pushing forwards advanced robotics. So very, very ambitious guy, and we're very grateful that he allows us to do the things we do, trying to push forwards and find new avenues for products in the future. It's pretty exciting. But I'll hand over to James.
In a way, problem solving is a disease. You want to do it, and although each one's a headache, it's there to be solved. It's a steeple to climb. It's a mountain to climb. Mountaineers have that problem, that disease, and that we have that. We were a group of engineers starting to want to make a different type of product with better technology, and we've carried on like that. I have 35 years' experience of making things, and it's taught me a lot. It's no good just being a designer. You've got to make a product that works better. Things are too heavy, things are too polluting, things use too much energy, things don't perform as well as they should, things don't last as long as they should. There are just hundreds of problems in every product. What we're trying to do every day is make products work better. And if we develop breakthrough technology like high-speed electric motors, for me that's a huge success.
Because this enables so many products to perform so well.
If you always do what you know is going to work, then okay, you'll have less failure. But you'll never make a substantive change or a breakthrough. What we're doing is trying to do something different and better, trying to advance technology, trying to advance what a product can do. So we're risk-taking all the time. We're stepping off into the unknown, sort of brand word, but we're pioneering. And I think we've gathered around us a group of people who want to do that. It's not a question of coming in to make money. We're coming in to make the business grow. We come in to make better technology and design and develop better performing products.
All right. Hi, everyone. My name is Ashley Edwards, and I'll be co-chairing the next session along with Dr. Wei Pan, who will be chairing the session virtually. So I'm excited to introduce our next keynote speaker, Dr. Vijay Janappa Reddy. Dr. Janappa Reddy is an associate professor at Harvard University and VP and founding member of ML Commons, a nonprofit organization aiming to accelerate machine learning innovation for everyone. He has done a lot of really great things for the community and is passionate about widening access to applied machine learning for STEM, diversity, and using AI for social good. He designed the Tiny ML series on edX, an online course that sits at the intersection of embedded systems and ML that thousands of global learners can access and audit free of cost. He is also responsible for the Austin Hands-on Computer Science program deployed in the Austin Independent School District for K-12 CS education. Before joining Harvard, Dr. Janappa Reddy was an associate professor at the University of Texas at Austin in the Electrical and Computer Engineering Department. His research sits at the intersection of machine learning, computer architecture, and runtime software. He specializes in building computer systems for tiny IoT devices, as well as mobile and edge computing. He is a recipient of multiple awards and honors, including the National Academy of Engineering Gilbert Lecturer Honor, Intel Early Career Award, and several Google Faculty Research Awards, to name a few. And he has also received Best Paper Awards at several conferences. So Dr. Janappa Reddy received a PhD in computer science from Harvard University, an MS from the University of Colorado at Boulder, and a BS from Santa Clara University. So it is an honor to have you here. And yeah, everyone please join me in welcoming Dr. Janappa Reddy to the virtual stage. Are you good? We can see your slides now and everything.
Should we get started? Sorry.
Oh yeah, we can hear you now. You can get started. Can you hear me? Thumbs up, maybe? Yeah, I don't know.
Right. Hi, folks. My name is Vijay. I'm a faculty member at Harvard, and I'm excited today to be talking to you about tiny machine learning, which is an emerging field within machine learning, and I'm going to define what it is pretty soon. But the biggest thing that I want to talk about is really about tiny machine learning and its potential applications in the context of robotics, because I feel like it's about to unlock a whole new area within robotics. And so today what I'm going to talk about is get you to understand what TinyML is, what the possibilities are, and how it applies to robotics, and then touch upon what are some potential research challenges and opportunities in order to be able to unlock the space. Now, let me start off by defining what I mean by TinyML. TinyML is, I would arguably say that it's one of the fastest growing fields within machine learning. Now, it's specifically interesting because it's about bringing around machine learning algorithms and embedded hardware and embedded software. Now, this confluence of these three usually disparate areas is what is going to give life to a whole new set of use cases. Specifically, it's about doing machine learning right where the sensors are and processing all that data right at the endpoint. Now, this is really interesting because if you can do this with ultra low power consumption, then you can enable always on machine learning, right? Effectively, as many sensors you might have around any kind of physical robot, you have the possibility of continuously mining all of that raw data and extracting interesting signals out of it. Now, the ideal goal of tiny machine learning is to operate on battery powered devices. Now, what I'm going to do is try and tie these things up in the context of robotics as we go through the talk. Now, one of the common applications of TinyML is probably something you and I take for granted. Typically, it's like when you say, hey, Google, or like, hey, Siri, and so forth. The keyword Siri or okay, Google, and so forth are the keywords that wake up the machine. Of course, all my machines end up waking up right now. Now, that said, there are many other kinds of applications that are on the horizon. Now, a lot of TinyML is really about deploying machine learning at the endpoint, right? So what I mean by endpoint is like things like Google Assistants or the smart devices that you and I have on a daily basis that we typically take for granted. It might be a smart toothbrush, smart watch, whatever it is. They've got a lot of sensors in there. Now, one of the key things we might be wondering is like, why am I talking about all these consumer devices when we're really at a robot learning conference? Well, that's the interesting point, is like when I'm talking about these consumer devices, that's really where TinyML has typically existed. But what we're seeing is increasingly a transition in terms of its applicability to a wide range of application areas. And specifically in the context of robotics, I think it's going to unlock the field quite a bit. Why? Now, if you just take an autonomous car, for instance, right? This thing is loaded with sensors. There is so much sensor information coming through across many different mediums or sensor types that trying to process all that information and trying to extract insights is fundamentally a computational bottleneck. So the key question becomes, instead of looking at all of that raw data that's coming through and housing it in the context of big GPUs, for instance, that actually consume a lot of power, which in fact consume so much power that it actually reduces the overall lifespan of the car in the sense that it consumes a lot of fuel. So the amount of distance that the vehicle can actually autonomously go is actually reduced quite a bit. So the key thing is about like, how can we actually process this sensor data that's at the tip of all these different sensors these many different vehicles have, and try and make sense of that very efficiently. Now, there are lots and lots of different kinds of sensors, right? The motion sensors, acoustic sensors, environmental sensors. This is just a sampling I'm providing. But you can imagine, depending on the kind of application you are touching, it's going to have some modality of sensing, period. Robotics in my head is all about sensing in some capacity and making sense of the environment or making sense of the information that you're getting through. And processing all of that is extremely challenging. Now, it's extremely challenging, not just in terms of like putting the sensors, in fact, just kind of putting the sensors on in itself is a problem. But what makes it really challenging is the fact that you have to process all of that information, which means that there's an additional compute burden that's put on. And today I'm going to talk a lot about this intersection between compute and this machine learning and how it applies in the context of robotics as we kind of go further. Now, one specific example, if I just take, right, would be like how sensor information is being used. We're in a robot learning in a conference. And so obviously, you know, we're very familiar with the idea of taking inputs and then, for instance, going from pixel to control, right? We have many different application use cases. For instance, the learning hand-eye coordination is a classic example where we built these robots where we're actually trying to look at pixel information that's coming through and learning how to grasp better. That's just one example. Now, over time, what we're seeing is that there are other kinds of applications that are coming about. So for instance, in this particular case,
there's a dangerous gas leak in a building. Wouldn't it be great if we could send in robots to find the gas leak quickly and without endangering human lives? We have developed the first autonomous swarm of tiny drones that is able to find gas leaks in unknown, cluttered environments. Their small size not only allows them to fly in narrow spaces, but also makes them very safe. Usually, it is very challenging to get such tiny drones to fly autonomously.
The key reason that they're actually challenging is what? Because they're swap constrained, right? There's size, the physical form factor, there's weight, because as you add the weight, then you're going to need the extra thrust. And then, of course, you've got limited flight capability because your battery is really small. This crazy fly, for instance, typically hovers for only about 5 to 7 minutes. And any little bit of additional compute that you put on board actually reduces the amount of capability that it has in terms of performing missions autonomously. Now, this is some collaborative work. Just want to give a shout out for the Mab Lab that at TU Delft with Guido. We've done some interesting work in terms of enabling compute on these small little devices. Now, there's also really interesting work that I think Scaramuza is going to talk about tomorrow in terms of agile drone racing capabilities using these small devices, which needs a lot of high performance compute. You can actually push these kinds of devices. The sensing modalities actually become really, really interesting as you go from big scale robotics, like the arms that I showed you, down to like these small little crazy flies, and you can even push them even further. So this is an example from Rob Wood's group at Harvard, which is an extremely small robot.
Harvard's ambulatory micro robot. Hammer is inspired by one of nature's most accomplished animals, the cockroach. Cockroaches are fast, nimble, and nearly impossible to kill. This centimeter-sized robot packs a lot of that same functionality in its small body. Each leg is equipped with 2 actuators, mimicking the joints of real insects. These actuators give Hammer a lot of maneuverability. Hammer is designed to run, trot, bound, and jump, and can run about 10.5 body lengths per second. This tiny bot can carry payloads 2 times its own body weight, which could be useful one day for carrying sensors and other equipment in the field. Like real cockroaches, Hammer can also climb steep inclines and fall from great heights without being injured. This versatile bot could one day perform a range of applications, from crawling through rubble on search and rescue missions to surveying dangerous environments unreachable to humans. So if you see this little guy scurrying down the halls of Harvard, try not to squish it.
So this is very exciting, right? So what we've talked about in this particular robot that is extremely small, right, is really about the physical actuation capabilities using PopMem's kind of manufacturing capabilities. But one of the really interesting things is how can we embed intelligence on these small devices, which I think is sort of the next frontier. Now, if you want to enable intelligence on these small little devices, then you really got to think about what is the sensor feed that's coming in? What kind of sensory input do I get? And how do I make sense of actually processing that information? As you can imagine, there is absolutely no way you can actually take any of the data that's physically getting gathered and offload it to a smartphone or a cloud or anything like that, right? You can't put a big fat GPU to run a big model down here. So the key question becomes, how can I use tiny machine learning in order to enable intelligence on board some of these emerging application areas? The key thing that I want to get you to kind of remember is, like, when you talk about sensing modalities, having different kinds of sensors, what's really interesting is the fact that we don't harness a lot of the data. We obviously are wickedly crazy about machine learning methods across the space, across the whole ecosystem in the application domain, right? And that's because we have a lot of data that we're making sense of it. But now once you start talking about sensors specifically, endpoint data, right, where we have all these sensors that are producing insane amount of data, you will realize that less than 1% of that data that we're actually already have today is being used in order to kind of make sense of it. So the point I'm saying is that as we go forward, and as sensors become an integral part of all these autonomous machines that we're starting to build, be it like a big autonomous car or a small little, ambulatory robot, the potential is going to be boundless. Now, I often go around saying that, hey, what's exciting about this space is that the future of machine learning is tiny and bright. Now, the two key words in here, the first part is the tiny element, and the second part is the bright. So the rest of the talk, I'm actually going to talk about what does it mean when you actually have tiny machine learning capabilities. I want to talk about the mechanics so that you can kind of think about the potential applications that will come out because of the mechanics that we are starting to solve. Now, in this particular space, I want to kind of put it in the context of what we're talking about when we say tiny. So this is a golf ball, and the little dips you're seeing are effectively the dimples on the golf ball. And I'm talking about these systems being extremely small and extremely light. Now, this specifically fits with the context of swap constrained systems because you want them to be lightweight, you want them to be able to perform intelligent compute on board. Or if I kind of put this back in the context of the hammer robot, that little chip you're looking at, right, is effectively, you can look at this in the context of the dime, it's got to be something that's lightweight. You can obviously think about the fact that the battery is going to be extremely constrained in order to do any of the processing that you need. But that form factor being so small opens up, real new challenges. I want to help you understand that in order to process the data, what sort of compute capability you typically have in the context of tiny amounts. I'm talking about the mechanics here, right? So this is the bit craze. This is one of those small little crazy fly drone boards. Now, if you look at this particular SoC, as we call it, the system on chip, what you will see is that this particular processor's capability is only about 168 megahertz, right? And the amount of RAM that you have, where you actually do your memory effectively, right, is 196 kilobytes. And the storage, like physically, if you think of it as a hard disk, that's only about 1 megabyte. Why am I talking about these numbers? These numbers are extremely important in order to understand the constraints of the system. Now, if you want to perform machine learning on these kinds of things, you've really fundamentally got to understand the nature and characteristics of these small little tiny systems. If you understand those constraints, then it kind of bootstraps the ecosystem in terms of thinking about what kind of models do I want to build, what kind of applications can I enable. These values are so small, right? If you look at a typical CPU that's running any kind of machine learning model, or you look at a GPU that's running any kind of machine learning model, that's typically in the order of like gigahertz, right? And if you look at the amount of memory that the models take, I mean, we're pretty bad just, as a community, just generally kind of thinking about the kind of models that we tend to build. We are often building models that are getting really, really big. So this is almost like going in the opposite direction of what the rest of the ecosystem is going. And I would argue that this is the kind of compute that is actually very, very pervasive. In fact, if you look at these small little systems that I'm talking about, I'm not talking about what's about to come out in the next couple of years and so forth. This is already all around us. Like virtually across all of the devices that you and I take for granted, there are about 250 billion of these microcontrollers today on this planet, right? And about 30 million or so are about to ship every single year, right? So it's an insane amount of volume in terms of these small little microcontrollers. So the ecosystem already effectively exists. That's a really exciting thing. And the other thing is that it's not only about just having commodity hardware where you don't have custom solutions and so forth, it's commodity hardware. And the price of these components has been dropping remarkably. They're only about 50 cents a pop, which is incredible, right? What this is getting to is that we have the potential to enable like really low cost, right, or low power, cheap commodity hardware, right? We have this. And Tiny Amount is all about taking machine learning and trying to enable it on this sort of, commodity hardware. And if we can do this, then it's wickedly awesome, because then we would be able to harness a lot of the rich sensory input that we're often dealing with in the context of robotics. We'll be able to we'll be able to perform always on machine learning right at the sensor tips that where we're actually collecting a lot of information, rather than trying to pull all that information up into a sort of a central computing system, which is actually very power hungry. It is not low power. It is not cheap, right? So it effectively goes against the grain in terms of embedding intelligence on device for robot applications. Now, I'm going to walk through this sort of a diagram for the rest of the talk, because I've talked a little bit about the machine learning space. Obviously, this is a community that knows a lot about robot learning methods, so I'm not going to waste my time on that, right? And then, but what I'm going to try and do is really try and talk about the interesting intersections that are happening here with machine learning, the robot applications that we have, and the embedded systems, right? So I'm going to just refer to these little dinky little computing systems as embedded systems. Specifically, I'm going to avoid talking about the intersection between machine learning and robot applications, because that is why we are here, and this community knows about this space much more than I do. My background, in fact, is really at the intersection of machine learning systems and embedded systems and like sort of interesting emerging application areas. The application is just an application for me. It's like I really build the, and building the systems, I'm often trying to unlock new application areas for other communities. And so part of the goal down here is for me to be able to kind of communicate where the TinyML ecosystem is, so that you can potentially connect the dots in terms of enabling those applications that I'm kind of hinting towards earlier. And so TinyML for robotics really sits at this intersection where we want to enable on-device intelligence for extremely small and agile kind of robots. I'm really hoping that tomorrow Scaramuza is actually going to go and talk about some of the really interesting applications that they have been pushing in the context of agile drone racing and so forth, which are highly computationally demanding. So I would encourage you to kind of keep my talk in mind and then think about what's coming down the pipe tomorrow when he talks about stuff, because you will start to be able to make connections. So because I'm about to kind of, I've introduced this whole notion of TinyML, and then I've talked about its potential applications in the context of robotics. What I want to do next is to try to do a little bit of mind share, or like a little bit of a shift in terms of kind of putting these little puzzle pieces together so that you can actually understand what are some challenges, what can I do today, and what will I need to do in the future in order to unlock some of these interesting applications. Let me start off by just kind of talking about the machine learning pipeline that we typically look at, right? The machine learning pipeline typically goes from all the way from data collection to actually deployment, right? Now, arguably, I feel that a lot of the community often is very focused in just unlocking the first piece of the pie. What do I mean by this? We often build data sets, we often build benchmarks as data sets, and then we go ahead and try and train models and get them to conversions and try and understand what policy actually works well, what kind of learning algorithms we got to put in place, and so forth. And that's kind of what we do. And that is an extremely important part. Right? And I think this community does a wonderful job of that. However, there is a second part to the whole aspect of pushing the whole robotic application areas that we come up with into a production sort of a scenario or a use case scenario, right? And this is really where my job usually kind of kicks in, because part of my job is kind of figuring out like, hey, you folks are coming up with these really interesting applications. How do I actually enable some sort of interesting deployments down here onto a physical device, right? Now, there are a whole load of challenges that you start running into when you actually take big models and you try and squeeze them down on small systems. I'm going to give you one cherry-picked example, and we can talk about more later. Let's say, for instance, I train a neural network, and I've done all my magic, and I end up with a neural network that's I'm going to give it a name called policy 3. It's got some number of parameters, and there is a base model is FP32, or just a default model that you get out of a trained system, right? And it's got some sort of success rate. This actually specifically comes from being able to do autonomous navigation on a UAV system. It's got a rough success rate of 86%. And if you look at the latency of the system, it's 208 milliseconds. That means from the time you actually put the model on the device and you actually push go for every single, let's say, perception frame that's coming in, right, to the point that you actually try and get the result of that, what the data was that coming out of the endpoint of the network, it's about 208 milliseconds. Now I'll get to the rest of these columns later. Right? So now if I take this little system and I deploy this on this physical device, let's say, for example, I deploy this on this Raspberry device, right, which is a small embedded device, then what you're going to see is that the time here is remarkably actually very inefficient. It actually does not work if you try and put it into a real-time loop. It actually falls apart real fast. You have this model actually works well, period. We can say that, right? If it works well, then does it actually work efficiently on device? That's the second question, right? Now, what I'm showing you here is that one of the reasons that it actually takes longer to run this is because even though it fits on the device, it doesn't fit on the device efficiently. In other words, you can see here that the memory consumption when I'm running this particular model, right? This is sort of around 900 megabytes or so. It's starting to use what we call, once you kick the model in, it's starting to use what we call a swap memory. In any computing system, you're going to have the typical memory, which is really fast and efficient. And then there's an entire backspace that actually supports the whole virtual memory architecture that traditional systems have, where there'll be a little bit of swap space, and the swap space is really slow and inefficient, but effectively gives you an extra virtual memory space, right? And what we're seeing is that this model happens to be so big that it actually is falling into the swap space. Once you go into the swap space, your performance basically collapses dramatically, right? And so that's what we're seeing here. The reason this 208 milliseconds actually takes place is because we're using swap space. Now, in contrast, being a systems engineer guy, if I go into the second phase of actually doing the deployment, right, what am I going to do? I'm actually going to take the trained model that you might have, and then I'm going to try and do quantization. I'll pull a whole bunch of tricks around trying to shrink the model, be it pruning, quantization or quantization of way of training, and try and get the model down into an int8 version. The int8 version, simply put, is going to be 4 times faster, 4 times smaller, and therefore it's actually going to fit very efficiently inside the memory system. And you can see, as a result of that int8 model, right, the performance is actually much, much faster. It's 11 milliseconds as opposed to 208 milliseconds. It's roughly about close to a 20x sort of a difference, right, in terms of performance capability. Now, this is key. This is key because if you want to be able to actually physically deploy something onto the robot, the real-time feedback loop actually becomes quite integral. So the point I'm trying to make here is that in general, when we're talking about deploying any sort of tiny machine learning, we're going to have to be extremely conscious not only about just getting models to actually work well and converge, but we're also going to have to close the full loop, which is thinking about, hey, if I've trained these models, how well do these models actually run on the deployment device? And if you don't close that full loop, then you often get into situations where you practically can't deploy things on the device. And this I see all the time. It can be some of the best people in the community working on this, but typically these two communities have been largely split. And increasingly, one of the points that I'm trying to make is that we need to look at the end-to-end ML workflow, going from actually training to full-on deployment, because that actually opens up an interesting new set of problems, some of which I will actually show. Now, before I go any further, first and foremost, I want to convince you that yes, you can actually start doing these kinds of things today, right? This is not pie in the sky kind of thing, the small little compute engines that I'm showing you, you can actually physically embed them right in next to sensors. The technology exists today. This is about one of the fastest growing fields right now within the systems community. And that's why I want to talk about it, because there are really interesting challenges you have to appreciate in order to know what you can and what you cannot do. So there are lots of these small little embedded systems all over the place. If you look at the ecosystem of embedded systems, these devices, for instance, I'll hold one up in my hand, literally physically, right? This is the small little device, and you can see it literally fits in my finger. And this is a development platform. A development platform is usually not the smallest little thing you can build. It's got a bunch of prototyping systems around it. But the key message is they're really small systems, relatively speaking. This is by no means compared to an NVIDIA V100 GPU. These systems are extremely small. And they're small, which means they're also tuned that way because you want them to consume very little power. What that means is that their clock performance, the performance abilities that they have in terms of just raw horsepower is going to be very, very small. These are, as you can see here, these are in the order of a few megahertz. Now, often when you're trying to do sensor processing, in some cases where you're trying to use it for filtering data and so forth, this sort of compute performance is usually okay. Now, you also got to keep in mind that the amount of memory that these systems have is also very, very small. As I mentioned earlier, we're talking about a few kilobytes of main memory. And if you consider it, quote unquote, your hard disk, right? The flash, as we call it, there's only about 1 megabyte, 2 megabytes. So they're very, very small systems. And they often are loaded with a rich number of sensors that you can actually harness. Now, one of the things that happens when you have these kinds of systems is it leads into some sort of deployment challenges. How can I deploy machine learning models onto small little devices like that? Well, broadly, these challenges can be put into hardware and software. On the hardware side, for instance, you have heterogeneity problems. What I mean by that is each one of these little devices that I might go in the market and kind of take off the shelf, you'll find well, I might have a CPU, I might have a DSP, I might have an NPU. They're all highly specialized engines for various tasks. Then you get into the issue that, as I showed you, they have very little memory. They have power limitations, so you can't actually run complex things on them. So you kind of have to appreciate the fact that there's a lot of limitations around this space, because often there are a few people that I know who kind of are working at this intersection of TinyML and robotics. And they often actually get stuck around this challenge of like, hey, like, I've got the system, but when I take the code from this system to that system, it just doesn't work. Yes, that's because you got to appreciate the fact that because these systems have to be efficient, you kind of shave off anything that is excess and any sort of excess. So there's no notion of general purposeness, really kind of breaks down. When you talk about software, right, how do you program these systems? Well, think about the last time, for instance, you might have thought about like doing memory allocation, like when you're allocating a tensor, right? You have, I got a bunch of tensors. Do you ever think about like the fact that, how much memory are you allocating for your tensors? I bet you probably never thought about it. And that's great. That's the way the world is supposed to be. But often when we're talking about these small little embedded systems, some of the challenges are like even simple things that we take for granted, like allocating memory to a malloc simply doesn't exist, right? These features don't exist. These libraries are missing. Sometimes the libraries are available on certain devices and sometimes they're not. So this leads to a lot of fragmentation in the software ecosystem. And of course, they don't even have operating systems. And when we're programming on systems, typically we're talking about Windows, Linux, or something like that. But these embedded systems sometimes don't even have that bare metal kind of capability. Now that makes it all look like, all of this looks really, really bad. But I still want to tell you that we have worked on sort of solving this. In fact, you've been probably training models using TensorFlow. And if you've been training models using TensorFlow, I got good news for you. Well, TensorFlow Lite Micro, which is one of the hottest things that has actually come out recently, actually allows you to run machine learning models on these small little devices that I'm talking about, despite the fact that there are all these challenges. Now, what's really interesting is that the code that you would write for one particular embedded device might then actually be portable and run across multiple devices. Now, we've actually used this in the context of robot applications. For example, we worked on a paper where we built an autonomous drone where the goal was to kind of do source seeking while avoiding obstacles, right? So you've got multiple different sensors because you're trying to seek a source. At the same time, you're trying to avoid obstacles. So you're trying to quote unquote do perception. And you're trying to do all of this while you're maintaining the feedback loop of just kind of maintaining a control loop to make sure that the drone doesn't fall off. And you can do these kinds of things, and you can use TensorFlow Lite Micro to actually deploy an end-to-end model onto this device, which is what we had done, for instance. But you get into some really interesting things that you got to keep in mind, which is like, if you look at the amount of memory that is here, the amount of free memory that is available is really, really small. I won't get into the details, but the key point is this. As you try and make things portable so that you can run the code that's running on one device onto another device, one of the fundamental problems you run into is that the amount of extra memory that is needed just to kind of keep all the machine learning stack going, which elevates the ability to kind of support different systems, starts eating up some of the very limited resources. So something to keep in mind. But nonetheless, the good point though is that you can actually deploy intelligent TinyML models onto small little robot applications. If you want to understand some of the details, figure out how to do this, you can go ahead and read our paper where we talk about how we engineered this machine learning inference framework to have a very, very small footprint. It's actually quite portable across multiple devices and can run really interesting applications that I can talk about more later. All right, so I kind of wanted to just touch a little bit on that particular point because it is extremely important to understand some of the challenges around the space. But now what I want to do is really kind of land on the heart of the thing, right? Which is, let's say, yes, we can solve this issue of how do I take models and how do I run them on embedded systems, right? That's that intersection that we looked at earlier. Now what I want to talk about is like from the context of CoRL, where we're looking at interesting application areas, what are some interesting possibilities when we put all three pieces together? So specifically, I want to talk about what's the general role of computing in this sort of a paradigm. Right? What I mean by that is that often when we're talking about computing, I feel that we often take the computing substrate that we have for granted. Now, in this kind of talk, you already have been seeing that I've been emphasizing, hey, like you got to pay attention to what the impact of that computing subsystem is. Right? So if you take a regular vertical stack look, right, this is pretty prototypical. Let's say if I'm doing some sort of reinforcement learning related navigation task, right? This is a prototypical sort of a stack that I would really have. In other words, I would have some sort of domains. I need some sort of domain randomization. So in order to kind of generate various scenes, so I'm going to have something that generates a rich variety of different environments. It might be a physics engine like Joko or something like that. Then, so I'm going to generate a lot of different scenes in order to just kind of, get rich data. Then I might have rich variety of different algorithms that I'm obviously interested in that are actually going to try and work on those different scenes that I'm creating, right? Maybe pick your favorite thing. It's a SAC or TRPO or something like that, right? So we're going to try and explore the different algorithms. Then, of course, and you can get into like policy architecture, right? Which is like, how do I do hyperparameter tuning and things like that in order to make the whole net effectively efficient? Now, I would argue that by and large, typically when we're thinking of the intersection between machine learning and sort of robotics, specifically robot learning, I would argue that like we largely tend to focus on these top three things. Now, these are obviously extremely important things to focus on. Over time, in fact, I would say that domain randomization, and these are things that have kind of like, just matured to the point that we have understood their criticality and that they play a really fundamental role. In a similar way, what I want to try and bring to the table today is to try and get you to understand what's the role of computing in this kind of a stack. And I'm going to try and convince you with some examples that if you don't take on board the computing constraints fundamentally as part of this design stack, then you will actually end up having suboptimal performance when you really deploy, when you go from training models onto the real device, you're going to have a gap. Now, in some sense, you would say, yes, I know that gap exists. This is called sim to real, right? I do things in simulation, and when I go over to the real device, I have a problem, right? But typically what you're talking about when you make that sort of sim to real gap issue is that you're thinking about the fact that the environment is different, right? Your simulators are not fully representative of what the real world looks like. That's what you're talking about. In a very similar vein, I'm going to try and convince you that if you don't take the lowest level of the substrate into account, which is actually doing all the grunt work of computing, you're actually going to have another hardware-induced gap, which is in fact part of, I would argue, that it's sim to real gap. So now, one of the key things to kind of keep in mind is that the reason you want to look at this full vertical stack going from the environments all the way down to the compute is that it's a really rich design space, right? So just illustratively, you're seeing a lot of different colored dots down here. And one of these dots is a particular manifestation that we're going to have in terms of what that robot is, right? It'd be in the physical sort of form factor. It's in terms of like the compute engine that you actually have and what kind of sensor you can pack in and so forth, right? So the point I'm making is it is a really rich design space. Now, the key thing, again, I said, is that I want to talk about what the role of that hardware element is, because when you talk about TinyML, that compute engine becomes actually quite critical. Now, if you look at any kind of, let's say, end-to-end learning engine, right? What do you have? You have some sort of environment generator, something like AirSim, or pick your favorite simulator that you would have, right? It's kind of generating the environment. You've got some sort of input data that's coming through, that's where you're actually doing your training, right? So that might be the stuff on the left and on the right. For example, if this is a UAV, I might have an environment here. I have some sort of compute engine, then I have a flight control stack, which is actually generating this. Now, in this kind of context, there's this notion of what we call as hardware in the loop. The hardware in the loop basically says that, hey, like, I have a flight controller that is actually generating the commands. So my simulation engine is taking hardware commands coming through about how the UAV has to behave inside the simulated world. But often what we do is that we tend to leave out this bit down here, right? This left-hand portion where the algorithms are running, we often tend to take the system that they're running on for granted. Why? Because look, when you're training your algorithms, you're often kind of just using high performance GPUs and so forth, right? Things that consume about 300 watts, 400 watts, right? That actually need to be physically located in a server room. But when you train that model and you get this nice little model and you're like, hooray, I kind of have this network that's actually able to perform the task. Well, the question is, how well does that algorithm actually perform when it's actually running on that big GPU versus when you actually port it over to a small device? That's where you get the gap. The way the networks actually behave in the real world is not just all about the environment issue. It is also about the compute substrate. When you take that trained model, which is working typically in your high performance system, and you drop it into a small device, it behaves differently, period. It exposes a whole new set of blind spots that the network actually didn't know about. Let me give you one example to kind of convince you about this. I'm showing you data for two systems. Arbitrarily, we chose, it's an Intel Core i7. Think of it as something like, it's a laptop kind of a system, a big beefy system, relatively speaking. And I just arbitrarily chose a Raspberry. A Raspberry is a small little embedded device. This Intel Core i7 will probably consume something around 30 to 40 watts. This Raspberry is going to consume between like 2 watts or so. So it's an order of magnitude difference in terms of the capability, in terms of just the overall performance as well as the power consumption. And what this chart on the top is showing you is the trajectory that a UAV that would take, an autonomous UAV would take, if I happily assume that the network is going to run on some sort of high performance system. Let's assume that I train the system on this Intel Core i7, and I try and deploy it onto a similar system. Okay, well then what you see is that you sort of see this nice purple trajectory, which is going straight from the start point to the end point, and it's a pretty effective trajectory. And instead, now, if I take this train model, which was originally trained on a nice big beefy system and evaluated on that big beefy system, and then I drop it into a small little device, what you see is the trajectory is actually inefficient and actually takes much, much longer. And you can see that in terms of the number of steps it takes in order to go from its starting point to the end point. Now, you try this across many different scenarios, you fundamentally get the same result. And the reason this happens is that it's exposing that hardware blind spot that is there. What do I mean by that? When you're taking a small, weak computing system, the amount of time that weak computing system takes in order to run the network is going to be much longer than if I was running on that i7. What this means is that effectively for the network to kind of make its forward pass through all those layers, in that time when I'm actually doing the compute, I effectively miss perception data that is coming through because I'm still in the middle of processing it, right? Now, typically, you don't run into this if you're just kind of ignoring the compute stack and you just assume, okay, I'm just going to be able to run this on some comparable sort of system. But that is actually not true. And I'm talking about this even more so in the context of TinyML, where you take models and then suddenly you try and deploy them onto small little robots, and you find that, hey, there's a substantial difference in terms of how this agile robot is supposed to be performing. It's not performing as well as it did in the simulated world. Now, so what am I trying to get to? The deployment platform that you have, it has a direct impact, quote unquote, on the performance, that is the success rate, the latencies, and how well the learning algorithm does. And so we might actually take that full vertical stack into account, and that is sort of key. Now, there's a paper that actually gets a fair bit into the depth of all of these little nuances. And of course, it does the complete stack, right? So I kind of cherry picked out one interesting data point out of that to kind of convince you that, hey, the role of compute is pretty critical when we're actually trying to get smart policies out. Now, pushing that a little further, let's say, I've got, I have to build this robot, right? I've got a whole slew of different sensors, autonomy algorithms, different kind of compute platforms, and different systems under which I'm going to be able to deploy. Let's just talk about UAVs yet again. Now, I can take a lot of these off-the-shelf components, but the question is this is a pretty large design space if you think about it, right? What is the optimal configuration? How do I kind of build a system? Do I manually kind of cherry pick all these components and put them together? Do I kind of do something intelligently where I might have some sort of push button solution? I say like, bam, I hit this button and pops out in a system that actually kind of fits my needs. So in some sense, what you want is you want to be able to design automated computing engines that effectively are able to take this rich design space and some sort of constraints and be able to generate a system that you want. I'm going to touch on something called autopilot. And these kinds of things are going to be extremely key in order to enable agile robotics in the future, because if at this point you are willing to run with me that compute does play a role, then for people like me who actually build these systems all the time, I'm constantly looking for, look, throw a whole bunch of different things together and I will build a system that automatically generates the best system for you, right? Given whatever your physical system constraints might be in terms of size, weight, and power. So let me kind of talk about what a system like this would look like. And again, this becomes extremely critical in the context of TinyML because you have extremely tight constraints in that space when you're trying to deploy these small little machine learning capabilities at the endpoint. So, you can structure these things in terms of specifications. So at the beginning, for instance, all you want to be able to do is get a specification and say, hey, these are my latencies. I've got to have a success rate of this much. I've got to have a latency in order to process this. If I'm going to deploy this on this device, I need to have a latency of, I don't know, maybe 16 milliseconds at best. I needed to keep it at real-time rates. You tend to just give it a specification in a file. Then you want to have a design space exploration engine, right? Which basically uses whatever evolutionary algorithms. So pick your favorite way of exploring some sort of parameter space in order to be able to take those constraints and try and meet those constraints from getting a network that is able to, for instance, perform the task accurately and be able to meet the physical latency constraints when you deploy it onto some sort of embedded device. And the third part would actually be understanding the physical components of the system itself. Now, a robot has certain characteristics. You know, for example, if you have a UAV, well, how fast it can go is not just, it's a function of the physical rotors, right? The thrust and so forth that you can generate, how quickly you can accelerate and so forth. But if it's an autonomous vehicle, it is also the role of the compute system, because it's about being able to process that information. Just because I can fly really fast doesn't mean I can actually just fly that fast, because if I can't process the obstacle that's coming in front of me, I might just very well crash into it. So this leads into this really interesting cyber physical co-design that you actually want to perform. And again, at extreme small scales, you're going to have to meld these two things together to be able to build these robots extremely fast and iterate on them quickly. So this little component that I'm showing you here is in the context of UAVs. I'm not going to go into the details. Happy to talk about it later. But the key thing it's getting to is really looking at what the physical components are and trying to balance this network policy you might come up with in a way that, hey, this network policy in terms of the accuracy, in terms of the latency and so forth, does actually meld well with the system. And out comes some sort of design point that says, hey, you know what, this is this BNN policy that I might have for end-to-end learning, for instance, and here is a chip that actually is the kind of design that you would want to have that would work well for the kind of specifications you gave me in terms of the robot physics. Now, you can actually push this even further. Now, this is obviously going to be pushing you all to the limit because it's starting to go pretty low level into the system stack, right? So this autopilot generates some sort of design configuration, right? It says, okay, well, I've got this robot that can move this fast. It's got to perceive this fast. I can come up with a network that's got this success rate, voila. Now what we can do is we can actually take this and say, hey, you know what? Let's actually build a custom chip. This is a little different than what I had talked previously about, which was actually building, you know, taking off-the-shelf components and kind of putting them together. What you can do is you can actually design a custom chip. A little bit of a sidestep, but I'll tell you, you know, one of the things that we're all facing in computing, right, is the fact that computing's performance is basically slowing down. This is why we're starting to build what we call as domain-specific accelerators. In other words, we specialize for domain. A domain would be like machine learning. We specialize. We build TPUs, GPUs, you know, a whole bunch of different accelerators just to run one gem kernel very efficiently in some craziness, right? Now, you can actually take that sort of an application domain specific thing and say like, look, I've come up with some particular system and I can customize it real quickly. Think of it as like going on Amazon, pushing, oh, I would like to have this particular chip that I would like to put on my little hammer robot. And voila, in 1 week, a chip shows up at your door. That is effectively where we're all pushing the computing industry at this point. So there are ways to actually kind of go to that extent and build what we call as a system on chip designs automatically. Now, a lot more details in this particular thing, but the key nugget that we're trying to get to is like, we want to automate the search space for all these kinds of building these autonomous robots as they come in different form factors and sizes and so forth. So, and then you need to consider both the cyber components as well as the physical components, and you can generate custom computing solutions that meet a very particular task's goal. In the context of TinyML, it often is very, very specific to a given task because TinyML is dealing with a few sensors, one sensor, and so you tend to want to customize for those things. Now that's been in the context of UAVs, right? But I don't want you to think like, oh, this all stuff is only in the context of autonomous drones that I can have. That's not true. You could actually generalize these principles around what we call as robomorphic computing, where the intent is that you'd actually look at the physical, the robot's morphology, right? The physical structure of the robot. And out of that, you can extract really interesting principles about the links and the limbs that the robot has and be able to use that information to automatically generate these custom solutions. So just a point of generality here. Where am I going with all this? Taking a step back up, right? So I'm trying to come back up here now. You know, I talked about how we are used to kind of having this sort of a vertical stack when we're exploring the design space of coming up with algorithms and trying to tune those policies. Now, and then I emphasize the fact that, hey, increasingly we are going to have to bring the compute element into the design space, right? Because if you don't think about compute as being an integral portion of building the system, then you're going to potentially run into suboptimal performance. I gave you one example. There are plenty of other examples where you kind of run into this. So in a way, it is a new sort of a gap that we're trying to, you know, tell people about. And if you understand that, then you can actually do really interesting co-design across the entire vertical stack. So this is nothing new, right? Co-design is something that the community has been doing in the machine learning space for a bit. Like, you know, we've been talking about neural architecture search, AutoML, AutoRL, effectively in some crazy sense, this would be like auto DSE, which is the entire design space can be actually explored all together at one time. And you want to be able to iterate on this. So coming one level back up, what I've talked about today is really kind of said like, the machine learning community and the robotics community has been working on really interesting intersection down here, which is what CoRL is all about. And what I'm personally sort of hoping is to expose you folks to some of the interesting challenges that come about and the opportunities that it enables when you actually start thinking about smaller scale embedded systems where you're physically trying to deploy things onto the robot, where you don't have the power, you don't have the size, you don't have the physical capacity to actually host these devices. And so this opens up a really rich space, at least in my head. And in an ideal world, what I would love to see is some interesting sort of intersection between machine learning, robotics applications, and embedded systems, right? So in an ideal world, what will continue to happen is that if we look at the paper submissions that are happening at CoRL, right? So I kind of just looked up some prior stats on CoRL. This is a very healthy sort of a venue that is actually growing in terms of its community. And over time, one of my wishes is that we'd increasingly see a new domain, sort of a set of papers that are coming in that sort of sit at that intersection where we're not just thinking about building better algorithms, but we're also thinking about building better systems that can actually run these algorithms on device efficiently. I was a little disappointed because I remember like seeing some sort of papers on the open review system kind of a while back that were actually trying to push the community towards thinking about this intersection. I was disappointed that they actually didn't get it. They were not my papers, for full disclosure, but I just happened to find them interesting. But I'm sure there were pitfalls, or the community felt like it was not a good fit. What I'm arguing for is that there's an interesting space that we should be opening up, right? How do you sort of build this, right? It's easy to kind of say, yeah, we should do this. How do we kind of jumpstart? There's a virtuous cycle that has to get lit up, right? Often in any kind of ML space, right, it all comes down to having data sets, comes down to building models and having systems. You got to get the right set of data sets. And TinyML, for instance, the question I often say is like, hey, we have this really interesting, amazing space of tiny machine learning that's happening around the ecosystem, but what's quote unquote the ImageNet of that, right? Or what's the Atari benchmark suite for that, right? We don't have that yet, but if we kind of think about this systematically, we might actually be able to pull together data sets and create an opportunity in order to foster this environment. And if we can get the data sets going, then we can obviously get the models going. Once there are data sets, the community jumps on board and we actually start pushing the models. Now, hopefully one of the key things that you all get away from this talk is that like, well, these models got to be really, really small. I'm talking about models that actually fit literally in the order of a few kilobytes. By the way, again, if any of what I've said in terms of the resource constraints, they seem really, really small, don't let that fool you, right? Because this is why I gave you the example of K-Siri and all these kinds of interesting applications that are already out in the consumer market. I'm talking about bringing some of those possibilities over to the robotics kind of environment, putting intelligence on these really small devices. And that intelligence might be, for instance, perhaps just doing better end-to-end control, right? That might just be it. But nonetheless, it's about being able to enable that. And if we have the models, folks like me will go ahead and build the systems that you all need in order to run them efficiently. Today, partly the reason I talked about TensorFlow Lite specifically for microcontrollers and so forth is to actually expose the community to kind of have an understanding about what can I do today, right? There are some challenges. Yes, there's a lot of heterogeneity. A lot of these devices are extremely specialized, but nonetheless, there are tools and there are frameworks that are coming about right now that are supported at large scale, right? Like by companies and so forth, that actually enable us to run these models on these extremely small systems. And that kind of generates the virtuous cycle. But if you really want to ignite this in terms of bringing communities together, which, as you can see here, these are, the systems community versus maybe the ML community, these are rather disparate communities. If you want to try and really bring life into this, what I believe is that we need more benchmarks. Now, benchmarks are often a super overloaded term. When I say benchmarks, it means something very different from when, the machine learning community, the robot learning community usually means when they say benchmarks. So let me define what I mean by benchmark. When I'm saying benchmarks, it's about kind of understanding not just what is the data set effectively, or what's the training environment where I'm exploring my policies and so forth, but it's also kind of standardizing them in a way that systems folks can actually take an environment or a certain model and say like, hey, these are some of the golden baselines that we have for these particular interesting tasks. That creates a common language in order for people like me who are systems folks to actually be able to engage with the robot learning community, to be able to build these interesting little widgets that'll enable us to build onboard intelligence, right? Now, if this seems like a bit of a stretch, I can tell you this can certainly be done. These benchmarks that sitting at the intersection can certainly be done. In fact, I'm one of the founders of ML Commons. I encourage you to just kind of Google it. It was actually kind of built out of this need that we saw in the community about 4 years ago, where the intent was, how can we build systematic machine learning systems, accelerate the pace of machine learning systems so that we can enable new application areas? But everybody in the systems community was talking many different languages. They were talking about my performance is better than your performance, but they were running totally two different things. Like there was no standard benchmark. So we created what was called the ML Perf, which then became ML Commons, this big entity that standardized the thing. So we all spoke the same language, and this has resulted in some remarkable acceleration in the machine learning systems community. Now, if I can borrow lessons from that, I would say that yes, building benchmarks has the potential to kind of drive innovative application areas, right? So at the intersection of machine learning, computing systems, and robot applications. Specifically, obviously, I'm really passionate about bringing around TinyML into robotics. So in trying to wrap things up, what I've talked today about is like, what is TinyML, right? It's all about low power, cheap, and commodity hardware use, and being able to run ML on these small little devices. And then I'm kind of trying to say that, hey, you know what, this capability is great for places where you have lots of rich sensors. And robotics is in large capacity. I feel like there's a lot of sensing of information, perception, planning, control. Like everywhere you see, there's going to be some sort of sensing modality going on. Now, while I've said that, how can TinyML really unlock robotics? Now that is a challenge that's for the community and not for me, right? So hopefully what you take away from this talk is that there's an emerging space that's actually really growing really, really fast. If you just Google this space, it's incredible. Like I have a class that I teach in tiny machine learning that's got about 58,000 students across the planet, right? And it just continues to grow. There's a remarkable amount of interest in terms of building these kinds of capabilities and running ML right at that endpoint. So if that's already happening, then it's really about being able to leverage that in order to unlock some really interesting application areas. So that is what I'm kind of hoping, you folks will get from my talk. I'm talking about many different things. Of course, it's not me doing a lot of the work. It's me being able to kind of orchestrate these things, but I want to give a big shout out for the students and a lot of my colleagues who've actually participated in kind of helping bring this really interesting intersection together between machine learning, systems, and robotics. With that, I started off saying the future of machine learning is tiny and bright, and that is what I go about preaching all the time. But I thought for this community, I'd say that the future of robot learning is tiny and bright, and hopefully this opens up a whole new avenue for future research. And with that, I want to thank you all for your attention. I'm going to turn it back to you all.
Awesome. Yeah, thanks for the great talk. So I'm wondering, does anyone have any questions? Yeah, there's a couple back there. Yeah.
Hey, thanks for the great talk. I had a question about co-design. So I guess the big plus with co-design is you can model these interaction effects that you wouldn't if you're treating the components.
I just want to say that I actually don't hear anything in case anyone's saying anything.
Hello? Can you hear me?
Yeah, okay.
Maybe in the back, is there anything you can do?
Hello?
Can you hear us yet? Can you see me moving?
Wayne, can you hear anything?
Yes. Yeah, I don't know.
Yeah, I can hear. I can hear you.
Oh, but do you hear anything else? I guess I don't.
Maybe we should go to virtual questions. I'll be back.
Oh, actually, there's a, yeah. Actually, there's one online question.
Okay, great.
Mm-hmm.
Wait,
I don't see the question, so I have no idea.
Wait, can you hear me?
So maybe I can tell the online question for Vijay. Yeah. So the question is, models are generally tuned to maximize the training speed on GPU, which often means taking advantage of the GPU's high memory bandwidth when deploying on embedded system.
I'm sorry, wait, what was the question? I only caught first part of it about training them for high bandwidth GPUs. Oh. I see it, okay. So the question is, VUA models are generally tuned to maximize training speed on GPUs, which often means taking advantage of GPU's high memory bandwidth. When deploying on embedded systems, however, memory touches dominate the energy cost. What strategies exist to take a high memory bandwidth model and making it energy efficient? This is you're talking you're talking to the key point, right? So it is true that, like, you know, when you're training them, it is often that we're considering like what ends up happening on the GPU, but hopefully the key point that you got is that, like, first and foremost, it's not about just taking that model and then shrinking it down. This is often the misconception that we often have, right? Is that, oh, look, I'm going to end up with a big model and then I'll just throw it overboard to the actual ML deployers, right? And the deployment pipeline folks are actually going to worry about, how do I take this model, shrink it down, and then actually put. And this is why I was saying, like, it does not specifically work well. This is a misconception that people often have. What you actually got to do is to actually take that embedded system characteristics and actually put that into the training loop. And this is extremely key, because the network effectively has to learn the implications of that hardware, how that hardware actually behaves. That latency characteristic is actually something that affects the learning behavior. And that's what I was trying to kind of hint at when I showed those UAV traits. And there are other examples that we have where you actually see the exact same behavior. So then you might ask, like, well, in that case, how can I do this? It's like, you know, I can't train on an embedded system. Yes, that's totally true. You can't physically swap the systems. However, what you can do is that you can emulate the delays or the latencies that are bound to happen on the embedded system, right? And this is very easy to do, because you would actually figure out, a quick profile run will tell you what the embedded system looks like, what its performance looks like, and then you would effectively mimic that into your training loop. And we have done this, and what you immediately find is that the gap, quote unquote, that you have in taking the model from a high performance system, right, and then deploying it onto that small device, ends up actually resulting in exact behavior they would normally expect, right, from the embedded system. That is a big thing. So just to summarize again, I think the notion of just training them all, then shrinking it or doing whatever optimizations you want to do to squeeze it onto an embedded device is the wrong approach. It conceptually makes the model fit, but it does not mean that the robot's actually going to perform the way you expect it to perform. It's often a remarkable sort of an oversight. And that's what, like, hopefully one of the papers that I talked about actually gets a lot into the detail around this. Hoping that answered the question. If not, please feel free to chime in the chat. And the other question is, does the same concept of compute, memory, compute, sensor, hardware, software, and algorithm co-design apply to full-size hardware too? For example, could the same concept be applied to optimize a self-driving car design to minimize energy usage and maximize safety? Beautiful question. The answer is absolutely yes. It is wickedly yes. And that is what is super exciting about this space. Once you understand this relationship, you find that it really, yes, it doesn't really matter. In the context of embedded systems, it gets extremely tight. You have to do it. That becomes the kind of need. But even if you kind of scale it back and say, okay, well, I've got this ginormous compute system in my trunk, right, because I have, like, you know, a big autonomous taxi that's running around, you still get into the same issue, the same fundamental issue. It just happens to be a little bit bigger, right? So it totally does play out that way, because, again, these autonomous machines are basically acting in a real-time loop. And so this co-design principle actually is something very important. And in fact, we're actually working on it. There's plenty of, like, research that's actually getting funded in this space. Third question. Hopefully I didn't miss something, but I hear much about training models on embedded systems. Is this possible since it could be very useful. Do any lightweight heuristic optimization methods exist for this purpose? Okay, so this is all about on-device training. I will tell you candidly, I do not have a very sharp and crisp answer on this, because I think on-device training is still very much in flux. What do we mean by on-device training? Clearly, we don't mean fully training the models from scratch, right? We're often talking about some sort of transfer learning-based method or something like that. That, I think, yes, that can certainly be done, and that's what people are doing. We already do this in the context of speech, right? So in the context of fine-tuning it for a robot task, I certainly think this can be done. But I personally have not necessarily been looking into that space as much, because I think that whole space is still evolving and people are trying to wrap their head around it. Fourth question, Vijay, when you say that you have to include the embedded system in our design loop, what kind of tools exist to be able to model that in our simulator? These are such good questions, my friend. I feel like I'm actually excited because you folks are getting it. Yes, so some of the papers that I've hinted at, that's why I was including the links to some of those papers. Like the air learning tool, for instance, that basically makes the case for having hardware in the loop. And you can actually use this in the simulation environment we built, but setting our own work aside, because we build them in order to explore these questions. Virtually in any sort of a simulation environment that you have, you can actually do this, right? So it doesn't have to be that like it is wrapped into some existing framework. Literally, if you understand the notion of hardware in the loop, then it makes sense that if you understand the concept of that, the triangle that I showed you, the simulation environment, the on-device compute system, and then, whatever other controlling logic that you have, if you understand that sort of a triangle, whatever that hardware in the loop mechanism is, where you're looking at your policies and you're looking at your learning algorithms and so forth, you simply need to make sure that that is actually running on a representative device. So that might be your GPU. You might introduce delays into it in order to mimic that, right? As long as you do that, that effectively closes the loop. In any simulation environment, you can do this. And that's the beauty about the whole thing. So it's the insight that I wanted to share. Again, the papers are just points for you to look for reference. Next question is, I think that should be it. Yeah, that's right.
Awesome. Let's thank the speaker for maybe when he's.
Finally hear you. Okay, good.
So if this happens again, if you have questions, maybe just post it on the virtual chat as well. And yeah, but yeah, Wei, I think you can go ahead and maybe take over the next. For the next
yeah, sure.
Great.
Thanks, Vijay.
Yeah, thank you.
Very, very nice. Super, super cool.
Appreciate it.
Yeah. Hi, Dr. Pierre Voudier. Pierre-Yves. Hi, yeah. Nice to meet you. Yes, just to make sure my French pronunciation is correct. Pierre-Yves Voudier.
Yeah. So you tell me when I think online and we can begin?
Yeah, I think we are online already. So first, let me introduce the next speaker. Today, Dr. Pierre-Yves Voudier will give us a tutorial on intrinsically motivated goal exploration algorithms for open-ended learning of skill repertoires. Okay, Dr. Pierre-Yves Voudier is a research director at INRIA and head of the INRIA and ESTA Peristaltic.
Okay, thank you very much. Do you see my slides?
Yes, and before he was a permanent researcher in Sony Computer Science Laboratory for 8 years. He studied theoretical computer science at École Normale Supérieure in Lyon. He received his PhD degrees in artificial intelligence from the University of Paris 6, France. He has been studying lifelong autonomous learning and the self-organization of behavior, cognitive, and cultural structures at the frontiers of artificial intelligence, machine learning, cognitive science, and educational technologies. He has been developing models of intrinsically motivated learning, pioneering curiosity-driven learning algorithms, working in real-world robots, and developed the theoretical frameworks to understand machines and humans to discover, invent, learn, and evolve communications systems. He has published 2 books, more than 100 papers in international journals and conferences, holds 8 patents, gave several invited keynote lectures in international conferences, and received several prizes for his work in developmental robotics and origins of language. In particular, he is laureate of the INRI National Academy of Science Young Researcher Prize in Computer Sciences and of an European Research Council Starting Ground, Explorers. He is also editor of IEEE Computational Intelligence Society newsletter on cognitive and developmental systems, where he organized the interdisciplinary dialogues in cognitive science, AI, and robotics, as well as an associate editor of IEEE Transactions on Cognitive and Developmental Systems, and Frontiers in Neurorobotics. He has been chair of IEEE Computational Intelligence Society Technical Committee on Cognitive and Developmental Systems in 2015 to 2016. He is also working actively for the diffusion of science towards the general public through the writing of popular science articles and participation in radio and TV programs, as well as science exhibitions. So Dr. Pierre-Yves, now the floor is yours.
Thank you very much. Thank you very much also for inviting me for this presentation today, the organizers. So today I'm going to introduce aspects of research on what with my team we've been calling autotelic agents, which mean agents that set their own goals and learn about the world by pursuing those goals that they set for themselves. And within an algorithmic framework that is relatively general and that we've been calling intrinsically motivated goal exploration processes. But before going into the details of this, I would like just to mention and thank many of my collaborators with whom I have been developing many of the works I will present today. So one extraordinary property of child development is that they spend a lot of time spontaneously exploring their environment. And they are not doing it because they are externally imposed some tasks. Rather, they are doing it because they are driven by different forms of what psychologists call intrinsic motivation, or what we may call curiosity in everyday language. And so during exploratory play, for example, they invent and they pursue their own problems. And such intrinsically motivated exploration has been argued to be key for children for several things, ranging from solving problems with rare rewards, but also to learn efficiently world models and to discover open-ended repertoires of skills. And so a number of teams in the world, including mine, have been working now for a while on modeling these capabilities, and also especially studying how they can be transferred into artificial intelligence systems, and robots in particular. And so in this talk, I will review some lines of research in this direction, which I think are quite important for the future of AI. So first of all, there are different forms of intrinsically motivated exploration systems, different kinds of experiments that children can imagine and choose to pursue when they are in a curiosity-driven exploration mode. So a first category, which we've been calling knowledge-based intrinsic motivation systems, relies on generating intrinsic rewards upon visiting some states S of t, or experiencing transition from S of t, A of t to S of t plus 1. And such intrinsic rewards include, for example, prediction errors, uncertainty, or information gain. So this can be seen as enabling an agent to choose to make prediction experiments, and this has often been made on short time scales in the literature. So here it's important to realize that there is no notion of goals, as opposed to another form I'm going to speak about in a minute. And so this family of intrinsic motivation systems is used quite often for solving external problems with rare reward, or also for efficient learning of world models when the goal is to do it in a sample efficient manner. But then a second important category, which we've been calling competence-based intrinsic motivation, consists in systems where the agent imagines goals he would like to reach in the future. So here the intrinsic reward is actually replaced by a measure of interestingness that's applied to the self-generated goals. such as, for example, a measure of competence progress to reach those self-oriented goals, and that is used to select which goal to pursue, which goal to sample and in what order. And so basically the agent decides which goal achievement experiment to make, and this has typically been studied over longer time scales in the literature, so longer time scale as opposed to knowledge-based intrinsic motivation systems. And so also this form of intrinsic motivation is used primarily to discover diverse repertoires of skills. And here when I say skills, I'm speaking really about parameterized problems, parameterized goals. And so in the talk today, I will really focus on this second family of systems. And this family of systems is also what we call autotelic agents. So there is a general framework that we've been working on to approach modeling this form of intrinsic motivation, and we've been calling this framework intrinsically motivated goal exploration processes. And it basically refers to all algorithms that have in common the following loop. So the basic loop is first observe the context, sample a goal internally, roll out the corresponding goal condition policy by using the current internal models, then observe the outcomes and update the various internal models for the next time the loop is going to be unrolled. I will come back into a little bit more detail on this loop later on. And so algorithms in this family differ along many dimensions. So for example, some are based on population-based techniques, which means basically that there is an explicit memory of policies associated outcomes that is stored in the agent. And examples of such systems are SAG-RAC or various quality diversity algorithms. But other IMJEP systems rely on goal condition reinforcement learning techniques, such as, for example, RIG or GoalGAN. You also have some systems that use learned goal embeddings, such as RIG, but others use hand-defined goal embeddings, like the system Curious. I'm going to quickly talk about those two systems. Some use learned goal achievement functions, such as the Imagine system. Others use predefined ones, like the L2 function in the embedding space in RIG. And some use goal sampling policies that are based on things like novelty search, like, for example, the skew fit algorithm, but also use other forms of goal sampling policies, for example, leveraging learning progress, like the Curious architecture. So concretely, how does this autotelic learning loop work? Let's go a little bit in more detail, and then even in more detail later on. And so basically, first the agent observes a context and samples the goal with its internal goal generator. Then it generates appropriate actions with its goal condition policy to pursue the goal inside the environment. And after it has taken actions and rolled out a full trajectory, it uses basically its own goal achievement function to evaluate its performances. So sometimes it might succeed to the goal it has set for itself, but sometimes it might fail. But even when it fails, most IMJEP algorithms include some forms of hindsight learning, which are basically a mechanism that is relabeling the achieved trajectory by a posteriori imagining the goal that could have been imagined and have been reached in this particular trajectory. And so this means that now you have an example of a successful trajectory for that goal, which enables to update usefully the internal model. But research on autotelic agent poses many challenges to achieve efficiently and autonomously this loop. And so here I would like to illustrate a few aspects of this research. So just also a remark before going into some examples. When I speak here about goals, I really speak about an abstract, generalized notion of goals, which means it's not like I'm not only speaking of goals as, for example, concrete configurations of a scene that the agents may want to achieve, but I'm really discussing about abstract parameterized problems associated to parameterized reward function to score the achievements of those problems. And so goals could be relatively concrete, such as, for example, pushing an object A to a location parameterized by X, Y, Z, and using a simple goal achievement function like the L2 distance in the object Cartesian space. But it could also be something like build something that has an image embedding that is corresponding to a certain vector in a spatial embedding space E. It could also be a combination of an objective with some constraints. So for example, a goal could be move as fast as possible while ensuring the steps are smaller than E, or have a style that is of type T, and the reward might be the speed if the constraints are satisfied, and 0 if the constraints are not satisfied. Could be, for example, to make an acrobatic jump with 2 loops while saying hello, or executing a following a natural language command. So it could be anything that can be parameterized in some space. But now let's begin by examples which are very concrete and where goals will not be so abstract. I will come back to more abstract goals later on. Let me begin by a simple population-based instantiations of IMJEP. So here we imagine a multi-dimensional robotic arm, and we imagine that motor policies are parameterized in a very simple manner, very simplistic manner. So this is just for the matter of explaining the basic ideas. And so basically here, the motor parameters is a set of vectors specifying the target value of the PID controllers of all motors. And then when this is achieved through the unknown dynamics of the robot body and environment, it's going to produce a trajectory of the robot. And then there is we assume here that there is a system for observing features out of this trajectory. And let's assume here we have decided to measure only the final 2D position of the tip of the arm after PID stabilization. And then something that we have now as ingredient of those IMJEP, and then later on I'm going to explain how we are going to use this, is that now we consider a space of goals, and actually the space of goals is actually a space of cost function, the space of reward function, which take as input the features computed from the trajectory and also each parameters of a given cost function, so a given goal. For example, tau here is used actually to compute the achievement of that goal, which is here simply, for example, if tau is the target tip position, simply the distance to the target tip position. But you'll see later, this can be much more abstract than this. Okay, so we have a space of goal, which is basically a space of reward function, parameterized here by a target position. And now, also, when we have the robot exploring, so it's going to progressively collect a memory associating the parameters of the motor policy theta, so the initial context S, and the outcome features of the trajectory W. And then from this data, there are several things one wants to learn. So first of all, we want to learn a predictive model that's predicting basically the features W given the parameters of the policy theta and the starting state. And this can be done using whatever your preferred regression method. And then we want also to acquire a meta policy, which is a form of inverse model, which given a goal or given a parameterized reward function, and an initial context is going to provide the parameters of the policy that will minimize this cost function or maximize the reward depending on the way you see it. And one way to do this is actually to do optimization over the forward model F that you have here, which you can do with whatever is your preferred optimization method. And then based on those tools, the basic population-based loop of the IMJEP goes as follows. So first of all, you have a bootstrapping phase in which basically you are going to sample random policies. So basically you observe the state, you sample a random parameter of the policy, you launch the experiment, you observe the outcome feature W, and you simply add theta, the initial state and the observed outcome to your database, and then you initialize a first forward model. Then there is the exploration phase, where now you're going to sample goals and try to reach them. So first of all, in first step, you observe the context, then you sample a reward function or a goal using a certain sampling strategy. I will discuss sampling strategies later on. Then you basically use your current inverse model for example, optimizing over the forward model. Then you launch the experiment corresponding to the motor policy you found. You observe the rollout of the trajectory, you measure the outcomes, you add that to the database, you update your forward model, and you update also the sampling policy. And then in the end, you can exploit what you've learned by exploiting the forward and inverse model you've been learning. So let's look at the corresponding usefulness of goal exploration, even if it is done completely randomly, as opposed, for example, to random action exploration of the parameters of the policy. So imagine that you have a multi-dimensional arm. Maybe you have here 2 joints, 7 joints, 20 joints, 100 joints. If you do random action exploration, if you don't have too many joints, the difference between action exploration and random goal exploration is not so big. But as you increase the number of dimensions, actually what you do when you do this is that you increase considerably the redundancy of the system and also the non-linearity of the system. And as you see, if you continue doing random exploration, you will actually discover less and less of the possible outcomes that you can do with this particular robotic system. On the other hand, if you do random goal exploration, you sample goals directly in the outcome space, you will see actually a graceful degradation of performances, and you really need to have many, many degrees of freedom until you really begin to be not able to efficiently discover the variety of outcomes. So in a way, doing even random goal exploration is a way to be efficiently discovering the diversity of outcomes that are possible with a given robotic system, such as the one I presented here. However, here I said you can be efficient with random goal exploration on random goal sampling, but still you need to be careful in what is the space in which you sample and how you sample it. Because, for example, if the space in which you sample the goals is smaller than the actual space in which it's possible to reach, then actually you will be suboptimal in discovering the possibilities. And if you increase the size of the hypercube in which you sample goals, you will also begin to be less efficient, as you will actually, in priority, only discover outcomes at the frontier of what's possible, but not so much within the cloud of what's possible. So maybe it means that we need more sophisticated mechanism than random goal sampling. And I will discuss that in a few minutes. But just before going into sophisticated goal sampling mechanisms, I'd like also to illustrate the fact that the loop I described now with a very simple kind of goals can actually consider much more elaborate kinds of goals. For example, this is what we observe when we look at quality diversity algorithms, such as the map-edit system, which can actually be formalized as a particular kind of IMJEP. So for example, in the map-edit system, you have this robot with multiple legs, and then it has a system of parameterized motor policies with 36-dimensional continuous parameters that control basically parameters of the oscillations of motors. And then it produces trajectories over a few seconds of rollout of the behavior, on which features that are measured that are the things like the forward speed, but also step patterns. For example, vectors characterizing portion of the time each leg is in contact with the ground, which is a way to characterize the style of walking, if you want. And then you have a space of goals, a space of reward functions, which are called cells in the map-edit systems. And so when you sample a goal, you actually sample a cell, and a cell actually defines an objective consisting of trying to maximize the speed while trying to display a pattern of steps that is respecting certain constraints. And so if you are trying to improve your capability to move fast within this particular style of walking constraints, you can actually improve the local capabilities. And sometimes you try to do this, but you don't manage to improve with this style, but you find another style which improves other cells. And this is what the form of hindsight learning that's observable in that kind of system. And so basically here, it means that a goal is something that is the combination of a cost function that might be, for example, interesting for an end user engineer, combined with compliance with some constraints, and the space of constraints is parameterized into a number of cells, and so it's equivalent to have this space of goals. And that's also a way to see how IMJEPs can enable a robot to explore a diversity of skills that are going to be still relevant and useful for a downstream task for an engineer. And this is in particular very useful here, as the authors of this paper were able to show that if you learn to walk fast, not only with one style, but a diverse set of styles, then in case, for example, you have a motor that is broken, then you could probably find a style of walking that does not really use a lot this broken motor and still is very efficient at walking fast. So you can readapt very fast. Okay, but now let's come back to one of the important problems is learning to sample goals in a way that's better than random goal exploration, and how to realize some forms of self-organized learning curriculum. So what's an interesting goal? What's an interesting learning experiment? So there are many ideas that have been proposed in the various literatures, actually ranging from psychology to biology to AI to reinforcement learning, quite often independently. So one example of idea is that an interesting experiment is one which leads the experience of high novelty or high control errors or high prediction errors. But in the real world, it's not going to work at all. So this will lead, for example, a robot to spend its whole day staring through the window, making movements with its arms and trying to predict how the color of cars passing by change as a function of movements. And of course, it's completely stupid. And you will not learn like this. But if you tell the robot explore goals or situation which leads to high prediction or high control errors, it is what it will do. Among other ideas, several of them are interesting, but I will now focus on one that we've been studying a lot, initially inspired by some limits of theoretical ideas of biologists Varela and Maturana, but that has also shown to be very robust to guide robot learning in the real world, as well to account for some developmental phenomena that we observe in human children. And so this idea is that the interestingness of a kind of experiment is proportional to empirical change in goal achievement errors. And so this change can basically be an improvement, but it can also be a decrease in competencies, which will enable to drive interest to parts of an environment that change or to skills that are being forgotten. And so we call this idea the learning progress hypothesis, but actually it includes also learning regress. So such a mechanism can actually self-organize a form of learning curriculum. And so to visualize how it's possible, let's imagine an abstract situation on the top right here, where a robot is confronting with 4 kinds of sensory motor activities, each of them characterized by a different learning rates. As we see on this graph with the different colors, which correspond to different kinds of activities. So each curve basically shows the evolution of the errors in each of those activities if the learner would focus on practicing each of them. But then the exploration driven by the learning progress principle basically will result in avoidance of activities that are too easy or too difficult to learn. So here the blue one and the red one. And first focus on the activity with the fastest learning rate. So here, initially the black one, and eventually when it starts to reach a plateau, to switch to the second most promising learning situation, which is here the green one. So let's see here how this kind of goal sampling mechanism based on learning progress, as well as an advanced form of the IMJEP loop I presented before, can be instantiated in a more complex real-world robotic experiment. So here we have actually an experiment where a humanoid robot can explore its body and how to interact with many objects. Some of them can actually be used as tools. There are also several distractors in the environment, which means that there are objects that are either too far to be moved or that move autonomously in a random manner. So here the robot is actually able to track the position, the color, and sound of all objects. So we are actually assuming there is already a sophisticated perceptual system that is object-centered and that is already working and given to this robot. In terms of action, so the robot can produce actions that are parameterized here by 32-dimensional dynamic motion primitives, which I guess many of you are familiar with, which are basically dynamical systems with some parameters. Then it has several actually groups of behavioral descriptors that we call modules that are characterizing the trajectories of various objects, as well as the trajectory of sounds and the trajectory of light patterns both produced by those objects. And so in total, we have actually a descriptor space with 310 dimensions, but they are organized in around 15 modules, which correspond to actually particular objects. and each module has around 20 dimensions. And as actually you see on the right, we've actually a farm of these humanoid robots that has enabled us to make many experiments. Actually, these robots are the open source Poppy platform that are 3D printed and that were also designed by my team, and that are now disseminated, and further versions have been produced by both a startup company from the team, which is Poland Robotics, as well as an NGO, educational robotics, called Poppy Station. And that's used actually by many universities and schools in the world. But okay, let's come back to the machine learning experiment here. Okay, so now let's look at the system. And just one thing I want to emphasize is, as compared to the system I described before, one important change in this experiment is that goal exploration will be modular, which in the sense that when the agent is going to set a goal, it's going to be setting a target trajectory for only one of the different objects in the environment. So that's not a target configuration. That's not a static configuration. That's more complicated. That is a dynamic trajectory, the goal, but it's not also a dynamic trajectory of the full scene. It's only a dynamic trajectory of part of the scene corresponding to one object. And then the way to sample goals is by actually estimating the learning progress or the competence progress to control the trajectories object by object. And so initially the robot will not know where there is learning progress and will progressively discover and sample the goals where it is providing most learning progress. So initially, actually, it doesn't know where learning progress can be made, so it samples goals for many objects around, but relatively quickly, it will discover that there is one special object for which it makes most learning progress, and that is actually the hand. The hand initially is perceived as one of other objects, but it is nothing special for the robot initially. It becomes special because it's the first object that is providing high learning progress. So here we actually see internally in the head of the robot the learning progress curve for the hand, which is rising. And so by doing this, actually, it is now focusing on setting goal for the hand, which is actually going to lead to discover a higher diversity of movements of the hand, which in turn will lead the robot to discover how to move those two little red things, which are joysticks. And now they become a niche of learning progress, and now it's focusing on moving them. But then actually he discovered that moving one of them actually leads to learning progress in controlling this little white electric toy that you see on the right. Actually, one of the joystick controls these white electric toys. And so now setting goal on the white electric toy becomes also a source of learning progress, and he's focusing on this. And then in turn, he discovers that setting goals on moving the tennis ball here around becomes interesting. And so in a few hours, he moves from not knowing how to explore to learning to explore the hand and learning the joysticks, then learning how to control the electric toy, and then finally learning how to control the ball. So he learned a whole set of skills, even in the presence of multiple distractors that are in the environment. And some of the skills are non-trivial, such as what you observe right now. And this is done basically between 10 and 15 hours of real time on the physical robot without any simulations. Okay, and so now if we look at the curve, we can also see, interestingly, the efficiency of such approaches. So here, the system that is sampling goals with learning progress in a modular manner are the blue curves. And what we show on those different curves is the speed at which the robot is discovering a diversity of skills for controlling various objects. So here you have the hand, the left joystick, right joystick, the white electric toy, and then the ball. And then you have also other sound and light things. So the blue curve, as you can see, is close to the top for most of the curves. And so we have some baselines and an oracle. So among the baseline, we have random policy exploration. This is the green one. The green one is only good for exploring the hand, but starting from the left joystick, it becomes very bad. And it's very, very bad, for example, for discovering how to move the ball. It does not discover at all how to move the ball. Then you have another baseline, which is what we call single goal space. It's like, imagine we would like the robot from the start to learn to move the yellow ball. And so instead of letting him free to explore goals about various objects, we impose this robot that he should only sample goals about moving the yellow ball. So it's basically suppressing most forms of curiosity. And so actually we see that this is actually very, very bad at learning to control the ball and even the ergo robot. So that's very, very bad. And it shows the usefulness of being curious, exploring the whole set of environment, even if you want to solve one specific problems like moving the ball. And then we have an oracle, which is the green curve, which is basically trying to put by the hand most of the expert knowledge we have about this robotic system to design by hand a curriculum of learning, where we actually start by saying to the robot, first focus on the hand, then on the joystick, then on the electric toy, then on the ball, etc. And actually what we see is that the oracle is pretty good, sometimes even better on the joystick and the ergo robot, but for the ball, actually it's ending up much worse performance than the blue curve, which is using learning progress for sampling goals, and even the orange curve, which is random goal sampling in a modular manner, but without the learning progress, which is less good than using the learning progress, but better than the oracle and orders of magnitude better than the two baselines. Okay, so now this was examples of IMJEP with population-based systems. So here again, remember this was a population-based system in the sense that the robotic system memorized explicitly the history of policy parameters and outcome it reached, and it would use that to train a forward model, which actually was trained in that particular case online as depending on the goal, you train a local forward model and you repeat that. But it's also possible to build an IMJEP architecture with very standard modern goal condition deep reinforcement learning systems. So this is, for example, something that we've been doing with the Curious algorithm. And so here we are basically starting from a very standard deep RL architecture, which was DDPG, but we could have used the SAC algorithm, for example, also. And the update that we do is that now we are considering what's called UVFA, which means that in addition to the current state in input of the actor and the critic of the neural network of the reinforcement learning system, we add some input neurons which encode the goal. And then updating the UVFA system, because we want to have modular goal exploration, like in the system I just presented, actually, we have a modular encoding system which enable to encode the fact that sometimes the goals are not about moving all things in the environment, but only part of the thing. So let's study this idea in the context of the simulated robot we have on the top left here. Here, the robot is free to choose or switch to any goal he might try to learn and achieve. And in this particular experiment, he is given a space of goals to sample from. That's including reaching, grasping, or stacking various objects. So one challenge is that here we put distractors. So for example, there are objects that move randomly and cannot be controlled. But here there are many goals in this goal space that are impossible due to these distractors. For example, stacking uncontrollable objects is impossible, but initially the robot does not know. But also even among the feasible goals, some are easy, some are more difficult, and depend on mastering other goals to be learned. So if the robot samples goals randomly, it will be very, very inefficient at learning. And so basically there is a need for automated curriculum learning. And this is really realized by sampling goals according to their expected absolute learning progress. So in practice, there are actually two kinds of difficulties that we need to solve. The first kind is how to estimate, how to track, how to predict learning progress for various kinds of goals. For this, we develop specific regression models. And another kind of technical difficulty is how to find efficiently the niches of learning progress. For this, we've been using bandit algorithms such as the X4 system that are especially made for non-stationary bandit system. And here, if the utility of the bandit is learning progress, this is indeed a non-stationary problem. So today, what I want to focus on is not rather how to solve these technical problems, but rather what are the good properties of these sampling skills when you can estimate well this LP. So on the right, we actually see the emergence of a learning curriculum, where on the top, you see the progressive acquisition of skills of increasing complexity. And on the bottom, you see the estimate of learning progress, which is proportional to the probabilities to select each goal type. And then we can check actually that there are 4 goal types, 4, 6, 7, which are actually the unlearnable ones in this environment. And they are indeed very little sampled. And so basically the system has learned to sample the goals of appropriate complexity, avoiding those that are either too difficult or too easy. And a very good property of this goal sampling scheme is that it can address one particular problem that we have when we use parametric models such as neural network, which is catastrophic forgetting. So catastrophic forgetting happens when sometimes with neural networks, when you train them on new tasks and you don't train them anymore on past tasks, and basically sometimes it erases what was learned about the previous task. And so here we see this phenomenon on the left, when after mastering the green type of goal, the robot focuses on the yellow one, and this actually leads to a drop in performance of the green type of goal. But this is catched by the estimate of absolute learning progress that we see in the middle, as there is actually learning regress, and as we are looking really at the absolute value of the derivative of the learning curve, we can spot that. And then, so the green task is repractice again due to the bandits maximizing the absolute value of the derivative. And then this leads to reacquisition of the task. And at the end, everything ends up being mastered and well memorized by the neural network. So now I'd like to discuss how it's possible to learn those goal representations. So in the examples I discussed so far, it was the engineer who was provided already a representation of a goal space. It could be complicated. For example, in the map-edit example, or if in the modular trajectory example of the humanoid robot I described, it was a complicated goal space, a large goal space. But still the engineer provided that goal space. But then the challenge is how you can learn a goal embedding. For example, when you have robots that are perceiving raw images. So one natural approach has been to train a generative model, such as variational autoencoders, to learn an embedding of images and to sample the goals in that embedding. So this was made, for example, in the RIG system with uniform sampling in the prior, or with UGL or SkewFit, where goals are sampled on the frontier of the known distribution. That's actually implemented a form of novelty search. So the advantage of this is that it enables much more autonomy as compared to the systems before. But yet these systems were not robust to environments with distractors, or simply large environments with multiple objects. So one way to address this has been actually to use forms of unsupervised learning of generative models that learn disentangled representation of the environment. So one of the first kind of model that were used in this direction was the beta variational encoders. And basically the idea is that this neural generative model tries to learn a latent space where latent dimension of the embedding correspond to independently controllable features of the environment. So for example, different features of different objects. And while learning this embedding, one thing that is possible is now to use that to do modular goal exploration by sampling only target values of a subset of those learned embedding dimensions, which basically correspond to sampling target transformations of particular objects in the environment. And we can use, again, learning progress in that embedding space to organize also the exploration in a way that is very similar to the humanoid experiment I showed before, except that here, the features, object-based features, are learned from images. Okay, so I'm late, so I will be fast, but just to explain that what's interesting is that when you use learning progress to sample goals in that embedding, it's not only useful for efficient exploration, but it's also a way to discover actually which of the embedding dimensions that are learned correspond to learnable objects and which other to uncontrollable objects, which can be very useful. And here, these are curves showing the evolution of the diversity of acquired skills, basically showing that with the learned modular goal embedding I just explained, we can basically reach performances that are very, very similar to hand-defined modular goal spaces, and much better than either using flat goal spaces, even if they are hand-defined or learned, and much, much better than random exploration of the parameters of the policy. Okay, now I'd like to discuss another topic which addresses another limit of the approaches I discussed so far. And I'd like to introduce the concept of meta-diversity search, as well as to put back a little bit the user in the loop. So all the approaches to learn a goal embedded I discussed so far basically assume that the intuitive notion of diversity can be captured within a single goal representation space. So this limits the scope of the final discoveries, which might be diverse in the chosen goal embedding, but actually poorly diverse in other potentially interesting ones. So again, if we look at children, it seems intuitively that they represent their goals in different ways, depending whether they aim to build a Kaplan structure or prune a tree in a certain shape, or do a skateboard trick, or even aim to cook a meal of their invention. They don't represent their goals in the same way in those different contexts. And so to address these limits, we've recently formulated the problem of meta-diversity search as a problem where an agent incrementally learns a set of diverse goal embedding spaces in an outer loop and searches to discover and achieve diverse goals within each of those goal embeddings in an inner loop using an IMJEP. And so we also considered how, with minimal external feedback from a human user, the agent should be able to efficiently specialize the exploration strategy toward the human initially unknown preferences. So to solve this meta-diversity search problem, we've been developing an IMJEP approach that incrementally learns a hierarchy of diverse goal embeddings. This is something we presented at NeurIPS last year. So the hierarchy starts with a single variational autoencoder. Actually, you could apply the same idea with other kinds of generative models. And this generative model is incrementally trained on the incoming data and encoding it into its latent space. So when the reconstruction loss of the VIE reaches a plateau, a split is triggered and two child networks are instantiated. Then there are lateral connections between the parent and the child VIE, allowing the child VIE to reuse its parent knowledge while learning to characterize novel dissimilar features. And each new observation falls into one of the leaves corresponding to different goal embeddings. And this is updated and split again recursively. So basically, all the leaves form a set of goal embeddings, and goal sampling is made here in a hierarchical manner. First, you sample a goal embedding, and then you sample a goal inside it. So to quickly adapt the search toward the preferences of the external user, then it's possible to ask the user to assign an interest score to a different leaf nodes when there are splits. And this is both simple and relatively rare. So one can prioritize exploration in those models, in those nodes, in the goal sampling strategy. So actually, this work was also the opportunity to explore what I think is a very important and interesting area of application of IMJEP algorithm, and which is quite different from traditional robotics. So basically, IMJEP can be used as tools to help scientists to make discoveries for complex systems in physics, in biology. And as you'll see in a minute, actually robots still play a role, but it's quite different from what many of you are used. So for example, a previous PhD in my lab, Jonathan Grisou, went to do a postdoc in a chemistry lab in Glasgow. And in this lab, they are studying the origins of life. And they want to understand how certain oil droplets with certain chemical characteristics can self-organize into protocells. And they discover that certain kinds of oil droplets have amazing self-organizing properties, such as what you see on the video right now on the screen. But they have no chemical model of those chemical systems. It's too complicated for existing chemistry and physics, so they cannot do any simulation. And they have very little understanding of what's possible to achieve in that complex system. Until very recently, they were just trying manually with their own intuition to make various kinds of mixes and observing what happens. A few years ago, they began actually to automatize the lab by building a robotic system that is actually being able to do the full experimental loop, mixing the oil droplet as you see on the screen, and then using a camera to measure the self-organizing system. And then what Jonathan Grisou began to do was actually to use the IMJEP system to drive exploration to do better than random goal exploration or grid search exploration. And he was able to show that if you do goal exploration with those systems, you can actually discover a much wider diversity of chemical and physical structure that you can do. And so we began actually to launch a research program on this topic. And we are also using now digital systems like continuous game of life to study them. And then we've been using the representation learning for metadiversity that I just presented before to you. And using that to discover new structures in continuous games of life, we could actually show the discovery of novel structures that people studying cellular automata were not able to find in a systematic manner before. So for example, we were able, so here there was a video, we were able to find some kinds of system generating gliders in those continuous game of life, which was only known in discrete game of life so far. And then we were able actually to show how it's possible to guide the system with very few input from the human. For example, imagine you have a human who wants to have localized patterns like little creatures in those game of life system. We see the evolution of representation and discoveries on the left that's specializing to this. But if you have a user who wants to find Turing-like patterns covering the whole screen, then you have the system discovering, making a different specialization on the right and making different kinds of discoveries. Okay. Just in 1 minute, there is a topic I will not have time to discuss, but I'll just mention it for those who want to take that offline. Another branch of work we've been doing, and that's very important in the recent years, is to go to a more abstract kind of goals, which are goals based on using natural language. Like children use a lot of language to imagine abstract goals and to simulate imagination. And basically, we've developed a system called Imagine, we presented also last year at MIRIPS, in which basically an agent initially interacts with a social peer that is using language to describe what the curiosity-driven agent is doing in a Minecraft-like environment. And then actually the agent is internalizing the model of language and the model of the social peer in such a way that later on, when it is alone in the world, it can reuse language to imagine goals and to imagine how a goal achievement function for those goals could be. It's like internalizing in the head a model of the social peer when the social peer is not there anymore. And we show that using language powers very efficient creative forms of exploration, enabling the system to make discoveries out of distribution much more efficiently than if, for example, you would use low-level concrete kind of goals like in the system I presented before. Okay, but I will conclude here, and I thank you very much for listening. Thank you.
Thank you. Thank you, Dr. Pierre-Yves. Any questions? I have one question, Dr. Pierre-Yves. So could robot be a scientist, like a physicist or biologist, to do curiosity-driven research? So what's the goal then?
So the goal, as I said, is to help the human scientists to make discoveries. So for example, as I said, in the system I was presented here, this is a real chemistry lab with real chemists. And they were really like in front of a major problem. They have a complex system. They want to study to unfold big mysteries of the origins of life, but they have no model of this system. They cannot make any simulation, and this is very costly to make experiments in the real world. But still, they don't know how to organize their exploration and how to map the space of possible structures in this complex system, from which they might base building a mathematical or a physical model of what's happening. And so here, basically what we are doing is that we are providing a set of algorithms that actually the physicists can influence or the chemists can influence in various ways. And that's going to help him or help her discover and model much more efficiently the complex system he is trying to discover.
Thank you.
We have a question from the audience here.
Hi, Per-Yves. Thanks a lot for this great overview. I have a question. So in this intrinsically motivated behavior is, of course, great. We are also working on it, of course. But if you have a big space, then it's very difficult to not just go for completely useless kind of goals, right? So you explained a little bit with the language and so on. So what other types do you see to incorporate usefulness or task behavior into this realm?
Yeah, are you still seeing my screen or not? Maybe not. Okay, whatever. So thank you very much for this question. So indeed, actually, what I didn't have time to explain in the last part of my talk is that actually language is precisely one approach to deal with this problem. Indeed, as you just say, if you let an agent learn its own representation in a way that's not at all influenced by any human, there are so many interesting structures in the world that it could actually go in a direction that may encounter obstacles, because it's like a little scientist. He's discovering the world, and if he's not reusing knowledge of others already exploring a particular path, he may actually go in a direction where he discovers that it's actually blocking, and so time is wasted. And so one way to do much better than this is indeed to leverage cultural knowledge already acquired by others exploring the world. And the way to acquire cultural knowledge is by, one very important way is by using language as a way to transport not only a language model, but also a model of relevance. So for example, when a human is describing what a robot is doing when he is exploring through curiosity, the human is not going to describe anything. The human is going to describe only things that are of interest to the human brain, and so things that are relevant to the human brain. And so the language, the rules of grammar, but also the lexicon will actually convey a model of relevance. And then this is exactly this model that's going to be internalized and reused by the system later on to imagine and to generate those goals. And so because it will be influenced by this, it will lead actually the system to explore kinds of goals that have a much higher probability to be of some form of interestingness to the human. And it will actually channel very much the system in a particular way. So I'd say that to me, language is one of the important ways to do this, but that's not the only one. As we saw in my talk about the system for helping scientists to make discoveries, we are actually using a very simple way to have the human in the loop to actually push the system towards exploring certain kinds of patterns as opposed to other kinds of patterns. This is relatively simplistic, but still it can strongly influence the exploration. And that's another way to drive the system.
I think that's probably all the time we have for questions. Yeah.
Yeah, there's an online question. Thank you for the very interesting presentation. So my question is about what would be a general way to quantify the results of intrinsically motivated behavior? As for example, learning improvement depends on the expressiveness power of the model and the coverage of the goal space. Even when using dimensionally reduction like a VAE, it is still hard for vast spaces.
Yeah, so there are several questions. Maybe the main answer would be that when we evaluate those kinds of systems, we never use only one measure. And the reason is that those systems can be actually very useful for various downstream tasks. So for example, one example of a downstream task would be that you want that the discoveries made by the robot lead to an efficient model of the world that can be used for many other purposes. For example, model-based reinforcement learning for solving external tasks. Another kind of downstream task might not be directly to build the model, but for example, for the physicists and the biologists here, you just want to have a map of the different possible outcomes. Another kind of downstream task, for example, in the language case, could be not only to make discoveries, but also to generalize better in language comprehension. So for example, in the language system I mentioned at the end, when the agent is exploring by itself by setting its own goals and trying to achieve them, it's not only a way to improve discoveries and exploring the world, it's also a way to train its own policies to generalize in new situations without the help of the social peer. So basically, it enables the system to generalize better the understanding of language sentences with lower number of feedback from the social peer. And so basically, in that case, for example, one of the measures that we use for evaluating the system is basically how much the train policy generalized on the test set of linguistic commands with various, actually we consider various kinds of test set because there are various kinds of generalizations. So we can use this, we can use those measures of coverage when of the space when what's interesting is the diversity of discovered outcomes. We can measure different cost functions about the learned world models. So we always use basically a battery of tests rather than a single test because those systems can be useful for a diversity of downstream tasks.
Okay, let's finish the question. Let's thank Dr. Pierre-Yves again for this exciting tutorial. Thank you very much, and thanks for everyone. And okay, let's have a 30 minutes break for the next oral session. Thank you all. Bye.
Thank you.
What you had to know. Tomorrow wasn't here, but you had to go. I could feel the tears deep down in your soul. Took away the pain so that you could glow. Sometimes they'll test your soul. Just stay true. Sometimes we just don't know. The light shines through. Sometimes you have to go, and I'll go too. Sometime real soon you'll glow, shine bright through. Take you. The light is there to hold you down. Take you. The light is there, you're bolder now. Wake you. The light is there to show you how. Break you. The light is there, it's over now.
Touching slow motion, don't wanna say goodbye. Hold on to all of the memories, everything we've been through. Hoping the day I come back here, you're gonna be there too. And I'm watching you leave this place. You come and you go like the ocean wave. But I'm keeping you on my mind, 'cause all of the memories still make me smile. Hold on, I'm drowning in feelings I can't seem to hold back. Hold on, I'm craving for you, craving for you. Hold on, I feel like
chill. Warm is the weather, when we're together. Temperature rising, couldn't get hotter. Steaming up the car. Are we going too far? I feel the fire sizzling hot. It's getting toasty, like it or not. Melting when you leave. It's getting hard to breathe. When I see you in the morning light, the sun is beating down so bright, heating up between us two. Sun vibes when I'm with you. Somehow you give me chills. Heating up, heating up. Somehow you give me chills. Heating up, heating up. Somehow you give me chills.
Eyes wide, tongue-tied, midnight. You can say all that you want, but you and I were meant for this. You know, sometimes we hide behind this illusion that we're done. Oh, please see that you're wrong in this. I don't fall in love cause I'm here tonight. I don't wanna say it, but it just feels right. I think the girl just to pass the time. I want to stay at the back of your mind. Wasting it all for him, don't get me wrong, but I'm done with these games. I'll hold on to faith. You and I are stuck on this. I can't seem to let it go. It's not too late. Just don't lose your faith this time. I still feel like you lied about the way that you can't love. We should have never let this go. No, we were the catch on the summer nights. Kids in the street that got it right. Every time I felt to let go. Every time I felt to let go. Wasting it all for him, don't get me wrong, but I'm done with these games. I'll hold on to faith. You and I are stuck on this. I can't seem to let it go. It's not too late. Just don't lose your faith this time. You can knock me down, but I'll find a way. She said you don't know. She said you don't know. If this is what you want, if you wanna go, I'll have to go and let it breathe. But I'll be waiting here, you see. I don't know if everything will be alright. Sometimes you gotta let go. Guess I gotta let you go.
Come and have this drink beside me. Let's open up, girl, speak your mind. I just wanna have a conversation. No obligation, show me vulnerable. We ain't come here for no lonely night. We ain't looking for no shallow tide. Ulterior motives just put aside. A
appreciation we've been trying to find. We've been trying to find. We've been trying to find. So come and have this drink beside me. Let's open up, girl, speak your mind. I just wanna have a conversation. No obligation. Show me vulnerable. Show me vulnerable. No obligation. Show me vulnerable. Show me vulnerable. Yeah. Let's not come off too impressed. How about we just do our best to express what we're thinking? Don't even know your name, but the way you're touching me is telling me it's gonna change. Like, telling me it's gonna change. Like, we've been trying to find. So come and have this drink beside me. Let's open up, go speak your mind. I just wanna have a conversation. No obligation. Show me vulnerable. Show me vulnerable. No obligation. Show me vulnerable. Come in and just drink beside me. Let's open up, don't speak your mind. I just wanna have a conversation. No obligation. Show me vulnerable. Show me vulnerable. Yeah.
Hi, everyone. Good morning, or maybe good afternoon, I guess.
Hey, everyone. Hi, Luca. Hi.
Robots running wild out in the street. Skate decks, Wu-Tang, and the aiming beat. Everybody's got a Mickey in the sagged out jeans, puffing smoke like a fence, chasing dreams. Mama was alone at the rental home. Daddy was as cold as the northern.
Hello, everyone. Welcome to the oral session 5. And just to kind of shake things up, for this session we have 2 virtual session chairs, and that would be Laurel Pinto and Luca Carlone. So for the kind of, as a housekeeping, they're going to be running session remotely. When it gets time to ask questions in person, they can kind of hand it over and I can go and select kind of somebody from audience to speak. And without further ado, Luca and Laurel, are you guys there?
All right. Hi, everyone, and welcome to oral session number 5. I'm assuming that the attendees in person are able to hear me, possibly are able to see me. It's really a pleasure to be virtually at CoRL 2021. I am Luca Carlone. I'm associate professor at MIT. And I'm the co-chair of this session with Professor Laurel Pinto, who is an assistant professor at NYU. So this session, very excited to be the co-chairing this. This session includes 5 oral talks, oral presentations. Each speaker will share screen and present their work, and each talk is supposed to be 12 minutes plus 3 minutes Q&A. And we're going to balance questions from the live audience with questions from Feedloop. So I'm very excited actually to introduce the first speaker. As first speaker, we have Boling Yang from the University of Washington. And the first talk is going to be about motivating physical activity via competitive human-robot interaction. Boling, the stage is yours.
All right, thank you. I don't think my screen is, oh, there we go. All right, hi, my name is Boling Yang. I'm a graduate student from the University of Washington. In this project, I'm working with Donuts, Patrick, Professor Brian Boots, and Professor Joshua Smith. In this paper, we explore the novel idea of competitive HRI human-robot interaction. As the first step toward this idea, we make a robot companion that could make exercise fun and effective. In this talk, we'll first discuss the significance of competitive interaction and justify why we believe that it deserves increased attention in the robotics community. We've created a robotic system for competitive HRI research. We use a multi-agent reinforcement learning method to train our robot to play a competitive fencing game with multiple gameplay styles. And finally, we perform 2 user studies with actual human subjects to evaluate the system's effectiveness, user acceptance, and more. So why do we even care about competitive interactions? Indeed, there have been a lot of research on human-robot cooperation, yet not too much on competition. But when we take a closer look at competition from a psychological perspective, we'll find that they can also be beneficial. Psychologists have found that in an educational mathematics video game, competitive players have significantly higher performance and demonstrated higher problem-solving efficiency compared to individual and cooperative players. Moreover, competitive players also experience a higher level of enjoyment with an increased tendency to engage in game. And similar effects has also been found in physical exercises. In tri-mile running, cycling, and the plank exercise, the introduction of competitions significantly motivates human participants and resulted in improved performance. Therefore, if we avoid unhealthy competitions that narrowly and overly focus on winning. We imagine that a robot competitor could be motivated and could potentially inspire our improvement in a given task. On the other hand, creating a robot that can physically compete with humans is technically challenging. The robot needs to constantly reason about the human's intent and strategically control its high degree of freedom body to counteract the opponent's adversarial behavior while maximizing its own reward. With these technical challenges in mind, we've designed a zero-sum attack and defense game as the evaluation environment for our system and the user studies. We call it the fencing game. Each fencing game lasts for 20 seconds. The antagonist agent on the right will get 1 point by placing his sword within the orange spherical area located between the agents, and let's call it the target area. However, the antagonist will receive negative 10 points of penalty if his sword is placed within the target area and make contact with the protagonist's sword simultaneously. Meanwhile, the goal for the protagonist agent on the left is to minimize the antagonist's score by giving him this penalty. Additionally, the antagonist will get 10 points of reward if the protagonist's sword is placed within the target area, passively waiting for the antagonist to attack for more than 2 seconds. This will encourage the robot to play the game more proactively instead of just camping around the target area. Given this research problem, now let's briefly talk about how do we create a robot competitor with a PR2 robot. To create robot policy that can play the fencing game sufficiently well, we formulate the fencing game as a multi-agent Markov game problem and solve it with a two-phase multi-agent PPO algorithm. The first phase of training can be seen as a pre-training process, with reward shaping and an iterative training scheme that allowed each agent to learn the best response against the most recent opponents. Both agents were able to learn to move and understand the game rules very quickly. However, this kind of best response updates in multi-agent systems are known to be unstable because all agents are rapidly changing and they could chase each other around a low quality equilibrium and never converge. Therefore, we use the second phase of training to create a more sophisticated policy with different rewards and sampling strategy. The agents are rewarded solely with the game score, which encourage better exploration in their parameter space. In each iteration of training, one agent will play against a random version of the opponents from the history, which diversified the training samples. The new reward and sampling strategy allowed the agents to learn more complex behavior and improve the convergence property. To make the learn policy work well in both simulation and real-world setting, we choose to control our PR2 robot with a Jacobian transpose and a factor controller. And we perform system identification to tune the parameter for both the controller and the simulation model, such that the end effector dynamic of the simulated robot and the real robot are similar. For experiments, we performed 2 user studies. The first studies evaluate the system's effectiveness from 3 perspectives. First, we monitor users' heart rates change in all games. Second, we assess to users' subjective opinion toward our system with a modified technology acceptance model. And finally, we study the human learning effect in the game. The second user study compare an RL train policy with a strong heuristic baseline policy in a long sequence of gameplays. Before the experiment, we recorded the average heart rate for each subject when they are walking for 3 minutes as a baseline value. We found that subjects' gaming heart rates in more than 92% of the games were higher than walking baseline heart rate. And the heart rates in 1/3 of these games are actually significantly higher than the baseline. So we're talking about around 20% to even 58% higher, which is a little surprising, because given the amount of body maneuver required for the game is not that much higher than walking. So to try to explain this, we try to look into the subjective response and finally found that the increase of heart rate also corresponds to or correlated to cognitive effort and some noticeable emotional reaction that were triggered by the game, such as frustration, motivation, and intimidation. And we are glad to see that human subjects are very accepting of a competitive robot exercise companion. More than 87% of the subjects agree that the competitive games were entertaining, and more than 81% of them think a competitive robot exercise companion will be desirable in the future. And around 69% of them agree that a competitive robot could improve the quality of their physical exercise. The second user study compared an RL train policy with a carefully designed heuristic-based policy. Action noise was added to the heuristic policy to create randomness in the robot's behavior. Despite some subjects thought the heuristic policy had faster reaction, the RL train policy was actually slightly better in game score performance. We also found that an RL train policy makes it significantly harder for subjects to learn to make improvement over time. And the subject considered the RL policy to be more intelligent because of its defensive and diverse behavior. So in conclusion, by using a multi-agent RL method, we've created a robot that can sufficiently fight a human in a fencing game. And at the end, I want to emphasize that we are excited about our competitive HRI research, and we hope you do too. Because from the HRI perspective, it is a relatively unexplored area with many open questions waiting to be answered. And from a human control perspective, it is not easy to create a robot with body agility that is comparable to that of humans. So as our next step, we're trying to extend our methods for full body control competitive task. So stay tuned, and thank you for your attention. I'm happy to take your questions.
Colin, thank you so much. Great presentation, very cool work. I think we should have a time, for 1 or 2 quick questions. And maybe we can start from the questions from the in-person audience. For that, I think I will need the help from Alexandra or somebody who's in person there. And the catch here is that I don't think we are able to hear the in-person audience, it seems.
Test 1, 2, 3. Hello. I think you can perhaps type on.
Maybe as the in-person audience are thinking of questions, I can ask a question.
Right.
So it seems like this fencing game is quite an interesting game. I was curious if there are specific properties of this game which make it favorable to use in this multiplayer RL framework, and how did you sort of figure out that fencing is the game that you want to sort of have for this human robot competition?
Yeah, definitely. So first of all, the fencing game is actually a very challenging game, especially for learning. Because if you think about the antagonist's task, the antagonist needs to reach out and place his swords within the target area. But at the same time, this scoring behavior also corresponds to potential high risk, because the protagonist will try to catch the attack and give penalty. So this actually makes it both cognitive demanding and physical demanding. And also, one of the reasons why we choose to use this fencing game is because it's actually very fun. We have human subjects in our lab, and really exciting about the game, and playing nonstop. So yeah, and also, of course, the design of the game. Actually, we put a lot of thought on how to make like actual human robot competitive interactions, kind of like embeds the difficulty into this game. We're talking about like how to strategically maneuver their body to actually gain more scores and give penalty, something like that. So the idea is that basically the robot needs to learn to how to counteract the adversarial behavior from, for example, a human or other intelligent agents.
Thank you, Bowling.
So, Bowling, there are several questions. I think we have just 1 minute left, so I will ask you just to give quick replies. I will try to sample a couple of questions. The first one is about how many participants were involved in the experiments. And maybe, like, together with that, there is a question from Panag about what is the speed of the arm moving. So again, how many participants and what is the average speed of the arm?
Mm-hmm. Yeah. So for the first user study, we have 16 participants, and for the second user study, we have 10 participants. And for the average speed, I don't have an actual number on top of my head, but basically what we play on the video, like what you see on the slide, are the actual speeds of the robot and the human movement. And feel free to scan the QR code to see more game examples. So.
Okay, thank you so much. In the interest of time, we have to stop here, but feel free to follow up on the feed loop chat if you want to reply to the other questions. And I will, thanks, Bowling. I will pass it back to Lerrel for introducing the next presentation.
Hi, everyone. So now we'll move on to the second presentation of the session. So we have Erdem. Erdem, do you want to share your screen to see if it's all working? So Erdem will be presenting his work on learning multimodal rewards from rankings. And Erdem, feel free to take it away.
Okay. Do you see my slides now?
Yes, we see your slides.
Okay, great. So, hello everyone. I'm Erdem from Stanford University. Today, I'm going to talk about how we learn multimodal reward functions using trajectory rankings. This is a joint work with Vivek Myers, Nima Nari, and Dorsa Sarik. So let me begin with defining the standard reward learning problem. We have a user who wants a robot to perform a task, and this user has an internal reward function that he wants the robot to optimize. However, the robot doesn't know this reward function. One popular way to learn the reward function of the human is through comparisons. In this approach, the robot shows two trajectories to the user, and the user tells which trajectory they prefer. Based on their responses, the robot learns the underlying reward function. Let's consider an example scenario. Here, we have the red autonomous car who wants to make a left turn. So it starts turning, but then it realizes the blue car, which is coming from the opposite direction and was previously occluded behind the red truck. Depending on its policy, the autonomous car may make different decisions now. If it's using a reward function it learned from comparisons made by a timid driver, the car may stop and give way to the blue car. It could avoid an accident in this way. As a second scenario, we could think of a case where the data come from an aggressive driver. In this case, the autonomous car could try to complete its turn before the blue car reached the intersection. In both of these cases, our autonomous car was using the data from one of the drivers. And there have been many works around these ideas. Some of them directly learn a policy, whereas some learn a reward function that encodes the policy. What's commonly assumed is that the underlying policy, so the data, is unimodal. For example, in the driving scenario, we said the data come from one driver, either timid or aggressive. But what if the data come from multiple users who have different reward functions, and our robot doesn't know any of them? It doesn't even know who provided the data. In the driving example, this would be a scenario where the autonomous car was trained using aggregate data from both drivers. In such settings, we cannot really use standard learning from comparison techniques because the car would have an accident while trying to find a policy that's close enough to both drivers. This means we need to be able to handle multimodal rewards to learn successful policies. Although there have been many works for the unimodal reward functions, learning multimodal rewards from comparisons was not studied. Let me explain why multimodal rewards are more difficult with an example. Let's say we have this task where the fetch robot wants to learn how and which shelf to place the banana. Perhaps a user comes in and says they prefer the first trajectory, and fetch can handle this because it knows how to learn unimodal rewards. However, if a second user with different preferences shows up, then fetch will fail. In fact, it's doomed to fail. Let me explain why it's doomed to fail with a numerical counterexample. So we have two trajectories, Xi1 and Xi2. This first user comes in. Let's say their reward for the first trajectory is 2 and 1 for the second trajectory. Following the prior work, we model the user's comparison with the softmax model. So the probability that the user chooses a trajectory is proportional to the exponential of its reward. This model would give us these probabilities. Now, we also have the second user with different rewards and preferences. And let's say the first user provides 20% of the data and the second user provides 80%. Combining these, our robot would observe a data set that's 24% in favor of the first trajectory and 76% the second trajectory. Now, the problem is, I can come up with another pair of users whose rewards and preferences are different, such that with different data frequency, they also provide the same data. Our robot is only observing these data at the end. So from its perspective, these two settings are indistinguishable. It would have no way of identifying the underlying true rewards. In fact, researchers in ranking theory proved that you can always construct examples where learning multimodal or even bimodal rewards from pairwise comparisons is impossible. So are we done? Well, no, because we can think of some generalizations of the problem. Specifically, instead of learning from pairwise comparisons, let's say we will learn from rankings of multiple trajectories. So in this work, we are solving the problem of learning multimodal rewards using rankings. To reiterate, the robot is going to show multiple trajectories to the users, and it will ask them to rank these trajectories from best to the worst. We will have multiple users, each with their own reward function, parameterized by some omega, and the ranking query will be answered by one of these users with some unknown probability parameterized by alpha. And the robot will not know who responded to the query. Formally, we will be given a set of trajectory rankings, and these rankings come from M humans who may or may not have different preferences, and we want to learn the reward functions of these M humans. For this, we will first model how humans respond to these ranking queries. In this example, let's say the first user is going to respond to this query. Our robot, however, doesn't know this. So how does the human answer? He will first basically select this best option. So we again have these probabilities that are proportional to the exponentials of the rewards. The user's top choice will be a random sample from this distribution. Next, he will noisily choose his second best option. Now, the first option has already been selected, so we drop that. And the user's second top choice will be a random sample from this remaining distribution. Similarly, the process will repeat for the third and the fourth best option. This response model that I described for a single user is known as loose choice axiom, and it's a very standard model for rankings done by humans. Eventually, what our robot observes is only this ranking. It doesn't know which user gave this ranking. It doesn't even know the probability that this ranking comes from this user. So from the robot's perspective, we have this user model. It doesn't know alpha, but it observed this ranking. It will start with a prior over both alpha and the user's reward functions. It will then use base rule to update its posterior based on the ranking it observed. Note that this likelihood term here is just the response model that I described. So we actually know everything on the right-hand side here. And our robot will perform this posterior update for all ranking data it has. At the end, it will learn all reward functions. In fact, it will even learn the data frequency parameter alpha. Let me show you some simulation results. On this fetch robot task with the bimodal data, we observed that modeling the reward as a unimodal function failed terribly. There were many outliers because the robot was trying to come up with one mode that explains all data. To get nicer graphs, we had to also plot the median error. On the other hand, modeling the reward as a multimodal function using our mixture model gave much better performance and learning, both in terms of mean and the median. The results were similar on OpenAI's lunar lander, where we again simulated a bimodal reward. One question that's still remaining is how the robot chooses which trajectory to show to the users. For this, we developed an active querying method to increase data efficiency. How do we do this? In the unimodal case, this has been studied before. The idea is to maximize the mutual information between the reward and the user's response given the query. It's very similar in the multimodal case. We now need to maximize the mutual information for both the rewards and the data frequency parameter alpha. I'll skip the derivation, but this is the final optimization problem we ended up with. Here, all probability terms are easy to compute. They are just our response model. What is more tricky is these expectations, because they require sampling from the distribution of alpha and rewards, which is multimodal. In the unimodal case, the most standard approach is to use metropolis hastings for this sampling, but it's problematic in the multimodal case. For example, let's take this distribution with two modes. Metropolis hastings would start with a random point, and it would just remain around the mode that point is closest to. It wouldn't be able to discover the other mode in a reasonable amount of time. To handle multimodal distributions, we simply run multiple chains of metropolis hastings. So let's say we start with these three random points and then run three independent chains of metropolis hastings. As long as we have enough chains with a good coverage of the distribution support, we will have samples around all modes. The only remaining part is how to solve the optimization problem. In the case of query-wise comparisons, looping over all possible queries might be feasible, but it's not here, because queries consist of many trajectories now. Hence, we used simulated annealing to solve this problem. In the end, we compared this information gain-based active learning with random queries and volume removal-based active learning. We observed in simulations that it gives the best result on both the fetch robot and the lunar lander tasks. Here, the top plots show mean squared error between the parameters of the learned and the true rewards. And the bottom plots show the predictive performance in terms of log likelihood on a validation set of rankings. In both metrics, the information gain-based method increased data efficiency. When we look at the policies optimized with respect to the learned rewards, we again saw information gain outperforms random queries. And the difference is statistically significant with a paired sample t-test. Finally, we designed an online interface to conduct some user studies. In this interface, multiple people provided anonymous ranking feedback to the robots by ranking 6 trajectories from best to the worst. Let's watch the end result after 10 random and 10 information gain optimized queries. As you can see, both robots learned the preference of the first user, but the robot who makes the random queries hasn't properly learned the second user's preferences yet. It still drops objects out of the shelf, as you can see here. We also looked at quantitative measures, such as the predictive power of the learned multimodal rewards, just like in the simulations. In both the fetch robot task and the lunar lander task, the information optimized queries gave the best results. To summarize, we showed that ranking feedback allows us to learn multimodal rewards, and active query generation improves the data efficiency of learning. I want to finish with discussing some future work. First, there is still a gap in the identifiability bounds. We already know that in the unimodal case, pairwise comparisons are enough. Naturally, any size of ranking queries would also be enough. In the bimodal case, we showed pairwise queries are not enough. They cannot identify the underlying rewards. In fact, even ranking queries of size 3 are not enough. One needs at least 4 trajectories in the queries. Things get tricky starting from the 3-modal distributions. Here, theory tells us ranking queries up to size 5 are not enough. It also tells us ranking queries of size 8 or more can identify the underlying rewards. But we don't know what happens in the region in between. And this gap gets larger as the number of nodes increases. Another research direction is about the sampling methods. We used multiple chains of metropolis hastings, but there are other methods that can give better mixing guarantees. Finally, learning multimodal rewards from multiple sources of data is an interesting problem. Thank you, and I can take any questions.
Thank you, Adam, for the wonderful talk. So for questions, let's first see if the live audience in person has any questions.
Can you hear us?
Yes.
Oh, nice.
Looks like at the moment there are no questions, so you can go with the remote. We can talk.
All right. So maybe just to get started, so in this work, you assume that you have a discrete modes, right? So you have like either a bi-mode or a tri-mode. So there's a discrete number of modes. But have you also investigated what happens if you do not have a discrete mode and instead a continuous space of modes?
So yeah, we have discrete modes, but like for each mode we can have different amounts of data, and I think for like in practice that's enough, and I'm not really sure how would we have like how would we have like non-integer number of modes. So
I see. So I guess an example is that if I just show you a user behavior, how do you select that M number of modes, right? So if I just give you a bunch of experience, how do you know like a priori what the number of modes are?
Right. Okay, yeah, that's a great question. So what we do is the algorithm requires to know M. But it's actually very similar to like unsupervised learning. Like it's similar to clustering. Like in clustering, you need to know the number of clusters, but what you can do is you can try different numbers and you can get an error curve to identify the trade-off. You can find a good balance for the number of clusters. So it's very similar here. You can start with only one mode and you'll probably get a high error rate if the underlying data is not unimodal. So you then go to 2 modes and like eventually at some point your error is going to plateau. And then at that point you can say, oh, this is a good number of modes that I can assume, and you can just use that.
I see. So in some sense you can keep incrementally increasing the number of modes and see at what point.
Yes, exactly.
Yeah. Thank you. Let's see. So if there are no more questions, maybe we can go on to the next presentation.
Perfect. Thanks, Erdem. Thanks, Lerel. So we're going to move on. The next talk actually is going to have 2 speakers instead of 1. So I'm happy to introduce Aviral Kumar and Aniket Singh from UC Berkeley, and they're going to tell us about their work on a workflow for offline model-free robot reinforcement learning. You guys take it away.
Yeah, thank you very much for the introduction. Yeah, hello everyone. I'm Aviral Kumar, and today with Aniket Singh, I'll talk about a workflow for offline model-free robotic reinforcement learning. And this is joint work with Stephen Tian, Chelsea Finn, and Sergey Levin. So standard online reinforcement learning algorithms typically train via trial and error. That is, the agent unrolls its partly trained policy in the environment, uses it to collect more data, uses the collected data for improving its policy, and then repeats this process all over again. In contrast, offline reinforcement learning algorithms aim to learn from a previously collected dataset of past interaction. And this dataset can come from prior RL runs, human demonstrations, scripted interaction, etc. And the agent is not allowed to access the environment, as in it's not allowed to do any online rollouts over the course of training when it learns a policy. So such a scheme is quite attractive for a variety of reasons. For example, it allows us to potentially use large general purpose the large general purpose datasets of experience to train policies that can effectively solve multiple tasks. And it also removes the need for any unsafe or expensive active data collection in the real world over the course of training, which is especially a quite important consideration in the robotics domain. So in this work, what we want to tackle is what would it actually take to apply these offline RL algorithms effectively into robotics? And there are many recent algorithms that have been proposed, but what would it take to take them from this algorithm design standpoint into like the real world? And to answer this question, let's first ask the same question in the context of supervised deep learning, which now has made its way to the real world. And I would argue that there are two key factors here that make supervised deep learning perform well. The first is the choice of a good algorithm, which is in supervised learning, just running stochastic gradient descent on a cross entropy objective with a large network, which works pretty well. And the second is what I would call a workflow, which basically is a set of guidelines on being able to make design decisions to tune various aspects such as network capacity, regularization, and hyperparameter tuning. And such a workflow basically enables a practitioner to take this general purpose algorithm and adapt it to the best design decisions for their own task that they care about. For example, in supervised learning, you could have a held out validation data set. You could measure the loss on this validation data set, and you could use this as a proxy for your test performance. And you could do all sorts of good things with it, like you can do early stopping, increase your capacity, add regularization, etc. And this works pretty good in practice. So we already have good offline RL algorithms out there, at least from a benchmarks perspective. So how can we tune them, or how can we design a workflow for them? How can a practitioner take them and adapt it to their problem? And so it turns out that one of the bigger limitations here for offline RL is that most of the procedures for tuning offline RL methods currently actually need to do online rollouts in the real world to select policies, to select hyperparameters. And this essentially just defeats the purpose of offline RL in the first place, because you are essentially, in a sense, running partly trained policies which could do all sorts of crazy things, like crash your autonomous vehicle into a tree in the real world, even though it's just for evaluation. But you don't want to do that because it can be a matter of life and death, basically. And so, in some sense, the key question here is we want to be able to tune these offline RL methods also in a pure offline manner. The conventional wisdom here, which has been studied for a long time now, is we can do this via off-policy evaluation, or OPE methods, which basically take in a policy that is given to it, and they would try to estimate how good the policy is by estimating its value function, return, etc. Now, these methods are good because they don't care about where the policy comes from. But the biggest limitation, which is really the big practical challenge with these methods, is that they have hyperparameters of their own, which are pretty similar to conventional offline RL algorithms. And recent works have shown that tuning these hyperparameters of off-policy evaluation methods is already an open problem that cannot be solved in an offline manner. So in some sense, you haven't solved the problem, you just delegated it to like a different step. So what we do in this paper is we consider a different view on tuning offline RL methods from the perspective of designing a workflow, which is basically, what does that mean? It means, given an offline RL algorithm, can I find a way to tune its hyperparameters? The good point here is that there's no additional hyperparameters that are introduced. It's just the algorithm that you began with. And also another good point here is, if you think about this from the perspective of choosing between various policies that you can train, now in this case, you only are concerned about choosing between policies that your algorithm produces. So that your offline RL algorithm that you are well aware about because you are trying to tune this on your task, only that algorithm produces those policies which you are sort of tuning from, and which is a much easier problem than this general purpose like policy evaluation type formulation. So the key question that we want to answer here is, can we devise a set of sort of offline metrics, pretty much like sort of validation error that practitioners can track, and then a set of guidelines that can allow practitioners to interpret the values of these metrics and accordingly adjust various knobs of their offline algorithm. And this hopefully allows us to get like much better policy performance. Okay, so before diving down into our workflow, let me very quickly go into what offline RL is about, what kind of challenges are faced, and what algorithms have been proposed. So if you take a standard RL algorithm, such as Q-learning, where the Q value is sort of an estimate of how good an agent is doing in terms of its long-term return. So this is the agent's estimate of how well it is doing. Turns out that in offline RL, often at times you have a limited data set. So the actions that you use to compute target values for training your Q function might actually be unseen and might actually be out of distribution of the actions in your training data set. When you use these out of distribution actions with this max operator, that will inevitably end up compounding some sort of overestimation bias into your Q function because you are backing up from unseen values. And what effect this will have is that it will cause your learned policy to deviate away from your data set. So if your data set are these black trajectories, it will cause you to go to unseen regions, which the agent is thinking are quite good because they have really high Q values, but they actually may not be good in terms of the reward because I mean, those regions might just be like unsafe. It could be a car crashing on your road. And so several algorithms have been proposed here to tackle this issue, which are of wide variety, like algorithms that would penalize Q values to not be really high on these unseen behaviors, algorithms that would constrain the learned policy to be close to the data, and so on. And I would not go into these details here, but we will consider a class of these algorithms and try to tune them. So in this work, what we do is we try to consider offline RL algorithms that penalize Q functions, and we try to design a workflow for these algorithms. So the primary algorithm that I would want to briefly introduce here is this algorithm called conservative Q learning, which basically trains a Q function using a standard RL objective, which is Bellman error, temporal difference error, using the recursion that I showed on the previous slide. And it pushes down these Q values on unseen actions. So it just tries to make sure that you don't go to unseen regions by pushing down the Q values. Our workflow also applies to other methods like BRAC, which are methods that do similar things, but in a different fashion. And I'm not go into details here in the interest of time, but these are in the paper. Okay, so now let's come to the interesting material, which is how does our workflow actually work? So let me first present the schematic skeleton of our workflow, and I'll try to bring in connections to supervised learning. And then I'll go into the components of this workflow in the subsequent slides. So our workflow first characterizes the run of an offline RL algorithm as overfitting or underfitting. Now, in this case, overfitting is said to happen when the performance of the policy first increases and then decreases over the course of training when you do more gradient updates. Underfitting is said to happen when the performance of the policy is just low and does not improve much at all, and just saturates at a not so great value. Now, to address underfitting, we could kind of sort of at a very high level take some inspiration from supervised learning and do some kind of capacity increase of the algorithm. And this does not just mean increasing the network size, because the capacity of an RL algorithm can be quite complex. And I'll go into what this sort of means briefly. And for addressing overfitting, we could do some sort of capacity reduction and early stopping to find the policy with the best performance. Now, this might appear very similar to supervised learning in the sense that this is exactly what I do in supervised learning. But turns out there are many major differences in terms of how you would actually implement such a workflow in practice. And the reason is because here, I mean, I could define these things in terms of policy return, but I don't have access to the policy return in an offline manner because I cannot unroll my policy. And so just using just a supervised learning workflow where you could use a validation error is not going to work here, because here you care about policy return, not your training objectives, like not your training temporal difference error. And so it's a big problem as to how even you kind of measure these overfitting or underfitting effects in practice without access to online rollouts. And that's what we solve in our paper. So let's first consider the case of overfitting. So as I mentioned, overfitting refers to the case when the performance goes up and starts coming back down as you train more. Turns out that fortunately, for the case of conservative offline RL methods, we can detect overfitting by just looking at the trend in the learned Q values of the algorithm, and this can be done in a completely offline fashion. So if the Q values first go up and then start coming back down, this means that overfitting is happening, and we have a theoretical argument in the paper to show that this indeed means overfitting is happening on the policy return as well. And now what we can do is we could do early stopping at the point of the maximum Q value. We could add regularization to fix overfitting, to stabilize Q values, and so on. In fact, on this task that I show on the slide, and this is the plot of the Q values. So the blue line is the base offline RL algorithm, which is CQL in this case. So Q values go up and come back down. Whereas for the case of when you add regularization, you can stabilize the Q values as shown in this orange line. And as I just mentioned briefly, the policy you would want to deploy or select or early stop at would be the peak in the Q values here. Turns out that if you just measure the returns of all these policies, so just for analysis purposes, just to see whether our workflow is working, you'll find that these policies are actually good. So these are not the best policies, but they're pretty good. They're close to the best policy. And adding regularization does actually improve the policy performance by 2x. So in some sense, you can now freely deploy these policies without caring too much about, without being worried about whether they'll work well or not. Next, let's try to understand the case of underfitting. So in the case of underfitting, the performance is just worse and does not increase too much with more training. And to measure underfitting, turns out that, again, a very simple thing ends up working. And we show this in the paper as well, why it works, which is basically you could track the values of the training losses, such as the training temporal difference loss over the course of training. If this loss is kind of high and does not decrease too much, and the Q values are not reducing, so there's no overfitting happening and the losses are high, then we could kind of say that underfitting is happening. And we show this theoretically as well. To fix underfitting, we can either use big policy networks or increase the capacity of the Q function in some way, but that's not quite easy. And I would love to discuss with you more about, more on the poster about how you could increase Q function capacity. So as shown in this example, essentially the dashed lines, so these are two tasks in the real world, and Aniket will cover the results more in detail. But these two tasks, the dashed lines are the Q values learned by CQL. They're increasing, so no overfitting is happening. This is the Q value plot. But the losses for these dashed lines are pretty high, so they're going up even. And turns out that if you use a bigger network here, it's just enough to prevent this Q values from blowing up, and it reduces the temporal difference error as well. And as we show, it also improves performance drastically. There's also many other details here, like tuning other hyperparameters like the conservatism hyperparameter, etc. And a lot of these things are in the paper, and we would love to discuss with you on the poster as well, but I'll skip here in the interest of time. Okay, now Aniket will talk about evaluating our workflow on real robots.
Thank you. Empirically, we evaluate our approach on real robot manipulation tasks on two different robot platforms, the Sawyer and the WidowX. We utilize offline datasets collected by prior papers. There are three tasks of interest: placing a lid on a pot, opening a drawer, and a pick and place task. Let's first consider the Sawyer tasks and consider how to use our proposed workflow in these domains without access to any online tuning. In this domain, we saw underfitting occurring and thus used models with higher capacity as recommended by the workflow. We then evaluated the policies with and without the underfitting correction. From the baseline CQL algorithm to the workflow specified underfitting correction, we see an improvement in performance from 0 out of 12 to 8 out of 12 and 9 out of 12 in the two Sawyer manipulation tasks. Below, you can see the robot placing a lid on a pot and opening a drawer. We also used our workflow for a pick and place task on the WidowX robot. When we run CQL on this domain, we find that the Q values exhibit an increasing and then decreasing trend, as shown in the blue line in the plot. This is indicative of overfitting. Our workflow would then suggest to deploy the policy near the peak in the Q value in the real world, and this is indicated by the vertical green line. We then evaluated these checkpoints to show the effectiveness of utilizing this fix from our workflow and see an improvement from the baseline CQL algorithm of 3 out of 9 to 7 out of 9 with policy selection. Notice that the dataset collection policy only succeeds 35% of the time, so CQL does improve on it with the policy selection criterion. To address overfitting, we use the regularization of the Q function network as recommended by our workflow. As seen in the plot on the right, the regularizer gives rise to more flat Q values, which you can see in the brown line in the figure. This indicates that this regularizer is effective in preventing overfitting. The performance of the policy as a result is also reasonably flat, between 7 out of 9 and 8 out of 9, which allows a practitioner to choose any reasonable checkpoint during training. In summary, applying offline RL to real-world problems will require designing offline workflows, which requires making the behavior of offline RL methods interpretable. we present a first step towards devising an offline workflow without any online interaction for certain offline RL algorithms, which empirically seem to work well even on real robots. Some questions in this area pertain to devising theoretical guarantees for workflows of this type and utilizing validation sets. Finally, I would like to invite you to our poster and please check out our paper. Thank you.
Thanks, both. Great presentation. Thank you. So we are running a bit out of time. So they are suggesting me to just keep questions for this paper, but I suggest still to follow up in the chat to get maybe questions and try to answer them. Yeah, I'm getting like, live inputs here. Maybe there is a quick question from the audience. Let's try to get that. Otherwise, we'll move on. Alexandra, can you help us on that?
Hi, can you hear me?
Yes.
Cool. So thanks for the great presentation. I was wondering about the overfitting detection. So you mentioned that the Q values go up and then down, but in the offline learning case, I could also imagine a case where the Q network just has incorrect beliefs about the environment and goes up and stays up, and there's no more experience to kind of correct those delusions. Do you have intuition for why we don't see that pattern?
Yeah, that's a great question, actually. So that's a thing that actually I did not talk about too much in the paper. So as I mentioned, so if you can tune the conservatism hyperparameter in the offline setting. So remember that these algorithms are offline RL algorithms that are actually pessimistic towards unseen outcomes. So they are conservative. They prevent you from going there. So what we do actually, the complete procedure is to first tune the conservatism hyperparameter that will allow us to be pessimistic on these unseen outcomes. And so once you do that, you would not see your Q values blowing up and going up too much. So once you do that, and then if you fix overfitting and unfitting, you'll find that your Q values will go down and will not go up indefinitely because of the kind of algorithm and the knob that you tune here. So I'd be happy to discuss more on this, like in fact, even the math on this on the poster, if you're interested.
Perfect. All right. Thanks again to Aviral and Aniket. We'll move on at this point. I will pass it back to Lateral for next paper.
All right. So the next paper is presented by Harshit. Harshit, are you in the live audience? Because it seems like you are in the live in-person audience. Just want to make sure that you're all set up. All right. So Harshit will be talking about learning of policy with online planning. And Harshit, feel free to get started.
Okay. Hi, everyone. I'm Harshit Sikchi, and I'll be presenting our work learning of policy with online planning. This is joint work with Wengshan Zhou and David Hill. First, let me begin with an overview for the work. In this work, we present a theoretical analysis of H-step lookahead with a learned model and a learned value function. Then we go on to propose loop, an efficient and practical instantiation of H-step lookahead that allows for flexible policies during deployment. Finally, we show that loop achieves competitive performance in online, offline, and safe RL on tasks involving locomotion, navigation, and manipulation. So now let's dive into the details. Off-policy reinforcement learning has seen numerous successes lately in robotics due to its ability to incorporate data from a number of different sources. So here are some examples with like recent works from that use off-policy learning. There's kitchen manipulation, industrial insertion, and grasping. So in model-free off-policy RL for continuous domains, we typically have a model-free agent which typically has a value function and a parameterized actor. This actor will interact with the environment, taking actions, and store this transition into the replay buffer. Now this replay buffer will be used to train the value function. So there are several potential issues in this framework. First, when we, to update the parameterized actor, we typically take the maximum of the action values of the learned policy, of the learned value function on the visited states. Now, this makes the performance of the policy highly dependent on the quality of the learned value function. So if you have learned a good value function, that means your performance of the policy is going to be better, otherwise not. Now, unfortunately, value learning remains challenging due to a number of different issues. So previously, people have studied a number of different issues such as overestimation, divergence, instability, rank loss, delusional bias even. Now, another issue in this framework is that the parameterized actor typically is a neural network and is mostly uninterpretable and is inflexible during deployment. Now, H-step look-ahead has the potential to alleviate all of these problems mentioned above. So what is H-step look-ahead? In H-step look-ahead, we want to find a sequence of actions of horizon H that maximizes the cumulative return that we get. So formally, we want to maximize the L objective here, where L is given by the summation of rewards till the H-1 time step plus the terminal value function. So here tau represents the action trajectory, and we are taking the expectation under the stochasticity of the learned dynamics model. To use H-step look-ahead in the off-policy setup that we have mentioned before, we can just replace the parameterized actor that we have with this H-step look-ahead policy. So H-step look-ahead policies are useful because they reduce the dependencies of value function errors using model rollouts. Moreover, they offer a degree of interpretability that's missing in parametric methods. And also, it allows the policy to incorporate arbitrary constraints and behavior priors during deployment. These constraints can even be non-stationary. So in our work, we present a theoretical analysis of H-step look-ahead with a learned model and a learned value function. So assume that you have a dynamics model which has some error of epsilon m and an approximate value function that has an error of epsilon v. So in general, we can bound the performance of the H-step policy with the optimal policy with the expression given here. So the takeaway is that the H-step look-ahead can reduce the dependence on value functions by a factor of gamma to the power h-1. So also for bounds under some weaker assumptions than what's shown here, please refer to our paper. But eventually, all of the bounds will have the same structure that we have shown here. One major consideration in this framework is like, how will we learn the value function? So previous work, Polo, uses H-step look-ahead to learn the value functions. To do this, they sample a bunch of states or a batch of states from the replay buffer, run H-step look-ahead for each of the states in the replay buffer, and now each of this H-step look-ahead is itself an optimization procedure. And this computation can be very slow depending on how many samples you want to have in your batch, how much resources you have, and how many times you want to reuse your samples in the off-policy learning step. So instead, we propose to use a parameterized actor to learn the value function. Okay, so towards this goal, we propose Loop, which is an efficient instantiation of H-step look-ahead. In this, we have the H-step look-ahead policy that interacts with the environment, taking actions, and storing them into the replay buffer. This the value function will be learned using samples from this replay buffer in an off-policy manner using any off-the-shelf off-policy algorithm. One issue in this framework described just now is that we have a H-step look-ahead policy that we are using for deployment, and we have a parameterized actor that we are using for learning. So this makes it difficult for value learning because of the distribution shift that's induced due to the differing state action visitations of the H-step look-ahead policy and the parameterized actor. We propose to remedy this issue by bringing the H-step policy closer to the parameterized actor. And we refer to this issue as actor divergence due to the specificity of the two actors that we are using in this method. To do so, we propose actor regularized control, or ARC. We'll understand ARC by taking a look at this general constraint optimization problem for policy improvement. So what we are doing here is that we want to find a distribution of action trajectories that maximize the H-step look-ahead objective while ensuring that your distribution is close to some predefined prior. Now, in this case, for arc, we'll make the predefined prior to be a parameterized actor. Now, this optimization has a closed form solution, which just reweights the probability of trajectories from the prior with its exponentiated return. So in practice, we'll approximate this optimal action distribution by a Gaussian with mean mu opt and a variance sigma opt. And we'll refine the estimates of mu and sigma by using iterative importance sampling that uses the ratio of the probabilities between both distributions. Our final empirical estimator is simple and is based on self-normalized importance sampling. So finally, what we have here is like we are sampling trajectories from the parameterized actor, which is our prior, and we are reweighting them with the exponentiated return. So now we have seen that loop works for online RL by optimizing the expected sum of rewards. Not only can loop work for online RL, but we can extend it to offline RL and safe RL as well. In offline RL, we can use an offline RL algorithm instead of the off-policy algorithm that we had in loop. And in this case, arc will optimize for an underestimate of the expected H-step return. This is in line with previous work in offline RL. Also for safe RL, we can modify the H-step look-ahead objective by making arc optimize for the expected return while ensuring that your cumulative cost in the planning horizon is less than some threshold D. So now we test loop on several domains and tasks. First, we test loop for online RL. In this case, we build loop on top of SSE, which is our underlying model-free off-policy algorithm. And we test loop against different baseline, the model-based baseline PETs, model-free baseline SSE, and hybrid model-based model-free method, MBPO, value expansion, and loop SARSA. So loop SARSA is just a variant of loop where we use, where we evaluate the policy, the replay buffer policy into the value function. So here we see that loop SSE works competitively to MBPO in the locomotion task and outperforms it in the manipulation tasks. The manipulation tasks are the pen and the claw environment. We also see that loop consistently outperforms SSE, which is the underlying model-free off-policy algorithm. And this empirically demonstrates that trading of value errors with model error is indeed beneficial. We also study the necessity of arc within loop. So in the right plot here, on the y-axis, we have actor divergence. And this actor divergence measures the squared error between the action proposed by the H-step look-ahead policy and the action proposed by the parameterized actor. So on Walker 2D, we see that arc successfully manages to drive down the actor divergence. And on the left plot here, we can see that loop without arc does not learn anything. As we discussed before, loop can also be adapted for the offline RL setting, and in this case, we build loop on top of two offline RL algorithms, critic regularized regression and policy in latent action space or PLAS. So we see that loop offers an average improvement of around 15% on CRR and over 29.49% over PLAS. So here we have tested in the locomotion environments of the D4RL dataset. We also test loop for safety in the OpenAI Safety Gem environment, where we have the point and the car robots, and we want them to reach some goal denoted by the green circle there while avoiding some obstacles. So on the left plot here, we see that loop with the safety modifications, we call this variant safe loop, is able to achieve high performance orders of magnitude faster than the safety baselines, while still being safer than the previous safety baselines. We also test loop for safety on the drifting task, which requires long horizon reasoning. So here we have this environment shown on the left. We want this car to drift around the blue dotted circle while ensuring that it's always within the red dotted circle. If it goes outside, it gets a constraint violation. So we compare against a version of loop without the terminal value function, which is the pets. So we see that with the safe loop, we are able to learn drifting policies while still being safer than the baselines. And without the terminal value function, pets is not able to learn the drifting policy. So in summary, we present a theoretical and empirical benefits of S-step look-ahead. We propose learning of policy with online planning loop as a practical instantiation of S-step look-ahead. And we demonstrate the advantages of loop through online, offline, and safe RL experiments. These advantages make loop a strong candidate for robotics applications and also gives us flexibility during deployment. Paper code and more videos can be found at this link or by scanning the QR code here. And I encourage you to visit us as the poster 8 for session 5. Thank you.
Thank you, Harshit, for the wonderful talk. Okay, so let's take maybe a question or two. Any questions from the audience?
Thanks for this talk. It's a very cool idea. Can you talk more about the trade-off between model error and value error? Like if it's better to optimize for value error than model error, like is that always true? Are there scenarios where that's not true? And like if it's true, then why not just use model-free methods?
Right. So yeah, so that's one of the points that we have tried to show in this paper. So when you're doing model learning, you're using supervised learning, and you have this strong supervision over all the dimensions of your observation that you want to predict. But in value learning, for particularly function approximation, it's really difficult to get like accurate value estimates. So like, although the theory does not suggest a particular horizon that you have to use such that the model error does not overpower the value error, that we find empirically that model error is like tolerating some amount of model error is beneficial at the cost of like value errors. Yeah.
Any other questions from the live audience?
Yeah, hi. So I didn't understand very well if your method is model-based or model-free. So this is the first question that I have. If it is model-based, then I don't think it's fair to compare it to MBPO because there are competitive also algorithms like Dreamer, I would say. And if you are doing also planning, are you using cross-entropy method? How is this?
Yeah.
How is this done?
So for the planning, yeah, maybe I'll start with the first point. So MBPO is, so I would characterize our method as a hybrid method. It uses model-based as well as model-free learning. So that exactly falls into the camp of MBPO, right? Because MBPO uses SSE in its base and roll out some model-based transitions from sampling state from the replay buffer. So that gives us like a fair comparison with MBPO, but we are approaching it in we are using the model in a different way than what MBPO does. Second, just to be clear, can you repeat your second question?
How do you do the planning?
Yeah, so planning is not done via CEM. That's we do via ARC. We use iterative importance sampling, where we start our initial distribution with the trajectories proposed by the parameterized actor, and then we'll use that to refine our mean and variance using the iterative importance sampling process. So it's similar to CM, but
it's MPPI basically.
So MPPI uses the prior as the normal distribution of 0 and identity. Here the prior is different.
Okay.
So yeah, that's just a subtle difference, but yeah.
Okay. Yeah, just a recommendation. There are I think there are also other works that you have should have compared with, but yeah, I can tell you in the poster session.
Yeah.
Thank you.
All right, so with that, maybe we can end this talk and go on to the next talk. Luca, on to you.
Right, thanks for the excellent discussion so far. We're going to move on to the last talk of this session. The talk is by Sriram Saiva. It's about enhancing consistent ground maneuverability by robot adaptation to complex off-road terrains. Sriram, take it away.
Thank you, Luca.
So currently, I think we can see you, we can hear you,
Yeah,
and
yeah,
you're probably trying to figure out the screen share, right?
Yes, I'm trying to share a second screen right now,
Sure.
and I am not able to see the second screen on the Zoom option. So. Okay.
That works. Yep.
All right, cool. Sorry about that. Yeah. Hello,
okay.
and yeah. Hello, and welcome to our presentation on enhancing consistent ground maneuverability by robot adaptation to complex off-road terrains. This work was done as a collaboration between the Colorado School of Mines and the United States Army Research Lab. So in this research, we addressed the problem of enhancing consistent ground maneuverability, which enables the robot's actual behaviors to accurately match its expected behaviors, while also adapting to a variety of complex unstructured off-road terrains. As can be seen from the motivational videos, this is a common problem in real-world everyday navigational terrains. The challenge we aim to address is the inconsistency caused due to setbacks. Setbacks can be defined as the factors that increase the difficulty of a ground robot to achieve its expected behaviors. Example setbacks would include wheel slip, reduced tire pressure, heavy payload, etc. Furthermore, when robots are navigating over off-road forest environments, it's challenging for a robot to model all the unstructured nature of these terrains, as these terrains exhibit a wide variety of characteristics, including changing terrain types and slopes that cannot be modeled in a robot beforehand. We then develop an approach that enables in robots the ability to generate consistent navigational behaviors. Our approach learns offset behaviors that allows the robot to compensate for the inconsistency between the actual and its expected behaviors, without the need to explicitly model the various setbacks, while also adaptively navigating over the changing terrain types. In addition, our approach is also able to integrate multimodal terrain features to characterize various terrains and estimates the importance of features to improve robustness of the terrain adaptation. This is all implemented in a unified regularized optimization framework with a theoretical convergence guarantee. The key novelty of our approach is the introduction of a novel mathematical formulation to generate consistent navigational behaviors by learning offset behaviors. We also introduce a new regularization term to learn important terrain features from multisensory robot observations and fuse them together to improve the robustness of robot adaptation to unstructured terrains. We then propose a novel optimization algorithm to address the formulated regularized optimization problem with dependent variables and non-smooth regularization terms. Our optimization algorithm holds a theoretical guarantee to converge to a global optimal solution. And as an experimental contribution, we provide a comprehensive performance evaluation of learning-based terrain adaptation methods on a physical robot over a wide variety of individual and complex unstructured off-road terrains. We first formulate the problem of learning to generate consistent navigational behaviors using a regularized form optimization framework, which is parameterized by two different weight tensors. Our approach includes 4 variables. The first one is the terrain feature tensor, which contains multimodal terrain features from a sequence of multisensory robot observations. we then have a second variable, which is the expected robot behavior, which is used to represent the behaviors that the robot is asked to execute. However, due to setbacks in the terrain, this behavior cannot be executed accurately. And the resulting behavior is the actual robot behaviors that we see indirectly using SLAM methods. Finally, the fourth variable to our approach is a behavior difference tensor, which is used to store the difference between the robot's actual behaviors as well as the expected behaviors. Out of the two parameters, the first parameter is the weight tensor W, which we use to learn navigational behaviors from terrain features. And the second weight tensor U is used to learn offset behaviors from the behavior differences tensor. Then we formulate the problem of generating consistent behaviors as a regularized optimization problem with the weight tensors W and U as its parameter. And in our formulation, we aim to optimize these weight tensors. In our formulation, the first term in our equation is a loss function that is used to represent the error of modeling the actual behaviors using a combination of both robots' terrain features as well as its behavior differences. The second term is a regularization term, which is used to find the discriminative terrain features towards generating robot navigational behaviors. And finally, the second regularization term is used to find discriminative time steps from a history of sequence of observations towards generating adaptive behaviors, with lambda 1 and lambda 2 in our approach as being the trade-off hyperparameters which are used to control the amount of regularization. Then for any given time with robot terrain observations and behavior differences, consistent navigational behaviors are estimated using the following equation, with the first term in the equation denoting the expected behaviors that are learned and the second term denoting the offset behaviors. To validate our approach, we use a clear path Husky unmanned ground vehicle and perform two sets of experiments. The first experiment includes the Husky robot navigating over individual types of terrains, and the second experiment includes the Husky robot navigating over complex unstructured off-road terrains. And for both these experiments, the robot autonomously navigates from one point to another while adapting its navigational behaviors over the different terrains. And we implement our approach as a local controller that acts under a local planner to generate navigational behaviors and goes from one point to a goal position that the robot is given. We compare our method using with three different baseline approaches. The first method is learning from demonstration approach, where an expert human gives expert demonstration to robot for navigating over various terrain. The second method is multimodal learning from demonstration, in where the expert is the human, and then we use multimodal terrain features to learn as a representation learning method. The third method is the terrain apprenticeship and terrain representation and apprenticeship learning, which uses joint terrain representation and apprenticeship learning to perform terrain adaptation. We use the evaluation metrics of failure rate, traversal time, and inconsistency to compare the different methods, with failure rate indicating the number of times the robot fails to complete the navigational task. The traversal time being the time taken to complete the navigational task in all of the successful runs. And the inconsistency is the actual error between the robot's expected behaviors and actual error in terms of the robot's poses. For the two sets of experiments we use to validate our approach, the first set of experiment includes navigating over individual types of terrains. In this experiment, all the methods are trained and tested over 5 different individual off-road terrain tracks, including grass track, sand track, gravel terrain, a medium rocks terrain, and a large rock terrain. And during testing, no online learning is performed to perform on-the-fly adaptation. The second set of experiments includes navigating over 4 different types of complex unstructured off-road terrain types, including grass to medium rock transition, a grass to a large rock transition, the mixed terrain type 1, which is a combination of grass, gravel, sand, as well as rocks. And then there's a mixed terrain type 2, which is a forest terrain. In this experiment, no additional training is performed, and we use this experiment to show the ability of ground robots to generate consistent behaviors in unfamiliar and unseen environment. Shown here is a video where we compare the methods over large rock terrain. We observe that our method, all the methods except the learning from demonstration approach are able to successfully navigate to a goal position, whereas the learning from demonstration approach encounters significant wheel slip and is not able to reach the final goal position. In the mixed terrain type 1, which is a combination of sand, grass, rocks, and gravels, we observe that both learning from demonstration and multimodal learning from demonstration approaches get high centered in the terrain, and both the TRL approach and our approach are able to successfully navigate to the goal position given to the robot. In this video, we show the mixed terrain type 2, which is the forest terrain. We observe that all the methods, except our approach, they fail to reach the goal position with either colliding with the trees in the forest environment or getting stuck in the branches of the trees, whereas our approach is able to successfully navigate to the goal position. And finally, we also present a scenario where we see that all the methods actually fail in this grass to large rock transition, where specifically the failure occurs whenever the robot is trying to transition from the grass to the large rock kind of terrain. For the quantitative results, evaluation of all the methods are performed based on 10 trials over each type of terrain. So for simple individual terrain types such as grass and gravels, all the methods allow the robot to successfully traverse over the terrain. However, for more challenging terrain, especially the large rock, we see that both the learning from demonstration and multimodal learning from demonstration approaches have a high failure rate, whereas the TRL approach and our approach have a low failure rate. Our approach, however, has only one failure rate in the large rock terrain and outperform the comparison methods. In terms of traversal time, it is observed that all methods have a similar traversal time in successful runs, but both learning from demonstration methods show lesser traversal time compared to other methods of rocky terrain, suggesting that they try to traverse over this terrain as fast as possible, which is the main reason why they encounter a higher failure rate. Thus, the higher emphasis on high-speed traversal used by these learning from demonstration methods produces an unreliable system where the robot traverses whenever the robot traverses unstructured off-road terrain. We also observe that both the learning from demonstration approach and multimodal learning from demonstration approach do not perform well and have higher inconsistency value over the individual type of terrains, especially over large rock terrain type, suggesting that their actual behaviors are not actually matching with its expected behaviors. We also observe that the TRL has a lower inconsistency and performs the best in the grass rock terrain, but our approach is able to outperform all the previous approaches and obtains the lowest average inconsistency value. When observing the results over navigating over complex unstructured off-road terrain types, each of these methods have a higher failure rate in general, especially over the grass to large rock transition and the mixed terrain type 2. Our approach significantly performs the learning from demonstration approaches in terms of failure rate. And similar to the first set of experiments, we observed that both learning from demonstration approaches have a lower traversal time, suggesting they have higher traversal speed, which in turn lead to a higher failure rate. Moreover, we also see that the learning from demonstration approaches are outperformed by our approach in terms of inconsistency, which with the multimodal learning from demonstration approach performing the worst. So this result suggests that the robots need the essential ability to adapt with the terrains, then only they can reduce the failure rates whenever they are traversing in unstructured off-road real-world terrains. In summary, we introduce a novel method for enhancing consistent ground maneuverability, which advances the state of the art by enabling ground robots' actual behaviors to accurately match its expected behaviors, while also adapting to a variety of complex off-road unstructured field environments. Our approach also learns offset behaviors for the inconsistency caused due to setbacks without the need to explicitly model the various setbacks that we see in real-world environments, and also learns the importance of multimodal features, which in turn improves the accuracy of terrain adaptation. Thank you, and I'll take questions from the audience now.
Very, very cool. Thanks, Sriram. I think we should have time for a couple of quick questions maybe, and let's start from the in-person audience and see if there are questions there.
Hi, Shuren. So it's first of all, thank you for the nice presentation, and I'm very excited to see the robot being brought into the real world and actually being deployed in the wild. So I have a question regarding the intuition behind the fact that the proposed method outperforms the TRAL method, because if I recall correctly, in TRAL, you actually do representation learning and apprenticeship learning at the same time, and to solve the same problem, right? So why this more end-to-end approach as you propose in this work? So learning kind of like a residue on top of the like expected and actual actions, why it can outperform the previous TRAL framework?
Thank you for the question. To answer your question, the difference of our approach in a theoretical level is our approach acts as a closed loop controller. So it takes the feedback of recent behavior differences. So it sees if the robot is actually being able to produce the expected behaviors or not. And it keeps a track of what the actual behaviors the robots are encountering based on like a SLAM-based method. So if the robot is able to encounter, if the robot encounters wheel slips, our approach is aware of that. So just because our approach has this closed loop capability, it's able to outperform the TRAL approach. So when we see the TRAL approach, the way it works is it's an open loop controller where it just sees the terrain in front of it, and then it just executes the navigational behaviors. However, it does not have a feedback on how it is performing. So that's the main difference between these two approaches, and this is the main reason why we observe and performance improve.
Okay, thank you.
Maybe a quick follow-up before we move on to the next question. A quick follow-up on that. Since you're mentioning feedback control and so on, is there any connection with traditional techniques for control theory, like adaptive control or things like that?
The control is kind of an adaptive control, but the gains are fixed, like if we are just comparing like the learning. But however, what we try to do here is we take, so the first expected behavior generation is based on like representation learning. So it just uses like representations of the camera images that the robot has got. So, but in terms of like learning, like the adaptive control, it's just learning from representation again and seeing like which of the behavior differences are the most important to try to suggest like how to go forward. For example, if we take the difference from SLAM-based methods for a robot like Husky, just because we can control only 2 degrees of freedom with this robot, there are going to be certain behavior differences that are not going to be important. So with learning, we are trying to figure out which are the ones which are like most important, and we ask the robot to automatically figure it out. So
understood. Okay.
Yeah.
Thanks. Let's see if there is one final question from the audience, and then we'll need to wrap up.
I don't think there are any live audience questions.
All right, thanks. Okay, so at this point, thanks again, Sriram, for the presentation, and I will pass it back to Lerel for the closing remarks.
Yeah. So with this session number 5, oral presentations, it'll come to an end. Thank you again to all the speakers, all the in-person attendees, and our virtual attendees as well. Next, we'll have the interactive poster sessions and the demo sessions. And I hope you have a wonderful experience at the CoRL conference.